इसको, ठीक है? कि क्या है, जो भी प्रेजेंटेशन हो यहाँ से जिसको भी देना होगा ना वो यहाँ से कॉपी करना, यहाँ से रन कराना। हाँ हाँ, ठीक है, मैं वहाँ से भेज दूँगा।
Check. Check. Warm good morning to one and all the esteemed dignitaries joined over here in this beautiful session, second day. We are celebrating here today the Platinum Jubilee of IREL conducted by REAI and IREL jointly. So once again, before starting this second day, can I hear a round of applause from everyone who are connected virtually as well as physically? Ladies and gentlemen, the rare earth elements perplex us in our research, baffle us in our speculations, and haunt us in our very dreams. They stretch like an unknown sea before us, mocking, mystifying, and murmuring strange revelations and possibilities. Yes, we are talking about rare earth. Yesterday, we had a discussion about the global scenario. process, research and development, and of course, RE permanent magnet. Today, it's gonna be very specific because we would be focusing on intermetallic sessions, overview, applications. So, before I would start, would like to say that everyone requested to put their cell phone on silent mode so that there won't be any disturbances and your focus would be on the presenter and their specific talk sessions. When it comes to NALCO, the Navratna CPAC under Ministry of Mines, which is particularly a Group A CPAC, and from the first day of its operation till now, 37 long years, it had never looked back. It is adding to India's growth in every phase. And if I'll say that from last couple of years, under the supervision and visionary guidance of such an amazing leader whom we have as our Honorable CMD, none other than Shri Sridhar Patra, it's flourishing, nourishing in every forte. Since you got the hint that today our first speaker would be none other than the Honorable CMD of Sridhar Patra, I would like to welcome you, sir. And let me take you through his amazing profile. Shri Sridhar Patra is the Chairman and Managing Director of NALCO Aluminium Company Limited under the Ministry of Mines. Known for his simple living, high-thinking attitude, Mr. Patra has craved for a niche for himself and has earned the tag of a result-driven and team-oriented leader, which is proven. As a seasoned professional, he places a premium on discipline and accountability, possesses strong financial acumen, and inspire his team to perform to their very best, as evidenced in the highest ever bauxite production and alumina hydrate in 2020. Soon after taking over the mantle as CMD of Navratna PSU NALCO in 2019, prior to assuming the charge of CMD, Mr. Patra was the Director Finance of NALCO. Earlier, Mr. Patra had served as Director Finance of THDC India Limited for more than 5 long years. He has over 3 decades of experience in handling finance and accounts functions of public sector undertakings like Odisha Mining Corporations Limited, Indian Rare Earths, and Mangalore Refinery and Petrochemicals Limited in various positions. His expertise and exposure in corporate accounts, budgetary control, direct and indirect tax management, financial and business planning, financial evolution of contracts, cost excellence, and treasury function are assets any institution or company will strive and vouch for. Mr. Patra's promise and professionalism to all stakeholders, hands-on approach style, and sharp business acumen has endeared him to one and all. Born in the iconic city of Puri, Mr. Patra is a member of Institute of Chartered Accountants of India, a rank holder graduate in commerce from Utkal University, and holds an MBA degree in HR. He has contributed significantly as an academician to professional accounting institutions apart from his employment in PSUs. So, ladies and gentlemen, let's welcome Mr. Sridhar Patra, the Honorable CMD of NALCO, with a gesture of bouquet from our own CMD. Please put your hands together. Come on, everyone. Let's hear an inspiring personality and let's welcome Mr. Sridhar Patra on the stage. Can I request my team to please escort him?
Good morning to all. At the outset, I pray Lord Jagannath to shower His choicest blessings on all of us for a healthy life and healthy years ahead. I feel privileged to be here with my team IRNs and the dignitaries through virtual mode and present, ladies and gentlemen. I convey my deep gratitude for inviting me to participate and share my thoughts and feelings and throw some light on the bright metal aluminum. COVID-19 pandemic has taught us enough. New normal is a living standard we have to maintain for our safety and safe and healthy life. Now I introduce myself, whether I am a team of Ayarian or I am a team of Nalconian. I say I am an alloys. Rare earth is present and aluminum is present. So this alloy will give the best required result. I feel privileged as an Ayarian to stand here, and I feel privileged as an Nalconian to address my team Ayarians. Career journey is a long journey. 7 years experience what I gained in IRL helped me to go further and prove my credentials in other organizations as a effective professional. So the organization has completed 70 years, a long journey. So all the architects of IRNs who has retired, who has contributed for the growth of the company, I pay my respect from my heart. Their team effort has made the company to stand and come up to this stage. 70 years means it is matured. Matured means it indicates we have potentiality, and I'll just tell what potentiality, what experience the company has gained, how it will help. In a marriage party, the bride people told to the bridegroom, you come with barat, but ensure no elderly man accompanies you. The grandfather of the bridegroom, he said what to do. There is a debate in the house that whether we should take the grandpa or not. Then they said, ठीक है, we'll take him, लेकिन let him be in the vehicle dicky so that nobody will see, they will not count them. He said, okay, I am ready. With my experience, I have gained enough strength, I can survive even inside the dicky. Don't be worried. You take me in the dicky. Then they went, and the bride people welcomed the bridegrooms, and they said, one thing we agree, we will give our daughter get married. हमारा गांव में एक नदी है, that river is flowing. We want the river should flow with milk, not with water. If you can do it, you marry or not. Otherwise you go back. Everybody was fearing water is flowing in the river, how will make the river flow with the milk? Then everybody thought, ठीक है चलो वापस चले जाएंगे, यहाँ शादी नहीं होगा. The old grandpa he said, do one thing, ये एक छोटा सा बात है, why you will go away? You be here, marry, बहू को लेकर साथ में जाना है. Then he said, कैसे, what will do? Now you tell them, this is the answer, you tell them, then they will agree. Then the people came, and to the bride's father they told, we will flow the river with milk. Milk का इंतजाम क्या है? We have made arrangement of milk. आप नदी का पानी सुखा दीजिए पहले. Then we will see that the milk is flowing. We have made enough arrangement of milk. Then the bride's grandfather told, definitely some old experienced person has come. Then they found, yes, grandpa. So now IRL has reached the grandpa stage. The old experience, what they have made, they can establish better and perform better with different innovation and technology. I am confident. I speak this as a IRN. Now, aluminium. English alphabet 26. A starts, the metal fortunately starts with a aluminium. That means this aluminium has been accepted as a strategic metal, had been accepted as a green metal, had been accepted as the metal of the future. Why? Lightweight, weight to strength ratio, anti-corrosive, and the strength it possesses, and the applications are so much. You see, in the ancient past, during the British period, the people who were taken to the prison, they were served food in the aluminum plates. Those days we thought aluminum is a inferior material and the prisoners are served this. But today you see, we feel proud for use of aluminum. We fly in the sky, the aircraft, spacecraft you see, it is based on aluminum and its alloys. So the applications has increased over the years due to its various characteristics. So it has got the image, it has got the recognition as a green metal, future metal. A metal by repeated recycling does not lose its character or property. It holds the same character and property. And in India, we feel proud. It is the third largest bauxite producer and bauxite reserve in the world. Barring China, which takes almost 50% of the world production and consumption, 50 to 55%. Among rest, we feel confident. India is a self-reliance, India is a self-sufficient for this future strategic metal. The world average per capita consumption is around 12 kg. China is 24 kg, but in India it varies from 2.5 to 2.8 kg. Now, steps should be taken how to increase the per capita consumption and how we can reach at a height for the economic growth. In the Paris conclave, it was resolved that sustainable activities, mining activities, everything should be carried on in such a manner that there is zero carbon effect. If you work in this line, giving thrust or focus on renewable energy, definitely the role of aluminum comes first. When you talk about the smart city, the role of aluminum comes first. When you think about the space, role of aluminum based alloys comes first. So in so to say, everything from pin to cushion, now the thrust is only for lighter metal having better qualities, recyclability. Now this sector in India contributes direct and indirect employment, around 1.7 lakhs jobs with direct employment, whereas indirect employment is 3 to 4 times. So a small growth will result a more than proportionate growth in the employment. If you see the global scenario of production and demand, the production demand forces have marginal changes. Sometimes production is more, sometimes demand is more. In 2021, 68.3 million tons production, the demand was 67.4. It indicates 0.9 million ton more. But this scenario does not remain always that the production is more or demand is less. In past trend, if you analyze, the demand is also more where the production is less. In India, if you see, the capacity is more, but we are producing around 3.6 to 3.7 million ton of primary metal. 45 to 50% more or less we sell in the domestic market, and more or 50% more or less we export to different countries. So it is a great source of export earning, which will help the economic growth and build the foreign currency reserve. Domestic sale is also increasing, and we are giving thrust on the scrap recycling. Reason is, it does not lose its property, it is a power intensive. By scrap recycling, you will save energy. Saving up energy is also a conservation which goes in a long way. So, if you see what are the sectors which is major contributing aluminum or which needs major, in the global, if you will see, for example, you are purchasing a motor vehicle or you are purchasing a car. Which car will prefer better? Simple term, everybody thinks mileage. If the mileage is more, we see. But that mileage is the outcome of its weight and performance efficiency ratio. By using aluminum, the car will be lighter and the mileage will be more, and it is also a way of sustainable action point. So the transport sectors globally use almost 26%. India, it is around 21% aluminum use. Building construction, till now we have a thought process. When we are constructing a building, we think wooden doors, chowkats, frames, all we prefer as a wooden. By that time we forget cutting a tree, how it costs to me. We never think life cycle cost. If you can replace by aluminum, then there will be a huge savings in polishing, treatment and maintenance cost wise. And it has also a resale value once you remove and throw it. In building construction, in the developed countries, around 25% consumption of aluminum is made by the building construction. Now the concept is gradually switching over, and all big towers, apartments, verticals, skyriser, they are using aluminum sections. And in India, it is around 9% of the total consumption is found in the building material. Packaging, again, Coca-Cola, we say it is a dil ka drink. Bada bada advertisement. The can which you are using, it is made of aluminium. Because it is considered as the safe even for food preservation. The foils, wrappers, what we made for food preservation, all these things also made of aluminium. So this packaging in the developed country, it is almost 15% consumed. Now we are in India, it is almost 5%. Electrical. In electrical, India is much ahead than the global average. Global average is 11%. We are using 38%. Again, copper is a better choice. But we are preferring aluminium because of it is a cost driver. So the metal is such, apart from its use, comparative cost analysis if you will make, then it is also found economical in other response. So basic fundamentally this metal which we are considering, India has abundant reserve, we have adequate capacity, and the population what we have, young population, vibrant populations, we can utilize the same, then all the resources if sync together, it will give a better yield for the economy, and it will be one of the most important drivers for the growth and GDP. Now, this industry is more attractive because the future is visible and seen. As investors, if you want to invest money, even for this share, you will prefer which company I should send. They will say whatever return, I must be sure that there will be no loss. Then we can say aluminium is one of the sector where there will be no loss. Market fluctuation marginally may be plus or minus, but in the long term we will see there will be no loss. National infrastructure pipeline of 100 lakh crores, government has declared, and effort for renewable energy, solar, wind, electric vehicles, then Atmanirbhar Bharat, Make in India, Local for Global, all these initiatives what the government is putting and giving, this will result in huge requirement of aluminium. As against present, it is 3.5 million. We project it will be around 7 million at the end of 2030. So the requirement will be double. Now smart city, we are seeing everywhere the need of aluminium emerges. What are the things required for the growth of the sectors? There must be a policy. Government of India is seriously thinking to make a national aluminium policy, and there is a thought process to declare this sector as a core sector. This matter is under examination. If it will be declared as a core sectors, various freight advantages and others can be reaped by the industry. It will be cheaper, it will lead to the cost reduction, and it will be accessible for various applications. Collaborative and collective R&D is also required, because the consumption will increase, self-reliance will be established when we make our own research to make more and more number of applications. So intensive research is to be undertaken, and the combination of rare earth with aluminium will give a new dimension for the growth. So we have to make intensive research, and I request all my IRN teams Any research required to be taken jointly for rare earth and aluminium, I assure NALCO will join hands for carrying such research which will give the progress path of both the CPSE. Another thing we have to think, you people might have attended some functions. After the function is over, if you go to the dining place, you will see people have taken the lunch or dinner and those plates they have left as such, and people will feel perhaps there is some, nobody was there to organize and manage this. Those collections of residuals, plates, making it clean, that indicate how efficient you are. The scrap will generated from increased consumption of aluminium requires effective collection, systematic collection in an organized way, segregation and recycling. It will give employment, it will save energy. So we must think to have a effective system of scrap collection. In the Western countries, consumption is more, and they have also kept as effective scrap collection systems by which. And in our culture, if we use, nowadays we are putting various bins, recyclable bins and non-recycle bins. Still then we are not conscious, we are putting recycle in the non-recycle, non-recycle in the recycle. That culture needs to be developed so that the scrap, what will realize and what will collect, that should be effective network. Rare earth and aluminium alloys having wide application. Cerium has been added with aluminium, which is extremely helpful to cast all aluminium alloys. It has huge demand. Scandium aluminium alloys have a great demand for aircraft and aerospace. Aluminium alloys developed with rare earth will give a better life with new features. So intensive in-house research should be taken. Nowadays in the MOU, they have put a conditions, if you do not spend 2% of your profit for R&D, there will be 3 marks minus for this. Earlier it was given as a 1 mark for the MO rating, but now they put, if you do not spend 2% of your average profit on research and development, there will be 3 marks minus. The intention is, it is to incentivize the nation. We should make intensive research and development. So IRL and NALCO, if joined together to make intensive research for doing any pilot plant and establishing commercial scale, then also it will give a long way benefit to the nation. The 70 years of experience of IRL, matured experience, and 38 years experience of NALCO, which is a youth is a mature person, will definitely give a better outcome, and I have that confidence. In long way to go, we will establish that both the CPSE has found out something which is highly helpful for the nation to make it is self-reliance. Red mud, which is a waste generated from the production process, it contains rare earth element. Yesterday, Dr. Saraswat was also giving emphasis that how to develop a system under a commercial scale to make wealth from waste with reference to the red mud. Some research can be continued, a team can be sent to our unit, they can visit and see what is the rare earth element content available, what is the cost economy. Cost economy you are thinking now because if you have sufficient supply. But mining mineral is a wasting asset. The moment you go on mining, it will be exhausted. By that time, cost is not a factor to be considered. So, in the long term, we should not think about the cost. First, we should find out some commercial scale for separation of the rare earth element present in the red mud, so that this red mud can give some value generation and employability. India is blessed with huge natural resources which is required for the growth of a nation. We are blessed. We have many metals and resources, almost 95 metals and resources are there. Optimal use of these resources will yield a long way. I believe this 2 days conference, 2 days workshop definitely ignite in the minds. If 1-2 product also comes out as a result, then the return can be considered as a manifold. Let us hope the conference will turn around and result in more impetus on the studies related to rare earth elements, which will secure the future of the nation and need of the country. NALCO is ready to join hands on this endeavor of ARL for development of rare earth element based aluminum alloys and extraction of rare earth element from the West. I once again congratulate IRL and Team IRL for successful journey over 7 decades, and I am confident the existing IRNs will take the company into a greater height and make it a vibrant CPSE. And by that time I will feel proud. I was also a Team IRN. So I wish a grand success in all future endeavors of the company, and these 70 years should be resulting some golden efforts, some golden outcome, so that 70 will write in the golden letters that this conference has resulted into this, and IRL hum chhenge asman, and Nalconian, the ordinary people with extraordinary attitude, the tagline of the company. If both will join, definitely they will create history, history, history for the country. Jai Hind, Jai Bharat. Thank you, Munmun, for giving me an introduction, and I suggested them to keep Munmun, because one is the moon, again here is the moon. So 2 moons will give better light. Thank you.
So there is a small token of appreciation from our end. We would like to thank you first, and after that our Honorable CMD sir would love to give a virtual memento to you. Can you please put your hands together, everyone? And now, since sir is there with us, he got some time from his busy schedule and mark this event. We would definitely like to present a physical memento. It would be given by Mr. Roy Chaudhary, Director of Finance, IREL. Sir, can we have you on stage, please? And we really loved, enjoyed and inspired how you managed the gap between being a IREan and now Nalconian. So I'm sure it would be inspiring to many one. So please put your hands together if you have really enjoyed the talk session. Thank you so much. I request our... Yes, sir.
I was born in the mines.
Okay.
Because I start my career in the Odisha Mining Corporation.
OMC, yes.
So iron, chromite, manganese, all put together they constituted me. Then I went to the rare earth. The rare earth gave me additional coating to make it still valuable.
Okay.
Then I went to the oil sector to become light to float.
Okay.
And then I came to the aluminum sector, anti-corrosive forever.
So now I would be using this as your introduction in further functions with your permission. Thank you, ladies and gentlemen. It was really delightful and an amazing session. Moving forward, we would be having someone very special, very noted in his own forte, and he is none other than Dr. Sanjay Kumar Jha, who happens to be the Honorable CMD of Medhani, and he would be giving his session on titanium alloys. First of all, I would like to welcome him. Thank you, Sridhar Patra sir, once again. Can we welcome Dr. Sanjay Kumar Jha? So we welcome you to this beautiful session, the second day of celebrating Platinum Jubilee of IREL family. My dear audience, valuable guest, there are many points which I can cite about Medhani and Dr. Sanjay Kumar Jha's association, but specifically in this note, I would like to give a deep insight, not a deep insight, but definitely I would like to highlight that Mishra Dhatu Nigam Limited, despite the difficult situation of COVID pandemic, is committed and always looking forward to target the new opportunities emerging from Atmanirbhar Bharat Abhiyan. What is the vision? What is the dream of our Honorable PM, sir? Numerous achievements and developments occurred with one of the very bright leaders association with Medhani, who believes that true leaders always focus on building other leaders rather than making followers. He is none other than, as you got the right clue, Dr. Sanjay Kumar Jha, who is the chairman and managing director. Under his leadership, Medhani has developed number of technologies in processing of ultra-high strength steel, Ni-based super alloys, cobalt-based alloys, iron-based super alloys, shape memory alloys, and titanium alloys. He has also led a team of scientists and engineers to develop near-net shaped titanium alloys casting for strategic applications. He has contributed significantly towards development of new process route to produce stringent quality ultra high strength steel rings and super alloy foreigners required for India's ongoing ISRO's Gangyan project. His long experience in thermochemical processing of materials used in nuclear energy and strategic applications such as difficult to hot work alloys 718, Titan 31, Titan 24, zirconium alloys of different grades, he has resulted in developing technology to improve quality and productivity in production of niche materials in Medhani. He has also contributed to development and complete indigenization of steam generator tubes of 700 megawatt pressurized heavy water reactor along with team of scientists from DAE. He steered the program to develop titanium and super alloys for aerospace applications. Due to his keen understanding and leadership, Medhani has been selected to participate in development of materials used in advanced multi-role combat vehicle AMCA program. His consistent effort has also resulted in Medhani developing alloy 617M and other super alloys for India's first advanced ultra super critical AUSC thermal power plant. Please put your hands together, and it gives me once again sheer pleasure to welcome Dr. Sanjay Kumar Jha. Thank you.
Your presentation is visible to us, sir. So your presentation is visible to us, sir.
Good morning. It's my privilege. Am I audible? Hello, am I audible?
Yes, sir, you are audible, sir.
Yes, please.
It's my privilege to be part of this very important celebration of 70 years for IREL. So let me first congratulate the entire IREL team, including the CMD IREL, for arranging such a unique event and giving me the opportunity to put my views here. What I would like to mention here that instead of going for the rare earths, I have selected alloys very important for our country, and where just similar to this, like zirconium, already IRL is contributing in the big way. So I am talking here about the titanium alloys and Midhani's contribution to the India's strategic sectors. And this is how the outline of my presentation is, that whereas first I'll give a very brief about the company, then different products, and especially focus on the titanium alloys, where we have contributed and what is the market scenario going to be in the future, and what should be our strategy for meeting the future requirements. As you know that Midhani is more than 40 years of expertise in the metallurgy and the manufacturing. And the main areas of focus in our products are in basically in the niche sector applications in defense, aerospace, nuclear, and strategic sectors. And we have made various grades of alloys, including the different grades of titanium, which I'll be talking subsequently. And with our versatility in our product variants, we are able to reach in the different sectors in different form of the products, which just I have mentioned here. We briefly, it is basically coming in the different form of ingots, slugs, forged products, rolled products, and drawn products. The varieties of equipments are there, different processes are there, and where we handle the various grades of alloys, including titanium alloys. And this is already known to this audience about the uniqueness of the titanium metal. It can be a very, very unique one, that is low density element and having high strength makes it very unique in application, and also it's getting the high corrosion resistance, especially against the very, very corrosive environment like seawater. And we have various properties, which includes also the biologically also it is compatible with the human tissues and the bones. So that gives a wide application of titanium alloys, and that's why it finds application in the different sectors. If I mention about the naval applications, missiles, aeronautical space, everywhere you'll find the titanium presence is there, and people are using titanium alloy in the different forms. Idani, as we know that we are located mainly in Hyderabad, but also expanding in the different areas, especially in the Haryana, Rohtak, and also in the Nellore with the aluminum alloy project, along with joint venture with the Nalco. As I told about the variants of the product, so that's why our process flow sheet and setup is very unique, where you will find that right from the raw material to the melting, forging, rolling, all these operations are there in-house under one roof, and which makes us to provide varieties of products to our different strategic sectors, which includes first starting from the sponge, which we are receiving in the form from right from the either from the domestic or from the international source. And then we go for this primary melting, which is very important, and which is a very unique type of melting, which includes the VAR. And also after that, we have a different high pressure, high force, the equipments, force press, 6,000 tons, 1,500 tons. We also produce the rings. We have the ring rolling facility, where we supply the rings of the various diameter, including up to 2.3 meter diameter of rings we can supply. And by the rolling, by hot and cold rolling, we can also go to the level of around 1.5, 1.67 thick, very thin plates also, sheets. Just a brief about the titanium, why it is very versatile in the application, because titanium, like you will find that there's a lot of there's a allotropic transformation is there. We have the alpha and the beta two phases, and because of that two-phase combination, this alloys can be varied in the properties by different combinations of the alloying elements and also in the processing techniques. That's why it makes us very unique. And whatever properties you can find in the steel because of the alloying, titanium also behaves in very unique way, and you can provide the different type of properties. And where we have the alpha, near alpha, alpha plus beta alloys, and beta alloys. So there are some 3-4 forms are available where people operate and select the alloys depending on this application. This is briefly about how the titanium alloy has been manufactured. Basically, we have a compacting press of 3,000 tons, where the sponge what we receive in the size of around 20-25 mm sponge will be compressed, and with the alloying elements addition, it will be compressed and compacts will be made. Those compacts will be welded by plasma electrode welding, and then these electrodes forms a very unique electrodes, and it will be finally melted under the vacuum, and the furnace is called vacuum arc remelting, and then you get the ingots after consolidation, and that ingots is the primary input material for processing the titanium alloys. This is basically the flow sheets. I have shown for the one application as such, but there are the various type of flow sheets being followed, where we have seen that one grade called Titan 31, which is workhorse titanium alloys, that is Titan 6Al4V, and that alloy is being processed here in our premises, and it goes from the different stages of the deformation, and subsequently it can be cold form, hot form, and then we make the product. So basically, for any other processing of any cast structure, the purpose is to how you can break the cast structure, refine that. Basically, the same type of system is being followed for titanium alloys also, where you have to go for the first breaking the cast structure and then the casting, and then after that, different stage of processing. Only that the different parameters will be quite different in the processing here. Now, since it's very costly and the alloys are weaker and its properties are data is not well very openly available, unless we generate some deformation studies we do, then only it is possible to understand its behavior, that how it is going to behave once the alloy is formed during the deformation. And there we use the thermomechanical simulations we use, and for basically the alloys unknown to us and some new developments, and that is where you use this equipment, and some of the cylindrical samples are prepared, and then you go for different temperature and the strain rate, and that decides our future course of action while processing the material. Just to give some science behind that, how we are using this properties and all, we developed some constitutive equations and then see that how the material is going to behave in terms of force, in terms of the strain rate, and those things we try to simulate and develop a domain of processing. It is called ISO efficiency deformation maps, where one can find out that what temperature and deformation speed is all right for a given sort of alloys, and that provides the clue for how to go for the selecting the processing parameters. So as you see that the right side, we have a very uniform grain structure, highly crystallized. So it is mainly because of temperature and the strain that has been selected very aptly and also the optimum way, and then that's why you can generate a very uniform microstructure. This is a deformation equipment we are having, 6,000 ton force press. We have 1,500 ton force press. Both equipments we are using for deformation and initial cogging of the ingots. Then it goes for further processing. You can see the ring rolling is there in the left side. Then we have the right side. We have one hot extrusion press. Ring rolling is made for the rings of different diameter. As I said, we are going up to the diameter of 3 meter. And then extrusion press I am using for the making the tube making. And Midhani has a well-laid quality assurance policy, since we are serving the defense, aerospace, and atomic energy and space sectors. So every area that our quality systems are defined properly, and then based on that, our the quality checks have been conducted right from the raw material to the finished product. And these are the different approvals we are having. And we are also trying to take, always trying to update our quality control system so that we can be aligned with the national, international, and national requirements. So these are different grades of produced at the Midhani. And I like steel, titanium also, the pure titanium is not so useful as such. So it has to be alloyed for different combinations. And you can find that the alloy combination like PT1M is the one alloy, Titan 11, Titan 14, Titan 21. All these things you will find that different combination of alloying elements are there. With titanium, you can find 0.4% aluminum. Some place there is a moly, some place you can find the tin, some place you can see the vanadium. So all these alloying elements combinations make this alloy very unique in properties. And then, as I told earlier, based on that, so there's a variety of grades, and origin of alloy is coming from the Western origin, Eastern origin. So depending on that, the alloying combinations also are being changed. And we are, all these listed alloys already we have developed, and then we have made specific to the different applications in our strategic program. Some of the grades which I have shown here, again, a very unique one, which we have developed for the different combinations. Aerospace application, I would just like to mention here, the aerospace application requires a lot of certification. And the listed alloys here, you can find that various forms we have used. And the first, I can say, the aero engine to aeroframe. Even our aero engine also we have made the alloy, and for airframe also. So what I can say, technology for manufacturing of these high-end products are available with us. Only thing is that its quantum and volume has to pick up in these areas. Also, titanium has a very has drawn a good attention for its cast product, because like steel casting, titanium casting is very, very different, because titanium casting has to be done under vacuum. You cannot do under the open atmosphere because it's highly reactive. So the type of equipment used for titanium casting is very unique, and we are doing the near net set casting, and these castings have find a special application in our strategics or the strategic and defense programs. And one sector, I'll tell you, the aero sector, this I have just listed for, so that what are the different applications titanium alloy is having. You can see that cockpit window frame, then wing box, also the hydraulic pipe, then landing gear, track beam, all these have a different combination of alloys, and its properties are so unique and very high strength and toughness, and with the lightweight, it makes very unique for these products. Will find application in the aerospace sector. This is basically the combination of so far there is a lot of like changes in the application of different grades, but you will find that in aero engine still we have titanium 36%, and airframe aluminum is the dominant player, but then titanium plays only 7%, but very unique in the application. So basically the aero engine has a unique requirement for titanium alloys as far as the aerospace is concerned, and which is shown here. And every time there's a lot of developments are there, where titanium is now using in the high temperature zone also. And these are the various grades mentioned here. And you can find that even the gas turbine components, compressor stator, even that is application in the different engine couplings. So everywhere the people try to find out that application of titanium so that it can give the highest strength, high temperature strength, as well as the lightweight. So those combinations are met, then this alloy finds the application in the aero engine and other components also. Fasteners is the one area. See, titanium fasteners has a tremendous application in the aerospace space and even the missile sector, because since it is a lightweight and also its corrosion resistance is corrosion free, people use titanium fasteners very frequently, even though it is slightly costly compared to the steel fasteners. You can see the titanium alloys for the space sector. Space has got a very unique application of titanium, and it's a very unique product. Like you can see that we are using the titanium 6L4V rings plates and used for the tank material, where you store the fuel, some of the gas, also storing of the gas. So the lightweight makes it very unique for that application in the space program, and it is a good weight saving if you see the space our rocket materials are concerned. So this I have mentioned that which location of a, like let's say for PSLV, the Titan 6L4V gas bottles are used, and it is going in the form of rings, plates, billets, rods and blocks for fabrication of these tanks. And also it goes in the PS4 tanks. So you can see that very critical areas titanium has a application, and which is already earmarked here in the block highlighted here for space application. And 6-ton titanium is used for PSLV as the input material for the space application. Similar is the case for GSLV also. For GSLV also, if you see the gas bottle is meant for titanium 5L 2.5 10 ELI grades. Then we have titanium 6L 4V gas bottles. So these are the different areas. Then Titan 21. So many varieties of grades are being used for this GSLV Mark II. This is the typical domes which is being welded for making the tank gas bottle for the satellite application, and also the domes welded for the rings for the satellite applications. So this is the use for our development of satellites in our space program. Various method of making the gas bottles here, components. And just I have highlighted a property here. You can see that the UTS is almost 895 MPa and YS is coming to 825. So it's very high strength we are getting. And in addition to that, you can find that fracture toughness. That's another very, very important part for a designer to make a component when our satellite launch vehicle is designed. And that is where you can see this 80 MPa root meter is a very important properties which we give it to our space applications. And these products are very different in the manufacturing. So we have a manufacturing technology where we use various simulation and modeling techniques. Just to have a glimpse of that, I am not getting the detail here, but just to have a glimpse of that, we try to design our process in such a way that these fabrications are taken care, because the material properties, uniformities are very important. These materials has a very it should be foolproof. It should not fail at any stage of their application. And one thing I just wanted to show, even it has gone in the Chandrayaan-1 Mangalyaan also, and you'll see the presence of titanium alloys in there also when it is landing on the moon. And there also we have this titanium 6L4V in the different form of seats and bars. So not only in the rocket, it is also going in our certain probes and satellites, which is being put in our space and different places. Naval applications are very, very different, because naval applications, because of its high corrosion resistance, titanium has taken as a wonder metal in case of naval application, because it is called almost the immune to the seawater corrosion, and that makes it very, very useful when going, especially for a submarine which is going inside the sea. And you find that titanium castings to titanium piping, titanium bodies. So varieties of domain titanium finds the application, including the welding electrodes, filler wire. So everywhere you'll find titanium has application, and it makes our our submarine or even our ship very immune to that, and makes its life gives a very high performance in our actual application. The seawater filter, in fact, there's a lot of good application. What I said about the castings, whatever body you see here, all are made of titanium casting, and these castings are very unique. In fact, other than this is the first time we have developed here in India the titanium casting. Mainly it is being imported, and this titanium casting has gone in our strategic applications in our submarine. Similar way in the naval application, that already submarine, even the ship also, titanium, if you use the titanium alloys, you can find that its life is very, very, very good. This is for the MiG aircraft. I have just shown that 4 or 5 different grades, that whatever the grades we have got from the foreign origin, we have developed and we have supplied for that. This area is very unique for biomedical implants, which has not been exploited as such, and totally we are depending on the import. This is a very unique product, and all our different implants of 135 types of varieties, types of implants, more than 1,000 varieties we have supplied. And this you can see that different color, that also we provide by the different type of heat treatment, and this has a very unique life in the human bodies. The market scenario for titanium is very good. In fact, if you see in the global titanium metal market is valued of 4,350 US dollar, million US dollar, and it is going to reach in next 5 years up to 6,000, more than 6,000 million US dollar. And the main drivers for the demand is coming from the aerospace, automobiles, electric vehicles, bioimplants, and basically the healthcare sector, electronics, and construction. So these are the different areas that is going to have the more and more demands for this alloys. And the current production of titanium sponge, if you see, China is 85,000 ton. This we have taken the data for 2019, and it has gone to 1 lakh, means 1 lakh 10,000 tons. And this has been, and now that India, we have only 250 tons, Japan 49,000, Russia 44,000. So these are the different combinations where we titanium alloys is being sponge is being produced by the different countries. And we in India, we have a plant set up with the KMML has a 500 metric ton per annum sponge capacity. But the domestic titanium sponge production is very low, and also because of its low volume, cost is becoming very high, and it is very difficult to become competitive in the domestic market as well as the international market using the sponge produced by our Indian company. So there we need a lot of change in our either technology, the production volume, and the future growth. As I told very clearly, in fact, energy sector also is getting a lot of requirement for titanium, because people have seen that use that whatever you fit and forget type of concept is coming, because since its corrosion is very resistance very high, you can utilize the different pipelines, impellers, seals, valves, and tanks, and which can give you the tremendous life, especially if the plant is located near the sea coast. And same is the case for desalination, where as because of proximity to the seawater, the resistance, the corrosion is very high. So there also titanium has a good application. Lithium ion batteries also is going to pick up this. Automobiles, because of this going for the lightweight, then heat exchangers, and also the construction of different type of monuments and all, people now use this. So basically that's popularity of titanium is increasing, but the cost is the one factor today. But as the volume is consumption is going to increase and people can afford that, it is like a fit and forget type of approach, its application is going to increase further. So what we have to see that in total that we have to go for a titanium sponge and titanium metal and manufacturing, which has remained a challenge for our country, since we are depending all, even though we have a lot of reserves, but we are all depending on the import. And also we is high production cost, we are not able to use in the niche sectors. So we are only using for the important sector. So the general applications we are not able to do. We have to depend on the import, or we are substituting with the other cheaper material. Powder metallurgy, one area that lot of now the powder metallurgy has, additive manufacturing has taken a big, big leap in the in application manufacturing, and there's a need for titanium alloys powders to be fit under that. And today, wherever a small amount of manufacturing is there in the country, we are depending on the import, and it's very costly. So what is it? Is basically the inadequate domestic supply of titanium sponge and other critical raw materials, the bottleneck for strategic sectors and other critical materials, raw materials. As I rightly this again this August audience that rare earths are the very important part, and already you have seen that a lot of alloying elements which has been already we are adding here is very unique, and we are not producing. We are still depending on the import. So this has to be developed in the country. So this is what I wanted to submit here, that this is a very important product, and we have to work for this to make it a good application for our nation. Thank you. Thank you very much for giving this.
Check. Okay, thank you so much, sir. And there we are ending the intermetallic session. Can we just play the same thank you gesture on the screen? For none other than the wonderful speaker we had today, Dr. Sanjay Kumar Jha. Please put your hands together, ladies and gentlemen. And right now the moment to felicitate him from none other than our own CMD. Can we have the same slide? Thank you, sir, once again for giving your valuable time and presence. Moving ahead towards the next session where we would be having overview, and the plenary session would be focusing on rare earth materials recovery from secondary sources. It would be taken by an eminent speaker and scientist, Dr. U.K. Mudali, former CE and Chairman HWB. Can we have the welcome slide? Let me take you through his profile. Dr. U. Kamachi Mudali, Vice Chancellor of VIT Bhopal University and Honorary Professor of Practice at IIT Madras, is formerly Distinguished Scientist of Department of Atomic Energy DAE and Chief Executive and Chairman of Heavy Water Board, a flagship industrial unit of DAE during 2017 to 2020. And let me tell you that as an accomplished team leader, Dr. Mudali has made pioneering contributions for 36 years during his service in DAE towards the production of heavy water and specialty materials, advanced materials, coating technology development, engineering, corrosion science and technology, materials process equipment development for reprocessing applications, failure analysis, consultancy and society contributions. Dr. Mudali has 465 journal publications, 5 patents and 9,400 citations with a H index of 43 and I-10 index of 245, and is recognized in world's top 2% scientists from India in the field of materials. I hope this goes for a huge round of applause, ladies and gentlemen. Dr. Mudali is decorated with several distinguished recognitions, which includes Distinguished Alumnus Award from both IIT Bombay, where he did MTech Corrosion Science and Engineering in 1984, and PSG College of Technology Coimbatore, where he did MSc Material Science. In 1982, G.D. Billa Gold Medal and Metallurgist of the Year Award, and there are many more accolades he has already bagged. And he has held the following leadership positions as Chairman Advisory Committee of DAE ICT Center, ICT Mumbai, Governing Council Member, Atomic Energy Education Society, Mumbai and Indian National Academy of Engineering, Chairman Committee on Strengthening Recycling of E-Waste, Niti Aayog, New Delhi Chairman, Corrosion Protection and Finishes Selection Committee, Expert Advisory Committee on ONGC Energy Center, New Delhi, and many more. This gives us sheer pleasure to welcome the first speaker of our session number 5 on overview, and this topic is already announced. Can we welcome him with a flower bouquet as a warm gesture of love from our end? Over to you, Dr. U.K. Mudali, sir.
Thank you, sir. Am I audible and my slides are visible?
Yes, sir. Your slide is visible and you are audible, sir.
Very good morning. Thank you very much for the kind introduction. I'm very pleased to give this overview talk in the plenary session on the rare earth element recovery from secondary sources, thanks to Mr. D. Singh, the IREL and the IRAI for giving me an opportunity to speak in this plenary session. And my hearty congratulations to all the colleagues of the IREL and IRAI, particularly the Indian Rare Earths Limited for the Platinum Jubilee celebrations today. And I could see the meticulous planning of the event and the wonderful inaugural session that we had yesterday. It gives me an opportunity to be here as a former colleague of the Department of Atomic Energy, who was also having very good connection with IREL in the past. I think I don't have to tell this audience about the importance of rare earth elements. It will be like selling coal in Newcastle upon Tyne. You all know very well that rare earth elements are the seeds of technology and green elements who have fantastic applications in catalysts, ceramics, glass and polishing, defense, magnets, special metal alloy production, and the phosphors. There is going to be a growing and increasing trend of using rare earth elements for various applications in the next 50 years and beyond. I have taken the topic of the rare earth elements from the secondary sources because I think all of you are very familiar. You are all working on the production of rare earth elements from the primary sources. But the secondary sources also we have to give a lot of importance today, as a tremendous amount of the rare earth elements are present there, which are just going to landfill, and also after end of life, we don't care about them, which is very important. What are those secondary sources? Secondary sources are those containing metals and alloys which no longer serve any useful purpose that was offered by them initially. That is where that they are becoming secondary sources. The secondary metal production offers energy conservation because it is less energy involved for the production compared to the primary metal production. Landscape and natural resources preservation, because if you don't use them, those secondary sources will go to landscape and they become land, they occupy the landscapes, and the natural resources are also getting exhausted by excessive use of the natural resources. And toxic and non-toxic waste streams reduction, because once you do the secondary metal production, you don't allow any of the toxic element just go into the landfill as a waste. And recovery through the recycling, the secondary sources benefits the society and environment because it establishes a circular economy, which I will show you in the last end of this presentation, how that is benefiting the circular economy by value addition and enhancing the sustainability of the metals. And we all know that the production of metals from the secondary sources are always less energy intensive, and mining cost is reduced, and technologically also less complex compared to the primary metal production from the parent ore materials. And the solid waste, metal waste, are the end of life products with significant metal inputs, even in smaller quantity per atom. If you are going to take it, the valuable metal from that, it is going to be a waste, it is going to be a toxic income, and it is going to be a landfill addition. And that's why that we should use them as a great source for various metal production. I am going to focus here particularly the secondary source, the electrical and electronic solid waste, which are popularly known as e-waste, or the WE3. That is the WE3 is nothing, the equipments, the waste of the electrical and electronic equipments, waste from the electrical and electronic equipments, which are an excellent secondary source of valuable metals, including the critical rare earth elements. What is e-waste or the WE3? They are basically electrical and electronic equipment which are whole or in part discarded as solid waste by either the consumer or the bulk consumer who is having them without sales, after service, or at end of life, and also the rejects from the manufacturing, refurbishment, and repair processes. It looks very complicated, but it encompasses the entire definition of what is a solid e-waste or waste from electrical and electronic equipment. It's a very highly complex and non-homogeneous waste stream containing over 1,000 substances, because These are very from micro component to mega components that are used from household to strategic applications. The presence of precious metals and scarce metals and base metals, all of them are very, very important when you look at the e-waste or the WE3. And also with respect to environmental considerations, the toxic constituents, particularly the lead, the arsenic, the selenium, cadmium, mercury, etc., they make the e-waste hazardous to the human health and environment if we are not going to treat them and properly take them out and store them. Most of the toxic landfills are coming due to the e-waste. And if you look at the material composition of e-waste or the WE3, it's one of the prediction in the early years, 10 years back, that is metal is about 60%, then plastic comes, then the metal plastic mixtures, then the screens like CRT screens, and the PCPs, and etc. Now, if you look at why it is called electrical and electronic waste, the electric waste includes basically the refrigerators, which are about 20%, and then the washing machine, dryer, air conditioner, vacuum cleaner, coffee machine, toaster, iron box. They are coming up to about 30%. They are all electrical waste, which contain very useful metals, including the critical rare earth elements. Then you go to the electronic item, you have the televisions, monitors, computers, telephones, fax machines, printers, then DVD, VCR players, many things. So if you look at, it's a very fastest growing waste stream in the world, and it is growing, in fact, 3 times faster than the municipal waste. All of us know that how much is the municipal waste is growing, solid waste is growing day by day, but the e-waste is growing 3 times greater than that as per the statistics. For example, if you take in the year 2019, the total e-waste in the world, global e-waste, was estimated as 53.6 million tons. It is worth about 57 billion US dollars. Can you imagine? It's the biggest money that you can see in the e-waste, that is 53.6 million tons, which is an average of 7.3 kg per capita in the world. Every person consumes and then throws as a e-waste 7.3 kg per year. And mainly which is comprising of small equipments, large equipments, and temperature exchange equipments, which I am showing here in pictorial format. And all of them are growing in, you can see the plus signs that all of them are growing year by year. So statistically what I told is that 53.6 million ton per annum, which is costing about 57 billion. And this is an increase of 21% if you look at in the last 5 years. And it is also estimated by 2030, it will increase by 38%. That is roughly about 74 million tons. And then the estimated value of the recoverable material after processing is roughly going to be 25 million tons per annum. That is out of this 53.6 million tons. If you do the secondary processing, you can recover 25 million tons of this from this valuable material. That's a very important number that we will discuss this little later. Now, only out of this 53.6, 9.3 million ton, that is about 17.4% of this 53.6 only has been collected and recycled. That means, meaning high value recoverable materials of only about 4 million tons with the cost of 10 billion has been recovered. So out of this 17.4 billion that is processed from the 53.6, you get only 4 million ton, that is valuable material, recoverable material. That costs 10 billion, but still 47 billion we are throwing into the landfills. And rest is dumped or burned rather than being collected for treatment and reuse. And if you look at the global e-waste, the data that I am showing in the pictorial way, which is about in the year 2016, this shows that China is the global leader in that, followed by US and Japan, then India was 4th. But today, as of 2019, if you look at the India is now the number 3, the largest producer, and China is still continuing as the world's largest producer. Okay, then Asia is generating together, as you know, India, China, and other countries in Asia. It is about 24.9 metric ton. That is more than nearly 50% of this whatever 53.6, nearly 50% is from Asia. Okay, the per capita is also given here. How much is being wasted? Of course, India is about 1.5 per person, whereas compared to Germany, which is 22.8, and Norway is the highest, 28.5 per capita that is producing the e-waste. Now, if you look at the scenario in India, India has generated in the year 2019 about 3.2 million metric ton. Okay, the biggest contributor is Maharashtra. You can see Mumbai, though it is 2016 data, Mumbai is still continuing the trend, and then followed by Delhi, Bangalore, then Chennai and Kolkata. And it is estimated that this 2019 figure of 3.2 million metric ton will be roughly 5.2 million ton per annum in 2020, last year, and then 9 to 15, anywhere number between 9 to 15, depending on the e-waste that is being dumped, will be in the year 2030. So this steep rise from 5.2, maybe 3.2 to 5.2, then to 9 to 15 in the the 10 year or so, you can see that is mainly because of the increase of the waste from mobile and computer. The mobile is increasing by 1,800% per year, and then the computers are increasing by 500%, particularly in the year 2020, based on 2007 data. And if you look at the item composition of the e-waste, computer contributes 68%, then household scrap is about 5%, telecommunication 12%, electrical equipment is 8%, medical equipment is 7%. The medical equipment is because of the huge machinery that is used in the scanners like MRI scanners and so on. Then if you also look at who is producing such waste, the government, public and private sectors contribute 70%. The manufacturers, they contribute about 15%. And then Indian individual households contribute about 15%. India, as I told, is the third biggest producer of the e-waste. And what is very important is only 1.5% of the e-waste that is generated. That is in 2019, we made about 3.2 million tons. That is about 32 lakh, out of which 1.5, only we have, more than 95% of e-waste managed by informal sector. Out of the, the only 1.5 is recycled, and out of this 1.5, 95% is managed by informal sector. They are not the regular people who are having a well set up facility for this purpose. And we have very acute shortage of recycling facility in the country. Today, if you see, there are 312 registered recyclers for such a country which is producing 3.2 million metric ton in the last year. And there are dismantlers in 17 states having the capacity of 7 lakh 82. Okay, we produce about 32 lakh, but the capacity is only 7 lakh 82. And this is a very small number. It is about even about 20% capacity only we have for recycling this secondary waste. And authorized recyclers using this capacity of 7.82 lakh ton per year, they are only recycling 4 lakh 38. In 2016, they have done only 4 lakh 38. So out of 30 lakh tons, only 4 lakh has been recycled and taken out the valuable materials. And we have very minimum number of well-established e-cycle industries, like e-Parisara, Earth e-waste management, Green Care, in e-front line. There are many people who are there who are established, but they are very small number compared to a country like India. The Department of Electronics and Information Technology, is promoting R&D in developing recycled technology in the country, and we should appreciate that Day-2 supports several national institutions like CMET, CSR labs, etc., by providing a lot of funding for the R&D projects to establish the process for e-waste management. And as I told you, that only 1.5% of the total e-waste of 30 lakh is processed, and out of this 1.5%, 95% is done by informal sector people. And if you go to Moradabad in UP state, which is the world's biggest e-waste processing capital, where absolutely things are done like this in an open yards, you can see mounds and mounds of PCPs and the computer waste, and then all kind of electrical and electronic equipments, creating so much of environmental hazard and toxic environment, and also the polluting the river Ganga. on which base they have established this informal sector facility. And I would like to tell you that if you look at the periodic table, about 69 elements from the periodic table can be found in this e-waste, including the precious metals, the critical raw materials, and also the base metals like aluminum, copper, iron, and zinc, and so on. Okay, so this is almost like out of 71 metals that are available in the nature, 69 elements are available in the e-waste. That's what is the most important point. And if somebody want to know more accurate data, is that how much gram of this metal present per unit of a selected electronic device. I have got a table here where you can see the TVs, the monitors, the cell phones, the computers, and the hard drives. You can see here aluminum, copper, iron, lead, cobalt, tin, gold, silver, palladium, and other rare earth elements. You can see that gram per unit of such elements, valuable elements that are available in these electronic devices. And if you look at the major elements, particularly in the electrical equipments like a refrigerator, washing machine, and air conditioner, they contain the major elements like iron, aluminum, copper, and PCP in little large quantities. And this gives an idea about category wise, the household appliances, IT and telecommunication equipment, electrical and electronic tools, consumer equipment, toys, laser and sports equipment. You can see that iron, aluminum, copper, and other elements, including tin, the rare earth elements, everything is present. And if we can find that including the major elements like iron, aluminum, copper, that can be recovered with a less energy intensive process compared to the primary metal production. And the most important point is that the 11% of the world's gold production, roughly about 320 ton of gold, and more than 7.5 ton of silver is annually produced from this e-waste by worldwide. And about 25% of the annual copper production is also present in these devices that can be recovered. Copper is available roughly about 25%. That's what you can see here, particularly in portable audio, you can see 21%, and in the PC board 20%, and the mobile phone 13%, and TV board 10%. So this is how the copper is distributed. And if you look at the value share instead of the weight percentage, if you look at copper is 50% of the TV board cost, and portable audio it is 82%, DVD player it is 42%. All these obsolete items will give you roughly 25% of the annual copper production in these devices. And 22% of the mercury produced in the world is also used in these kind of electrical and electronic equipments. Not only the valuable metals and alloys, but you also have the toxins which affect the body parts. And you can name it any of these toxins like lead, beryllium, mercury, cadmium, and PVC, bromine, anything you can find in such components like CRT or the computer batteries, plastic housing, which affect so many parts of our body. They are all present in this, and it has been estimated 50 tons per year of mercury and 71 kilotons per year of PFR plastics can be made available from these e-waste every year. And now let us focus on the REE, which is our main primary topic. And if you look at the REE recovery potential from the e-waste, what I have given is particularly for the Indian target here, and the recycling potential of REE up to 2023 and also in the long term. The long term, we are going to have tremendous REE that is available, because these days the equipment that we use, because depending on their life, they are not yet available as a base to that level that you can get it. For example, wind turbines, they use a huge quantity, okay, about 400 kilogram of per megawatt, 400 kilogram of megawatt of power. They use the magnets, and they are still under service after 20 years. That means in the long term, you get very high input of such magnet, which should not go to landfill, which has to be recovered and used. At the same time, there is also something like mixed metal that is available in the lead metal hydride, nickel metal hydride battery, that is in a low level, in a moderate level in the future. And so today there are, depending on the usage of this equipment, you have, for example, electric bike and electric hybrid vehicle. We don't have anything today. they have an average life. Even if it is introduced in between 2020 and 2030, they will be available only after 10 years. That means 2040 and 2050, they will be available for the secondary processing. As I told you, in the medical equipment, the MRI scanner, which is up to 0.35 Tesla, if you have an average life of 10 years, we can get 1000 kg per unit. I think in 2018, estimated to be 1700 units. After 10 years service, you will be getting tremendous amount of this magnet that is available from that. So this is another pictorial way of representing the RE potential from the CFL, that is the fluorescent lamp. You get 0.9 gram RE from each lamp. The average life is 6 years. And by 2022 onwards, you will get a tremendous increase. But with the time, it will get phased out, as we are not going to use that much of CFL. We are going to LED and so on. And similarly, if you look at the RE potential from mobile phone, it keeps steadily increasing as per the usage. You also get more and more the neodymium and the praseodymium from these mobile phones. Then you have the RE potential from the absolute HDD of the computers, which you can see that the potential is increasing very high, and RE potential from nickel metal hydride batteries, that is also showing an increasing trend after time. And particularly for the turbine, the wind turbine magnet, as I already mentioned, 400 kg per megawatt power, you can see a very steep increase that will happen. And depending on the setting up of wind turbines, this number also will keep changing as time is running out. Today, by 2041, you get maximum input from the wind turbines. And from electric vehicle, which is about to start now, 2020, we are just starting. So after some time, you will find that the increase is too much. The magnetic material from the electric vehicle is going to be increasing so much, particularly the NdFeB magnet that is being used in small motors and sensors. So overall, if you look at with the time wise, 2018, 2023 and 2026, you will find that there is a fluctuating number depending on the life of the particular equipment, the electrical equipment, and the usage of the critical metals in that. You will find, but it is going to be tremendous in the future. In 2026, by 2026, the wind turbine is the one that is going to contribute roughly about 31.75. It will give neodymium and also the praseodymium, the dysprosium, and the gadolinium and terbium, and other sources are about 68.25% in 2026. I don't want to explain to this august audience about the rare earth. They are basically the group of 70 elements apart from the scandium and yttrium, and they belong to two groups, the light rare earth and the heavy rare earth. And all of you know very well that the processing of rare earth involves a dedicated flow sheet that has been already established by the Indian Rare Earth Limited, where you get a chloride. Rare earth chloride is our production, and India is the second largest producer of RE chloride today, and we have about 3 million tons of resources. Particularly, we have the light rare earth elements, and we have mastered the extraction of rare earth through fused salt electrolysis as well as calciothermic reduction processes. And we ultimately produce either a metal or oxide of the particular rare earth element or the critical element that is required for the strategic applications. We have many technological challenges in recovery and reuse of rare earth elements, because it is a big challenge for both manufacturer and environmentalists. And why it is so? Because only about 1 to 2% of rare earth element is present in the end of life products that are now getting recycled globally. And the challenges are like this. Number one is technological difficulties. Separation and purification of individual RE is challenging due to the chemical similarities, because most of them are in the same lanthanide series. Their chemical similarities are together. So it is very difficult to separate and purify them. They are present in very small concentrations. So there is a low yield with very varying quality. Then there are a lot of contaminants and mixture of many hazardous substances. So it leads to environmental issues. And often it is present as a very difficult to decompose compound. That means in a V-waste, it is not used as a simple as, for example, NdFeB. You have to decompose that and to separate ND, and you have to separate NdFeB. Then only you can take NB separate. So the end is separate, and that is not going to be that easy. And the economics of operation has to be seen, the energy intensiveness would be seen, and the chemical form of such recovered RE also different that in the product. So how that can be further process has to be looked into, and high pure RE is in specific chemical form required for new product. We cannot use the whatever product that comes out of this process, secondary process cannot be directly used for the primary application, where still you need more purity and so on. So these are all the challenges and technological difficulties when you are doing secondary processing, but that does not stop us in doing recovering this RE from the e-waste. If you look at the global status, the recycling is done only less than 1%, only from 3 waste streams, that is magnets, nickel metal hydride batteries, and fluorescent lamps. These are the 3 categories in which less than 1% of RE only is getting commercially recycled. And the countries which have an established technology are Japan, USA, UK, and Germany. Japan is particularly leading the RE recycling, and their technology is most matured. And they have also they have been setting up plans for using the established technology. For example, the Honda and the Hitachi people in Japan are the front runners in rare earth recycling, and their processes are mostly patented and classified. And apart from them, there is extensive R&D across the world, including in India, and many published literature are available in this field. But further towards the RE recovery from India, there is a lot of research work going on by several research organizations, including the CSIR labs like NML, IMMT, SECRI, the RRL Trivandrum, and so on, and the educational institutions like IITs and so on, the industrial sectors like the IREL, the research laboratories like the BRC. Then industrial scale recovery from e-waste is not yet established. This is one of the most important points that I want to highlight. Though some technologies are available, patents have been made, some technology transfer also have been effective to some small players, major industrial scale recovery of RE from e-waste is yet to happen. And that is definitely very, very important for a country like ours. For this purpose, we need technologies. E-waste recycling, as I told, is a very complex technology. It involves so many metals put together and with similar chemical properties, and that is not that easy, which are in small quantities. There are many, broadly there are 2 ways of recycling. One is conventional recycling, other one is advanced recycling. The conventional recycling involves only the direct one, where from the landfill and incineration, you take either it goes to landfill where it is getting recycled by the informal sector, or it is getting incinerated and the rest is taken for the application, or the physico-mechanical separation where comminution, size separation, magnetic separation, air classification, density separation, and electrostatic separation, all that is done to take out the recycled useful material. But if we come to the advanced recycling, we heavily employ the chemical and metallurgical methods like pyrolysis, gasification, combustion, hydrolytic degradation, the supercritical depolymerization, or like pyrometallurgy, hydrometallurgy, biometallurgy, electrometallurgy, and vacuum metallurgy for efficiently recovering these very valuable metals, particularly the RE metals from the e-waste process, e-waste materials. Let us take first the case of the RE is from magnets. As I told, there are 3 groups. The first group is the magnets. Industrial recycling of the magnets is pursued in several countries, particularly the RE recovery of neodymium from NDFB magnets, or samarium from samarium cobalt magnets. Hitachi and Mitsubishi, they have developed dismantling machine for extraction of magnets from the HTDs, then the air conditioners and washing machines. And the researchers at the University of Birmingham, UK, they have developed hydrogen decryptation for extraction of magnet. And some of the companies which have mastered is including Hitachi, then Santoku, Japan, then Mount Pleasant, Mexican company, and then Apple, USA also is doing that. And basically, this is a Hitachi's recycling process. RE recovery from magnet involves first the dry extraction using molten magnesium, and from there the distillation is done for taking out the magnesium and the residue or REs. Then also the production of waste from end-of-life magnets. They have got the Santoku has got a recycling process that is industrially utilized today. In India, NML has developed a hydrometallurgical process to recover the REEs from the magnets. The process has been very well established in the laboratory process, and they get a NDFE F3 powder that can be re-synthesized for particular application in the industrial scale, and as well as the recovery of samarium from samarium cobalt magnet. Only the difficulty is that we have never gone to the pilot scale and industrial scale, and it's not being industrially practiced in the country. E-Parisara is one of the leading company in the country where they have been recovering neodymium magnet from HDD of PCs and the laptops, and they have an established industrial setup at Bangalore, and they are using a hydrometallurgical extraction process by leaching and separation of nickel followed by iron, and this is still in the scaling up process for higher quantities. The RE recovery from lamp phosphor, because now huge lamp phosphor is available from the discarded CFLs, and many countries like Americas, Asia, Australia, Africa and Europe, they have all, particularly the renowned lamp manufacturers like the Solvay, Osram, Endeavor, Veolia, they all have established different processes, and what you see here is one of the processes by the Solvay Rhodia process, and the other one here by Osram process. They are all established process, and where they significantly recover this phosphor from the lamps. And the recovery of yttrium and europium from fluorescent tube and CFL has been established in our country by single step process by NML, and where they have successfully recovered and then shown the efficiency of the process. They also established a two-stage process for recovering the rare earths, the yttrium and europium, the lanthanum, cerium and terbium from the spent fluorescent tubes and CFLs. The novelty is that very high pure product can be made by them, and they also made a recovery of the process for rare earth metal from scrap fluorescent tubes. And according to the analysis of this phosphor that is recovered by them through CMET, they say that in a year, per year, by processing this lamp waste by industrial processes, industrial scale, assuming that 100% collection of lamps have been done, one can get yttrium 304 tons, europium 15.2 tons, terbium 10.1 tons, and lanthanum 23 tons. That is a quantity that we can get from the lamp process, the lamp. Including the IIT Roorkee also has made a RE recovery from the CFL, the lamp process, discarded lamp, that this is also a process where they get yttrium and europium oxide of 98% purity. E-Parisara has processed low-cost lamp crushing setup to recycle all the types of lighting to recover glass and phosphor. And in fact, the lamp glass recycling is of negative economic value, because you create more waste by, after taking the phosphor, the lamp becomes further waste unless you utilize them for very useful products. They make a lot of glass cullets and very useful products that are available for the market. They send it to the Firozabad glass cluster, and they avoid landfill of the glass waste. So that is how it is going to be a successful process that is established by them. This is the process established by E-Parisara, which is a very industrially adapted process. They also have an indium tin oxide recovery plant from the LCD screens, which is being also used by them in the industrial scale. And if all the end-of-life LCDs are collected in India, according to them, they can get 10 ton per annum of indium, which the end-of-life SATA as per the Central Pollution Control Board guidelines. The recovery of the RE from the nickel metal hydride battery, the third class of material, there are several companies. Again, they use the pyrometallurgical route followed by hydrometallurgy for the processing to either the rare earth oxide or rare earth metals. And particularly, most of these electrical vehicle manufacturers recycle this nickel metal hydride batteries. The Umicore process is a very popular one. And the Honda Motor and Toyota people also have their own processes for the nickel metal hydride batteries recycling. And this is because of the upcoming electric vehicle manufacturing, and the huge magnet that is roughly about 400 kg per unit that is being used, there are a lot of interest shown internationally for establishing this recycling process. Particularly after 2040, there is going to be huge inventory of such magnetic waste, battery waste in our country, and that is going to be very, very important. The IMMT Bhubaneswar has got also a lot of lab scale studies, recovery of the neodymium and the praseodymium from the scrap of NDFEB magnets using 2 different routes. They also have recycling of samarium cobalt magnet and the processing of spent nickel metal hydride batteries. SECRI has also got established processes for cerium recovery and also for lanthanum nickel and neodymium nickel alloy through molten salt electrolysis. Then electrosynthesis of samarium boron and neodymium boron using the molten salt technique, and preparation of NDFP alloy using molten salt electrolytic reactor. They have pioneered this molten salt route very efficiently for a quite long time. And of course, with respect to DAE units, BRC and IGCAR, they have established also many processes, including processing of PCB boards, purification of ND oxide, dysodium extraction, and the liquid membrane based extraction of europium, then the gadolinium separation by ion exchange process, and so on. Now, if you look at the e-waste management, particularly in our country, it all started in 2002 when there was an e-waste was considered as an important environmental issue, and the guidelines for electronic waste management came with 2 formal recyclers after just about 5-6 years, 2008. By 2012, the electronic waste law came into effect with the identification of 100 dismantlers and recyclers in the country. And 2016, it has grown into 178 dismantlers and recyclers, and many items in the e-waste category has been put into the revised e-waste rule. And 2018 included much more items, much more amendments have been done, falling in line with international rules. And we have today, as I told in the beginning, 312 recyclers and dismantlers with a capacity of 782,080 tons per annum processing capability. And 17 states have at least 1 recycler, and as per the data in 2019. So we need, this is the time after this 2018, we have to shift from the the reduce, reuse, recycle principle to reduce, reuse, recycle, then recover, redesign, and remanufacture. This 6R principle will lead to us to have a circular economy in the country, and that will be possible only if we scientifically handle, process, and dispose e-waste through authorized centers and facility. Towards that, Niti Aayog set up a high power committee strengthening the recycling of e-waste under the direction of Dr. V.K. Saraswat, the honorary member of the committee, Niti Aayog, and I was the chairman of that strengthening the recycling of the e-waste. And we have proposed setting up of the Eco Park for processing of e-waste with the PPP model, public-private partnership model, according to which the Meiti and nationally set up National E-Waste Management Association or Authority will regulate and control and monitor the storage and segregation, the dismantling, the recycling, as well as the training and testing and technology development, everything, and including bringing all the e-waste from the strategic sector, using their technology, recycling, and then bringing all the useful material for product manufacturing. That's what I told 6R. You recover after the material is recycled, you recover, redesign, remanufacture, and put it into use so that we can have sustainability of the metals, as well as we will have a circular economy in the country. What is the benefit of that circular economy? If you look at the circular economy, the number 1 is that you can see, for example, I'm telling you that 53.6 million tons, that is about 7.3 kg per capita is the 2019, the e-waste produced 53.6. This contains about 25 million tons of the recoverable material, which costs about roughly about 40 billion US dollars. That's what I told you in the beginning. That's about 57 billion US dollars. So if you 100% recover from this e-waste of 53.6, you will get 25 million ton useful metals and alloys valuing 57 billion. And this, if you want to make 39 million ton equipment that was originally produced, electrical and electronic equipment, put it into use, which has become a waste, 53.6. Now, if you want to remake this 39 million ton for putting it into use again, so according to this calculation, 25 million ton needs additional only 14 million ton of virgin new material. So the load on the primary processing goes down. So instead of again producing 39 million ton of the primary metal to produce this equipment for use, we can, if we can recover this 25 million ton from the e-waste, we need only 14 million ton to make this 39 million ton, and that becomes 100% recycling as well as a circular economy that is getting established with 100% urban mining of the e-waste. If this can be done, the metals are getting sustained, they are going for reuse, and they are redesigned, they are remanufactured. So instead of the 3R principle, that is the recovery, reuse and recycle, we go from recovery, reuse, recycle to redesign and remanufacture. That will be only using 14 million ton. So this is going to be a circular economy that will be establishing benefit the many countries in the world. And this is to say that the quantity of such raw material, you can get the bulk material other than the critical RE material. If you look at the value of the material that you can get, it is 16,283 kilotons. Copper is about 2,164. Aluminum is 2,472. You can see that tremendous quantity of this material can be reused, redesigned and refabricated worth of this money, and that can be used for this. Particularly if you look at the Indian scenario, the electronic market is one of the largest in the world, and it is growing. In the year 2020, 400 billion has been invested by the government, and the monetary value of the recovered material from e-waste was about only 4 billion in 2015. That we should increase to 20 billion by 2020. Only if that means we have to produce more and more secondary materials from the e-waste processing. And it has been estimated that gold alone, that we can get 1 billion, that is worth of 6,900 crores from urban mining of e-waste. And the concentration of precious metals in e-waste is much larger than it in the ores. Hence, urban mining is much cheaper than extracting metals from the ores. Recovery of strategic materials may reduce countries' import dependency also. That is very important that we have to consider. And apart from that, if you look at the environmental and societal incentives, okay, urban mining saves energy, reduces pollution, reduces greenhouse gas emission, and saves natural resources by extracting fewer raw materials from the earth. That is what I was telling in the circular economy slide. Urban mining can potentially help mitigate climate change and prevent unnecessary dumps and landfills. The recycling of iron, aluminum, copper, and such major elements contributed to a net saving of 15 million tons of CO2 equivalent to emission from the recycling of secondary raw material substituted to the virgin material from the primary material reprocessing. And repurposing of obsolete or discarded EE for reuse after repurposing or repairing provides an opportunity for middle and low income group people to have an access to household appliances. This is very important. And information technology and communication devices will be made available at affordable cost. So this makes the obsolete and discarded EE can also be made reuse after refurbishing. So that makes affordable for middle and low income group. It's a very important concern with respect to societal incentive. Finally, that this is going to be a very high opportunity for a lucrative business model, which will provide excellent job potential and livelihood to millions of the people. According to International Finance Corporation, e-waste recycling sector will create 4.5 lakhs direct jobs by 2025 and another 1.8 lakh jobs in the allied sectors of transportation and manufacturing if one can properly do the recycling of the e-waste. Not only it benefits circular economy, it also provides ample employment opportunities for the people. In a concluding remark, I would like to say that the colossal e-waste is a treasure trove of valuable rare earth elements and critical materials which provide gold mine of opportunities to the global scenario, particularly for a country like ours, India. An efficient e-waste management can successfully contribute to urban mining, offering several incentives, including economic and social benefits. Recovery of RE material is pursued in smaller quantities in world and India, which needs greater attention today, and various chemical and electrochemical methods are employed for the recovery of RE metals from the electric and electronic waste devices. The efficiency and the effectiveness of such technology is very, very important for the useful recovery of various metals. Why we need to do this reuse, reduce and recycle at least to treat this e-waste? Because we always think that we heritage this earth from our ancestors. Actually, we do not inherit the earth from our ancestors. Actually, we borrow it from our children. Unless we keep a clean and environment benign earth today, our children and grandchildren will benefit from that. Otherwise, they will suffer from whatever damages, whatever the landfill that we are going to do it today. I want to finally acknowledge the Niti Aayog, Government of India, for giving an opportunity for the committee to look into e-waste as a potential source of secondary source for the REE, particularly not only the major metals. Particularly, I want to thank Dr. V.K. Saraswat, who was our mentor, who guided us to do this particular topic. I want to also thank late Dr. Baldev Raj, who was the chairman of the particular committee with 8 subcommittees and who motivated us, the members of my subcommittee on strengthening recycling of e-waste, and my former colleague, Mrs. Manisha Patel, and colleagues at Hay Water Board, and my former department, the Atomic Energy. And these papers, the essence of this work is published by us in the Transactions of the Indian National Academy of Engineering in the issue 3 of 2021, in part 1 and part 2, part 1 on the e-waste management, part 2 on the technologies for e-waste. One can go through for more details. Thank you so much, IREL and IRAI, for this grand opportunity. And once again, my hearty congratulations to IREL for its Platinum Jubilee celebrations. And thanks to Mr. D. Singh for the invitation. Thank you very much.
Sure. Thank you so much, sir, for your wonderful contribution in the form of this wonderful talk session. And this is the time to acknowledge. Yes, there is a question. Okay, can we have a mic, please, team? So meanwhile, can we just thank sir virtually?
Yes, please.
Very good morning, sir. Very good presentation, particularly giving the scenario of e-waste, scenario of waste management, and all the kind of the important products recovered. My question is, when we talk about recycling, you have given a very lucid presentation, but if suppose you treat 1,000 tons of waste, how much environmental pollutants generated? How we are going to treat them? Then what type of the, do we have any comparative studies that with this kind of the products, and also you have said the kind of rare earths recovered or product recovered may not be 100% pure. So under those circumstances, whether those products will be usable or not usable, and how we are going to justify in terms of pollutants generated by recycling of all those things.
Thank you so much, Mr. Verma-ji. This is a very good question that you have asked. See, the point is that I have not given the complete details. It was a huge report that we made to Niti Aayog, and part of it is published in the journal also. One can go through leisurely. All that I would like to say is that this study has been done. Okay. For example, if I say today the figure, 2019 figure is that 3.2 million tons, 32 lakh tons of the e-waste as per the estimation has been generated in our country, roughly. And out of these 32 lakhs, only 1.5% that has been processed. And that also, if you look at the capacity of the government authorized recyclers, which are about 372 people, is about only 7.8 lakh. So that means remaining 25 lakh ton is not being processed. It is going to landfill. It is going to the hands of unorganized sector. And what has been produced out of the 7.8 lakh ton is only 4.8 lakh ton that has been processed. And from the 4.8 product, how much has been, categorically taken the primary metals like iron, copper, nickel, and how much is the REE? Whether we are able to separate all these minor elements carefully as an individual element, whether we have seen the process completion with all the elements individually separated, the data is still, there is a lacuna in the data that is available in our country. There is no forum that has been doing it, and I am sure that the part and parcel, the data available with Day-2, the Department of Electronics and Information Technology has got some data on this, that how much valuable material that has been collected out of the Indian detail. But if you look at the global details, there is some valuable data based on that only the circular economy model has been made. If you look at 53.7 ton of million tons of the waste that is generated, they could estimate that 24 million ton, 25 million ton useful metal and alloy can be taken back, which can be only mixed with 14 million ton to produce 39 million ton of equipment that can be put into use. That means instead of creating about 59 ton of this material that is required for making the equipment, you can only need to produce 14. The remaining comes from your the recovered materials. So the global data is available. If you want more details, the Global E-Waste Monitor 2020, a big report is available in the public domain. I'm sorry, I may not be able to give you precisely the data. That is, I'm not able to remember. But you can see our report. You can see our papers that are giving all the information that you need.
I hope your
Thank you,
query
Mr.
is
Verma.
answered. Thank you so much, sir. Can you play the thank you gesture on the screen? We thank you, sir, from bottom of our heart for giving your valuable
Thank you.
time and such a detailed presentation. And moving forward, let us present a virtual memento from our Honorable CMD to Dr. UK Mudali. Thank you once again, sir.
Thank you. Thank you.
Thank you. And moving forward, we would be covering the next session on rare earth magnet manufacturing in India, which will be given by Dr. Gaurav Shukla, Assistant GM Technology Department, MSPL. Can we have this intro slide? So we welcome you to this beautiful forum where we are celebrating the second day of Platinum Jubilee celebration of IREL family. And ladies and gentlemen, let me take you through his profile, his achievements, accolades so far. Dr. Gaurav Shukla have earned his PhD in Semiconductor Optoelectronic Materials and their applications from Indian Institute of Technology, Guwahati in 2010. Subsequently, he has joined the Global R&D Center of Crompton Greaves Limited at Mumbai to work on novel RE phosphor development for lighting and initiate LED manufacturing in India. During 2010-2016, he has worked with various business units of Crompton Greaves Global R&D to lead the development of energy-efficient technologies and products, including permanent magnet-based motors, soft magnetic materials, sodium-ion batteries, solar cell manufacturing, and novel carbon-based dielectrics, etc. In 2016, he has joined Delta Magnets Limited as R&D head to improve the manufacturing process, develop new grades and applications of hard and soft ferrite magnets. Presently, he is working as Deputy General Manager Technology Development with Baldota Group of Karnataka, India, and responsible for new technology-based business development in the area of rare earth magnet resource cycling, advanced carbon, energy storage and renewables. So once again, delighted and cheerful to have you as our next speaker. Can we welcome him with a warm bouquet from our end? Though our CMD sir is not present physically, but virtually everything is sorted from his end. That's a true shine of a good leader. Please put your hands together for our CMD sir also. Thank you. Moving to Dr. Gaurav Sukla for his next set of presentation.
Yeah, good afternoon, everyone. Am I audible? Hello. Am I audible?
You are audible, sir. Please share your presentation.
Okay, okay. Sure, sure.
Yeah, your presentation is visible to us, sir.
Yeah. So, so good afternoon, everyone, again. And I would like to give my best wishes to IRL family for their this 17th Platinum Jubilee Year celebration. And I wish I would have been there. I wanted to join there, but due to certain issues, I could not join. And I would also personally like to thank Sri Anuttam Mishra ji and Sri D Singh ji for giving me this chance to present our thoughts about IDFE manufacturing. So I'm not sure if the slide is visible in full mode or how it is. It is in full screen. Okay.
It's in full size, sir.
Sure. So
sir, please come
yesterday we already have multiple talks about NDFEB magnet manufacturing by Professor Basu, then Professor Gopalan, then Dr. Raja, and they provided a very excellent summary about the work being done in India, about the technologies and everything. So I would not be covering that aspect in general, like the key technology aspect. What I will be covering here, like how commercially viable it will be to manufacture NDFEB magnets in India, and what are the challenges to make that happen. So before I move ahead, I would like to introduce about myself and about the company which I represent. So my name is Gaurav Shukla. I work as a Deputy General Manager of Technology Development for this company called Bhagavata Group. And I think this slide is, so you can see in this slide that this is about the company briefly. So we operate into these 5 segments. So we have iron ore and gold business, mining. Then we operate into shipping and water purification. We operate into wind energy, aviation, industrial gases. We operate into iron ore pellet manufacturing and steel manufacturing we intend to go into. And then we also do a lot of CSR activities and a lot of work on environmental sustainability as well as mental well-being. We also operate one company on mental well-being called Samarpan. So multiple companies are there in the group. So MSPL is one of them. Then we have Ramgarh Minerals, MSPL Diamond, RS Iron and Steel, Gujarat Chemical and all. So we are working on this to initiate magnet manufacturing in India for the last two years. We also discovered one deposit in Rajasthan in 2014, and subsequently we are yet to get the ml for that deposit. And from that point onwards, we initiated our journey into RE value chain. And in 2019, we initiated our program to start manufacturing, to look into viability of manufacturing NDFE magnets in India. So in that way, we have also participated recently in the RFP of IREL, where we have been declared the selected bidder. But due to some differences about the, about the quantity of the material pricing and all, we could not move ahead at this point of time. But we remain interested in to initiate NDFE magnet manufacturing in India, and we would look for the next set of opportunities. So this is about the group and our vision on the magnet manufacturing in India. Yeah. Now coming to NDFE magnet manufacturing. So as I said, like the technical aspects have already been well covered. Know that the technology is available as such, and even the Indian Indian R&D institution, the technocrats in India, they are well capable of providing this technology to the industry as such. So what I'm going to talk about whether the business, what can be done about the business viability, how viable the business is, and what are the issues there. So to determine the business viability, in my opinion, the following need to be understood, like whether the market is there, what are the demand supply gaps, what is the growth forecast, whether the readily executable technology is available, and what is the cost. So obviously the technology is available in the form of like the R&D is happening and all, but for a large scale commercial perspective, the technology has to be readily available, readily implementable. So that sort of technology, whether it is available to the us or not, that has to be seen before going into NDFE magnet manufacturing. Then what are the regulation standards, market trends which can impact their business, availability of raw material, plant and machinery, trained manpower. So we know that all raw material is obviously available from IREL. Plant and machinery, we know that since nobody is manufacturing as of now, magnets in India, so it's not there. And similarly, the trained manpower who have had a training in the actual, in the actual manufacturing environment, that is also missing. So that is one issue there. Then what are the profitability in the NDFE magnet manufacturing? So so we know that it is great that it's a very strategic material and a lot of people are means a lot of countries are interested. It has huge geopolitical impact. So all those things are fine, but from a commercial venture perspective, what is the profitability there, and what is the possibilities of scaling up that particular business? So one can initiate at say 1000 TPA or 500 TPA, 100 TPA level, but at what scale that one can go with this? So that will determine how much risk can be taken in the initial stages. Then there is a threat of new competition, technology, and product obsolescence. So on these lines, I am going to I will confine this talk, and so yeah. So first, I would like to initiate with this RE material value chain. Already, a lot of people have already discussed, so I would not go into that detail. But what I would like to discuss here is like, the RE ore. So we start with RE ore. So as of now, we have discussed about a lot of application of RE as such. But in the current scenario, the 90% market value of this entire RE oxide value chain is coming from the permanent magnets, or that permanent magnets or the alloys and magnet products, so all put together. So they contribute to the 90% of the value of RE oxide value chain. So if someone is mining RE ore or doing RE processing, so 90% of the revenues are going to come from a buyer who is into permanent magnet manufacturing. So that's how the value of NDFEB magnets have emerged out of other applications of RE, because all other applications are either have diminished over the years, like phosphor, specialty glass, battery alloys and all, either they have diminished or the values are diminished there. So like the phosphor, which at one point of time for CFA phosphor, which one point of time people used to sell at quite high values. They from that point in 2011-12, what was tribe and phosphor value for a CFN powder was there in 2011-12, and now if you see, so that has came down by 70-80%. So similar thing also happened in catalytic converters, obviously proteins, because these are the technologies which are bit going towards obsolescence. So catalytics are going to be obsolete because of the new EV is coming up, EV mobility, so that no need of that kind of catalytic converters anymore. Similarly, phosphors are going out because LEDs came in. And for polishing and coating in specialty glass, there are other options emerged like which can replace the RE content there. But NDFEB magnets remained an area where not much of replacement is there as of now, and also in the near future, it is not visible that whether I will be able to replace NDFEB magnets. So most of the market value of RE oxide value chain is going to be derived from the NDFEB magnets in the future also. And now the application wise, if you see, these are used for permanent magnet generators for wind farms, then motors, then sensors, hard drives, and other magnetic force applications like filters, separators, and all. So if you leave aside the magnetic force application, but then the motor application itself in different categories, whether it is EV motor, whether it is energy efficient motor, whether it is a conventional automotive motor for wind, so for wiper blades, for window, to roll the windows and all. So all these put together, so they are going to contribute heavily in energy security of it by two ways. So one is like directly if you use NDFEB magnets for EV, so EV is going to be there and you will not be using much of fossil fuels. So that is there. Apart from that, even for to generate more energy efficient appliances and all, you need to have motors based on these magnets. So people like even now also in India, the major portion of motors are being made basis the induction kind of technology, which is old and which consumes a lot, which have a lot less energy efficiency compared to the permanent magnet-based motors. So that shift has to happen, and when that shift will happen, obviously a lot of demand for NDFEB magnets will come. So from those two streams, one is the EV and another is the energy efficient motors. Now, again, demand supply wise, again, you can see here. So what I was telling, in the right hand side graph, the NDFEB magnet consumption, how it is going to increase. So the most of the increase everybody is expecting to come from obviously the e-mobility, and second number of high increase is going to come from the consumer electronics part. So these are the two verticals from where most of the demand for NDFEB magnets will come globally. So right now this is hovering something around 1,20,000, 1,30,000 tons global consumption is there, which is expected to reach up to 3 lakh tons by 2035. Okay, so accordingly with this, there will be a supply gap of close to 4750 tons of NdPr oxide by 2030. And in the image you can see most of this supply is coming from China. Then second is Linus. Then there is MP materials from US. Then obviously our very own IREL is also there, which will be supplying a certain amount in this gap. And just to have a idea about how much ND magnet is required for a particular EV. So for one EV, you typically need 1.25 kg of NDFEB magnets. For a four-wheeler EV, which is 80 to 100 kilowatt. For a two-wheeler EV, which will be 8 to 10 kilowatt, like one which recently Ola had launched. So that uses quite around 0.2 kgs of NDFEB magnets. So this is about the demand in India, which we have estimated during our last 2 years of study along with our global consulting firm EY. We have done that study with them, this demand. So this is how it looks. So in 2019, the demand of in tons, it was 500 ton, and that has not changed really because in 2020 COVID came and then it is 2021. So last 2 years, not much have changed. So at that point of time, the forecast was like that it will by 2022 it will go up to 2,000 tons, which is not really happening as of now. So maybe something around 800 or 1,000 tons of demand maybe there in 2022 as of now. So, but this was the projection at that point of time, depending upon the interaction with different buyers there in different segments. So you can see one of the biggest existing buyers are the wind turbine manufacturers. So we have 3 or 4 wind turbine manufacturers who do the permanent magnet based generator manufacturing in India, Vestas and Renew, and all 3 are based out of Chennai only. So they do this and they have this fixed demand, but this demand is the cost is quite low for this demand. Other than that, the new demand, you can see it is very, very small. It is still emerging in different segments, be it consumer electronics, means like for personal PC computer and all, because all the motors used in PCs which are assembled in India, they are imported from China. So similarly for a smartphone also, since multiple new this manufacturing facilities have been set up. So there some demand came due to Xiaomi, due to Foxconn factory and all. But how much that will go up, that is still a question, because they are also importing most of the things as of now from China, the subsystems basically. BLDC fan manufacturers are a segment which was emerging and which can emerge quickly because they offer a lot of value in terms of energy efficiency of the ceiling fan. So a lot of new players have come in that particular space, and similarly for BLDC motors. But EV, either a 2-wheeler or 4-wheeler, so that is something yet to be seen, that how fast the country will transition to the e-mobility, towards e-mobility, and even if the transition happens, how fast the transition will convert into a manufacturing backed, Indian manufacturing backed setup here. Like Ola is saying that they will be producing 10 million number of 2-wheelers by in the next few years or so. But whenever they will reach, so that has to be seen. And for a 2-wheeler, like 1 million, we are estimating that 1 million will be by 2025. And for 1 million, typically you will need 200 tons to 50 tons of ND field magnets. So for 1 million even 1 million EV motors are produced in India for 2-wheelers, then also the demand of magnet is going to be 200 to 50 tons. So not too much. So this is how about the demand, and 10,000 can be seen by 2030. That is even with the COVID. That's what we hope. So this is again about the same, but in terms of like what can be the value, what value we can assign to that demand, and what is the base scenario, what can be the high end scenario, means the optimistic scenario. So this was like 5,000 ton in 2025 at 2,500 crore. That would be the market, and this is going to be 9,000 ton, 4,400 crore market. But again, this is because of the COVID. I think this is not possible for 2025. So this may happen in 27, 28. So this will definitely be displaced by 2-3 years of time, like the demand. And for 2030, obviously. So the whole point is of showing this, that the demand is right now it is not there in India of that much of demand that at which you can make a big size of plant viable. But yes, the demand is expected to come, and it has to come. There is no other option that this demand will not come. Like the 10,000 or 15,000 tons it just cannot happen because this is linked, all the consumption categories you can see. This is all linked with something in which has to happen in India. The solar power pump has to be manufactured. The energy efficient elevator motors, smart BLDC motors has to be manufactured. Without that, it will not work for us. Similarly, EVs has to come. So there is no other option. So all these areas are there which has to come, and so if those manufacturers will come and everything will be there, so demand will obviously be there. So that's all. So this long-term demand is at least is not an issue. So now going on this about China. So what I will so yeah. So for China we know that different the REO. They are regulating, first thing that they are regulating the RE oxide production as well as the smelting RE metal production also. So both the things they are regulating. So each year, like they were doing in 2017, they were doing 1 lakh tons of REO. Now they have done 1 lakh 20, then 1 lakh 32. This year also it is close to 132. So not much of increase there. So because of this regulation, obviously they are able to control the price. So whenever they want, they can reduce the pricing also. And whenever they want, they can control this pricing as far as the REO pricing as well as the RE metal pricing is concerned. So this is something which is controlled by China, and for other countries, I think they would need to develop their own pricing mechanism and their own. If everybody is going to be independent in this area, in this particular segment of RE value chain. So each country has to have their own RE deposit. Each country has to have their own extended RE value chain, and each country has to have their own RE pricing system and RE product pricing system. Because this China comparison is not going to work as long as, because they have a different altogether the whole policy there. Everything is not very. It's quite opaque. So we don't know that how they are controlling it, what is happening, and what will be the pricing in the coming years. And so this next slide shows that what are the different grade of productions percentage-wise, what is happening in China. So I think if we see the left-hand side, that summarizes it well. Like global production in 2019 was 2 lakh ton, which is expected to be go to up to 2,50,000 ton. Out of that, the low-end magnets were the highest, but that is not a segment which is expected to be increasing, simply because the main demand, everything will be coming from energy efficient motor and EV going forward, the additional demand, and that two particular segment needs high-end magnets. So anybody who is coming now into this business has to plan for a high-end magnet manufacturing, SH, UH, ES series, so that they can remain sustainable, they can remain relevant. So that we have discussed about the China capacity and China the global manufacturing also. But now let's look at the capacity utilization in China. So because a lot of times, so this is the capacity utilization in China. Even whether it is RE plant, whether it is RE separation plant, or whether it is RE manufacturing plant. So more or less the average utilization rate in China is between 60 to 62%. So they still have 30 to 40% of capacity which is lying idle because government is not increasing the RE quota and the capacity is built there, and that's why they can offer much lower prices because that capacity cost is not there for them. Anytime government will say, okay, that we want to go to this, and they have that spare capacity available, and they can utilize that capacity, and they can put the product in the market. So this is the capacity for NTF magnet production. You can see. So right now, this is for April 2021. So China is doing by April 2021 this year they are expected to do close to 210,000 tons of magnet production. Which will be almost equal to 90 to 93% of global magnet production, because rest then 20,000 only in Japan and the WAC in Germany. So they will be doing. rest everything is being done by China. So 92% will be from China. But still, if you see the capacity they have, that is huge. 3,70,000 is the production capacity they have. So still a lot of spare capacity available to them, and that's why means the magnet cost, the magnet pricing is not increasing, and that also we will see. And this is about the rest of the world scenario. You can see the Hitachi Metals, which had 7,000 tons capacity, recently being taken over by Bain Capital. So they may initiate their efforts to capture US market. Then we have TTK and Showa Denko, which have 5,000 ton capacity. Shimizu have 8 to 10,000 tons capacity. One is small player, Shagami, they have 360 tons capacity. So this is about Japan. So they don't have any RE, ore mining. So for RE ore supply or oxide supply, they are completely dependent on Lynas, which is in Australia. So they supply the oxide to Japanese players. And then in USA, we have MP Materials, which is doing close to 40,000 tons of RE ore concentrate, which equates to 6,000 tons of NdPr oxide. And this is again being sent to China because there is no magnet manufacturing in US. VAC and its subsidiary Neorem, which is in Europe. So they have 2,000, 2,500 tons of combined capacity in Germany, and Neorem is in Finland. And then we have a small plant of Magnequench Silmet, who do 500 tons of RE metals. Apart from that, obviously, we have less common metals and other small players in Russia and other. They are not that significant. So all put together, you can see that the first thing that nowhere apart from China or obviously Japan have developed that magnet manufacturing capacity much earlier to China. So they are continuing with that capacity. No significant capacity expansion in terms of magnet has happened in Japan. No other capacity came up in US, Europe, or Australia or other places where some sort of NdPr oxide supply is available. So to summarize about the demand supply gap, what we can see that the demand supply gap in India is there, but only from localization perspective. So competing with Chinese in export market and all that will be quite difficult in that way. So no barrier as of now is there or additional duty on magnet import. So the users are they're not worried about like buying from a local supplier or buying from Chinese or any other country out of India. So that is there, and in some cases the duties are even waived off for captive consumption and value addition. So that's why the user industries are not facing much threat. The second issue, this is also one main issue, like India demand of NdFeB magnets is spread across many buyers. So there are a lot of buyers who do this thing in very small quantities, except for the winter wine buyers who are 3 and 4 and who buy big chunks. But apart from that, everybody is like, somebody will say that I will need 100 pieces, somebody will say 1,000 pieces, something like that. So that translates into very small amount, kgs kind of amount. And that all that kgs across India, if you put together, it will become say 400 ton, 500 ton. But because of that different demand of this spread in demand, a lot of size and grade demand comes up. And for that to cater by a single magnet manufacturer in India is very difficult, because you have to put a lot of capex to cater each size in terms of the sizing, in terms of grinding, in terms of machining, and in terms of getting the grade. So that is a big challenge. Next is obviously a lot of end users are preferring to import the complete subsystem, including magnet itself, because even if because of magnet, even if they can save some cost, but they don't want to invest in any capex here. The end user, they don't want to capex any capex here to manufacture that subsystem. So what they do, they import directly with magnet and book some loss event. So that is also okay with them. Obviously, demand is expected to come online because of EV or energy efficient motors, but it is not there yet. So that is something one has to see that when it is going to come and when it is the exact transition point is going to happen. So whether it will be 2022, 23, 24, that is something we are watching. So these are the main points about demand supply gap. Now let's skip this. So about like we have already yesterday we were discussing about a lot of discussion happened about the technology part. So availability and this thing, whether technology is available. So here on this part, so what I would like to, since we have been obviously interacting with a lot of tech providers from Japan, China, and all. So what we can say that like for oxide to metal conversion, so fluoride oxide molten salt electrolysis is the de facto technology for conversion at economically viable scale. So other techniques are available, obviously calciothermic as well as the chloride route, but they will not be economically viable. And currently the current efficiency in China are 70 to 80% for the fluoride oxide molten salt route. And recovery rates for metal recovery rates are around 95% and above. And the Chinese focus is entirely about the improving the current efficiency, developing a small size but efficient cells and having reduced PFC emission. So that is the whole target along with the automation of the system. And there is also embargo from Chinese side on oxide to metal transfer outside China. So and that is not because the technology is very novel or that is not available anywhere, but because the technology Chinese have developed that is very cost effective. So and if you don't have that technology, you will not be able to again compete with with them in that way. So even the Chinese manufacturers are also, there is intense competition among them, the Chinese metal manufacturers, oxide to metal. And typically oxide to metal manufacturer in China have less than 5% of EBITDA. So I mean that EBITDA level or profit margin you can say. So that is less than 5%. Even the biggest company of China who is doing oxide to metal, which is Reliant, so they also operate at hardly 1 or 2% of profit. So that's how, because there is very, very small gap there. So next is about the manufacturing process. So it is already covered. So I will just go through quickly. So we have the typical, this is the typical process from an industrial setup perspective. You start with melting, strip casting, hydrogen crepitation, then jet milling, then powder blending, magnetic alignment and pressing, inner atmospheric sintering. Now that so now after sintering, whether you are employing that slicing followed by GBD and heat treatment or not, so that is going to make a big difference, because based on that particular step, you will be able to have a high temperature grades, or you may not be having high temperature grades with the minimum amount of HRE diffusion. So that can be enabled by only by GBD, and that is one technology which is hard to get from China or Japan. But again, that is also commercially available. So there are suppliers who can provide the equipment for GBD and heat treatment from China as well as Japan. And there's other equipments, whether it is strip casting, whether it is HV, whether it is jet milling, whether it is magnetic alignment pressing, sintering. So all these equipments are, at least it is available from China readily. And Japan, not much people are involved into manufacturing of these equipments anymore. So, but even from Japan also, there are some suppliers who can provide this, as well as the grinding, washing, cleaning, surface coating, magnetization, everything. So all the, apart from GBD, most of the setup is quite readily available from the individual suppliers. But obviously, getting that equipment and then, aligning into optimizing them for a particular process, that is still a task. So these are some of the, you can see the setups, typical setup. So here you can see on this is strip casting. So typically for strip casting, people prefer to have only one unit. It can be, if you are going for a 3,000 ton plant, it will be 10 ton per day kind of setup. This is hydrogen decapitation furnace. So this actually, it cannot be a single unit because of hazardous nature of this furnace and all. So this comes in small sizes, so you have to install 2, 3, 4, 5 as per your need, different type of HD furnaces. This is jet milling. So this also normally installed as a single unit for a particular plant size. Then you have this sintering furnaces, which can be again, so there you have option, you can install individual kind of batch type of sintering furnace, a line of that, or you can install a continuous kind of sintering furnace there. And this is the pressing units. So pressing units also, they typically installed in China as a single unit of 2, 3 different sizes, because they press in size of blocks. So then the blocks has to be cut by these kind of slicing machine, an array of that, and these are the coating units. So this is also typically one unit. So like you can see that this is one unit, this is one unit, this is a single unit, this is also kind of single unit. So all these 3, 4 single units are like, they are one of the costliest, and they form the major portion of entire capex. Other than that, the smaller units which can be set up in different sizes or different in an array kind of setting can be done. So there you have some modularity available. But for these kind of systems, normally you don't have that modularity available, that you can install a 1,000 ton plant and then you can switch that over to a 3,000 ton plant without changing these individual units. So that is a issue. So if you want to go for a 5,000 ton plant, or even if you plan to do a 5,000, but you will be initially doing only 1,000, so you will prefer to go for a 5,000 size of these units so that you don't have to change them later. And that will add obviously into your capex at the very initial stage. So, these are some of the cost reduction strategy for an Indian manufacturer, which can be there. So to secure a low cost raw material supply, 10% cheaper than prevailing rate in China, because that will offset the higher process cost in India, because of initially you will have more than 10% process cost compared to China, obviously. And then optimization of magnet grade with minimum or zero HRE using technology like GBD and all. So this is also very, very critical, that you need to have a tech which utilizes minimum or zero HRE, because HREs are not available in India, and there is no further scope of getting the same in the future also. So use of hafnium iron alloy to save some percentage of dysprosium iron or terbium. Similarly, use of NDCE FEB and NDPR FEB dual alloys to save some percentage of NDPR, because NDCE is cheaper. And secure large quantity orders, and using continuous type of vacuum sintering furnace instead of batch type. So that will lead significant energy cost saving, electricity cost saving, reduction, and very stable magnetic properties. Obviously, the initial capex is going to be higher, but in the long term, it will benefit. So this is about the requirement. So there is a certain requirement about humidity and temperature also, which should be 60%, not exceeding 30%. So that also makes this plant location a bit. You cannot put on the coastal areas. You cannot put on very hot and humid areas. So kind of prime location, maybe Bangalore or there, where the all round the year where the temperature is cool and the humidity is good. So that type of area should be targeted. 2 acres of land will be required to set up 10,000, 1,500 TPA plant, and 4 to 5 acres will be required for 1,500. So all put together, 5-6 acres of land as per the National Building Code for 1,000 to 1,500 TPA new manufacturing plant. The setup time can vary between 12 months to 24 months. So that is something between which one can get the equipment from China or Japan and install them, the equipments, and another 6 months will be required to train the manpower and commission. These are the grades. As I have said, like obviously the audience, I think here knows very well, because a lot of discussions are happened. So they know that there are different type of grades in magnet as per the temperature. So the grades which don't have any number, so they operate at 80 centigrade, then it goes up by 20 kind of. So M is operating at 100, H is operating at 120, SH is 150. So that's how it is. So maximum it goes like right now there is BH grades are available, so which can go to 240. So these are the different grades are available. And as I was telling, like the technology, basic technology without GVD is readily available. So that without GVD will cover all the grades in blue, and the grades, almost all the grades in green can be covered without GVD. The grain engineering, initial grain engineering or dual LR technology, you can achieve 30 EH, 30 VH grades also. Other than that, for the light orange, for dark orange grades, you will need to have access to the grain mounted technology as well as the other technologies which are required to get this kind of high porosity combined with the high remanence. Pricing wise, so you can see here, so the pricing is quite what I was telling initially, the pricing doesn't match really with the oxide or metal price increase in magnets. So the NdPr metal prices you can see, or the oxide, they move in sync. So oxide and metal move in sync because there is almost 0% a conversion profit. So if it is 40, so this will be 25% higher. So that's how it is. So so you can see that the oxide or metal have doubled, almost doubled. But okay, here the 2020 price is not there. But in 2020, between 2020 and this 21, the pricing of magnets have increased only by 15 or 25% at the max, where the oxide or metal prices have doubled. So that puts extra pressure basically on the magnet manufacturer. It is good for a metal or oxide supplier, but not good for a magnet manufacturer. As far as because the pricing is linked with the Chinese market, if the people are in Chinese market there. So now you can see this is the pricing. You can see this starts with like 35H. So what are numbers here? You can, these are in all in renminbi. You can multiply this by 11 and you will get the INR prices. Something around 22-2300 per kg is the starting price for 35H type of grades, and which goes up to 3,200 rupees for 50H type. So not that means costly. So in that way, quite cheap. Obviously, it will land to India, so landed cost has to be will be additional 10 to 15% cost will be there. So if you see this number, you can see that. So this was the like July 19, and this is like May 21. So remaining 2 years, as we have earlier seen, the metal and oxide prices have doubled. But here you can see the between 2005 and 170. So hardly 20% of increase in the magnet price. So this is the one issue which is not, so this linkage is not linear there. This is our own estimation at some point of time for India magnet pricing. So, but it is obviously the best case scenario. It will be less than this. So average was coming around $52 per kg, which will translate into something around 3,800 rupees. But actual buyers are like, even their average is a bit less than that. But again, that depends on what kind of grades and what kind of weighted average for those grades you are considering price. So that can range from 37 to 66. So that is much better way to understand this. So this is the pricing for your magnet. Now, another important point is like in a magnet, a typical average sale price is not something which is like the only magnet manufacturing cost. So you have something called magnet manufacturing cost contribution in the pricing, which is only 50%. So this 50% only will take care of any kind of fluctuation in oxide pricing, metal pricing or oxide pricing as such. But other than that, you have something called grade performance premium, which is 20%. So that is like how much of your supply can adhere to a particular grade requirement. So sometimes as a supplier, you are supplying, but then your performance is not that much. So the OEMs will not be paying you that kind of. Similarly, the size performance premium is 20%, brand premium quality recognition standards. So all put together, the manufacturing cost contribution in the ASP is only 50%. So this is so again about whether it is a commodity business or product business. So it is not a commodity business as of now because there is no established index for NDFeB magnets, and it is not. So it is mostly one-to-one kind of setup. So where you deal with the OEM buyers on your own, and then you finalize the pricing after lengthy discussion on magnet design, drawing, quality qualification, rejection, penalties, and all. So all put together, this is a business where you can have, at the best cases, 10 to 15% of EBITDA. This is the cost components for NDFeB magnets, where you can see what are the different cost components as such. And this is, I think, for a 1,000 ton of scale. Obviously, when the scale will change, your this composition and everything will change. The cost components will change. But for 1,000 tons, this is the composition of different cost components. So you can see the 60% is only coming from the raw material. So from a manufacturing or product perspective, it is very high. 60% if it is coming from raw material. So any fluctuation in raw material will lead to eat your whatever EBITDA you are having. So it is only 7% of EBITDA at 1,000 tons, which we could have calculated. And process cost and everything, you can see it is 16%. HEA is selling in general admin. R&D 1%. Product qualification is 1%. Direct labor is 7%. So very reasonable kind of structure, but still because of the a lot of weightage is for the raw material itself. And now again in the raw material bifurcation, this is the bifurcation of raw material cost itself, like the bifurcation of this 58%. So here you can see the 50% is NdPr cost, whereas 35% is the HREs, where you consider 2 or 3% of debye doping in the entire magnet for an average grade. So this will come around 35%, which has to be imported from China, because it is not available. And then you have ferroboron at 7%, and the metal will be 8%. So 10% cost reduction in NdPr oxide pricing will increase your EBITDA by 3%. Similarly, 10% cost increase in HRE will decrease your EBITDA by another 2%. So this is kind of a balancing act. So if you are getting any kind of rebate here, but if there is no rebate or there is higher cost here, so it will offset for you. And this is something like the typical NdPr oxide requirement which you can have. So like if you have 500 tons of NdPr oxide supply, you can manufacture close to 1,000 tons of single magnets. If you have 1,000 tons of supply, you can manufacture close to 2,100 tons of rest will be like the lead. Obviously, this will also be magnet, but it is low grade block magnet, which you cannot really sell at the same pricing. Has to be sold at less than 40% of price of whatever this price is, which is the market norm. And these magnets are typically used for the application where you don't need the electromagnetic performance out of the magnet. You only need a attraction force performance out of it. Basically, for furniture and for all those applications, you can use these low grade magnets. So this which will be produced here. So typical revenue wise, you can see 500 tons will fetch you close to 60 million. So this is 450 CR, I think, in Indian, 450 CR. And 1,000 ton will fetch you double, 120 million. So this is 900 CR. So basically 900 CR will be the revenue for if you put 1,000 ton of magnet plant. So 1,000 ton of supplies there, and you can put a plant of this configuration which can effectively produce 2,500 tons of magnets, both grades. So finished as well as the block. Now coming to the, I think, last few slides. So this is about capex and scale. So this is one big issue here. So because as I already said, like there are fixed units in the plant configuration. And then there are modular units, also small modular units. But there are fixed units which have the basic cost, which increase the basic cost of the plant depending upon your planning in the future. So if you want to go for a 5,000, you are right now setting 1,000, you have to invest for a 5,000 kind of size for certain equipments at the initial stage. So that's why the cost is increased versus the capacity is not linear. Not linear means like it is not 1 to 1. The slope is not 45 degree. And you can see that for a 1,000-ton sellable production plant, the typical capex required will be 26 million or 195 crore. Whereas if you go 10 times 10,000-ton plant, you will need to spend 150 million or 1125 crore. So there a lot of capex reduction happens when you go high on the scale. And that capex reduction will actually help you in fetching more profit out of the plant and make the your overall project viable. So just to show the same with this example, you can see like if we do 500 ton of magnet production, then effectively we have 0% EBITDA. And this is the bifurcation. So by process cost goes for 20%, and then there is a fixed cost of SGA with that will go 12% because your revenue is less. So these percentages are increasing, and direct labor is also kind of fixed whether you go for 500 or 1,000. So effectively you have 0% EBITDA at 500 level scale. At 1,000 level scale, 1,000 tons of sinter magnet production, you have 7% EBITDA. And if you go for 2,000, you can see 10%, then it goes to 15% or close to 20%. So numbers are like obviously a bit rounded off. It will be slightly here and there, maybe 0.5% up or down. But this is the typical behavior in this particular magnet plant setup and the magnet manufacturer. So just to take the same from example, if I set up a 10,000 ton sinter magnet plant, I need 4,625 tons of NdPr oxide and 1860 tons of low grade block magnet will be produced. Along with whereas for 2,000 tons cell, 925 TPA of NdPr oxide is required and 372 TPA of blocks will be produced. So if you see the working here, so revenue wise, I can fetch close to $500 million for 10,000 tons plant, whereas that will be 108 million. And on a EBITDA level, whereas in this year I will be fetching EBITDA of 108, here it will be 10. Then the DA is the depreciation and amortization, and the interest is the interest for my investment. So all put together, you can see the stark difference. For a 10,000 TPA plant, everything remaining same, I can fetch around 55 million of profit. But for a 2,000 TPA plant, there will be nothing. And all this working is without considering any technology transfer cost or any technology related royalty to a third party. So if that will come into picture, so essentially this will become negative. So yeah, so apart from talk about the RM supply scenario. So 400-500 tons is available currently from IREL. No availability of additional quantity even at higher cost from, this is not about IREL, but not from outside India. So it is not available as of now. We have discussed with many people, but it has not been available. HREs are not available in India, has to be imported from China. And this will impact 30% additional cost is currently coming to Indian manufacturer due to import duties, transportation in China, right? New NdPr oxide capacity, particularly Arafura, and then there is a 3R mining in Russia. So they are expected to come online by 2024-25. They will add maybe 6,000, 10,000 tons of NdPr supply as per their plans. But obviously, it has to be seen that how the supply comes and how means how much it will come in the phase ones. So this is the request to policymakers from our side that we would request that adequate quantities of necessary raw material shall be made available in India, either by exploitation of our existing resources or by acquiring new resources overseas, as we had been discussing yesterday. Like the government is also planning for new resources, so to make the magnet manufacturing viable, obviously. So if this step is there and the resources are available, then obviously the people, the investor here can think about putting the plant, manufacturing plant in India, and they will not have a threat in terms of, they will not feel a threat in terms of whether my plant will be, I will not be able to scale up the plant, whether my plant will be viable or not in the long run, 2, 3, 5 years. So initially, even the investor is ready to book the loss, but then they would like to have some kind of profitability from that plant after 5 years or so. So that visibility has to be provided, means it should be provided. Um, uh, and a commercially sustainable NDFE plant size can be of 5,000 tons. So adequate visibility and guidance shall be provided to secure raw material for such a plant. Additional 15% of safeguarding duty has to be there, because right now there is no duty, and the Chinese manufacturing cost is obviously going to be lesser than this, because anybody manufacturing in India with HRE has to incur 30% tax after HRE. So that has to be offsetted if this has to be made viable in India. So that additional safeguarding has to be there for and the entire value chain shall be covered in PLI scheme. That is also required to boost the scale of possibilities and year-on-year capacity addition. So this is all from my side. Thank you. Thanks.
Thank you so much. Can we play the same slide? And right now, I would like to request our Honorable CMD Sir to virtually present a memento as a gesture of love and token of appreciation from the family of IREL to Gaurav Shukla Sir.
Thank you.
Thank you so much, Dr. Gaurav Shukla, once again for your time and this elaborated presentation. Thank you so much. Well, ladies and gentlemen, yeah. Okay, we are continuing, and let me tell you that we will be announcing the lunch break. But before that, may I request all of you, since it's the last day that we are celebrating, this is the second day, and thereafter we would be back to our workstations and would be busy in our work life. So can we have some canon moments as of now? Can I take your permission that you would be spending few seconds and we would be taking some group pics? And we have divided that few people would be standing up in the dais and few would be below the dais, so that we can capture all of you. Can we go for this? Thank you so much. Please spare your few moments. And may I request, meanwhile, our event team to please clear, or let's keep it aside so that we can have more space on the stage. Team Eyeball. Okay, take care. So as we have decided, this will be there, but I request all of you who are sitting at the last, first, middle, and wherever you are occupying the chairs and table, please come over here and join us, because this moment is never gonna come back and we are required to capture the same. Please come forward, gentlemen. And may I request team of IREL to please guide them how to stand and where to stand. And photographers, be ready. May I request few of you to please be on the stage. Some of you can be on the stage and we can join us for the group photograph, because I'm sure many of you won't be able to get chance in this year, maybe particularly, to be together and to take this picture.
Madam, you come first.
Thank you, sir.
1909, discovered something interesting. Yellow grain-like particles that were sticking to coconut fibers exported from Kerala. That is the beginning of our story. Envisioned by Dr. Homi J. Bhabha, the father of the Indian nuclear program, the first chairman of Atomic Energy Commission of India, Indian Rare Earths Limited was incorporated in 1950 to unleash the massive potential of India's rare earths resources and to cater the strategic requirements of the nation and become a full-fledged central government undertaking under Department of Atomic Energy. IREL, that started out as few plants in South India, has grown across different parts of the country while making ourselves indispensable in the global rare earth and beach sand mineral industry. Ilmenite, rutile, zircon, sillimanite, garnet, and rare earths mineral. From the shores of Kerala to that of Odisha, the nation identified deposits of these precious heavy minerals. Our product range varies from minerals, chemicals, to rare earths compounds. Technological advancements recognized a wide array of end-use applications of our products, ranging from the toothpaste you use to complex roles in the nuclear industry. Over the years, IREL has accomplished significant milestones. In recent years, we have witnessed a massive surge in production and sales turnover of over 10 billion, contributing to the country's growth. Community-oriented, socially responsible, and environmental-friendly mineral harvesting and value addition broaden our horizons and capability. In this momentous occasion of our platinum anniversary, IREL India Limited is proud to present our key projects that will shape and broaden the profile of our nation. The Rare Earth and Titanium Theme Park that will enhance the production and consumption of rare earths across the whole of India, which will boost entrepreneurial opportunities. The Rare Earth Permanent Magnet Plant that is set to come up at Visakhapatnam that will add strategic edge for India. More than an organization, we helm the complex role of driving the nationalistic spirit and be in the forefront of driving the country to a symbol of progress and power in this decade.
IREL, Unleashing Values. If you strive to go further than what you see, if you look past these beaches formed over millions of years, you would find alluring beach sand mineral deposits washed to shore each day, every day. And in India, we are blessed with one of the richest and largest coastline placers. With over 6,000 kilometers of coastline, our beach sand deposits and dunes spread across the states of Odisha, Andhra Pradesh, Tamil Nadu, and Kerala contain heavy minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral. India has abundant deposits of ilmenite, rutile, zircon, sillimanite, and garnet. Indian resources constitute about 10% of world reserves of ilmenite, 12% of rutile, and 5% of zircon. India meets about 18% of the world's requirement of garnet. Back in 1909, when German chemist Herr Schomburg realized that the shining yellowish-brown sand particles sticking to coir, a coconut fiber shipped from India, contained rare earth mineral which was used in the manufacturing of gas mantle, led to setting up a few plants in southern India and ultimately IREL with plants in different parts of India. IREL India Limited is one of the key players in the global beach sand mineral industry and has been the driving force behind the growth of hundreds of industries in country and has been proven reliable global partners for end user industry. With different deposits located across India, sea washing and surface collection are the two main processes used for the winning of mineral sand. IREL plants are strategically located that are close to the richest mineral deposits and are near to major ports and cities. The method of winning is determined by the terrain, like in intertidal areas where replenishment of heavy mineral sands happen mainly due to wave action. In such terrains, manual collection is done for harvesting the replenished material and transported to the mineral separation plant. While in terry and coastal areas, where there are inland heavy mineral sand deposits, the extraction of mineral concentrate is carried out by using the mechanized surface collection, like floating dredger and tipper and excavator combination, with simultaneous backfilling. With a series of mineral separation processes, extraction is done thoroughly for every mineral from the deposits using cutting-edge technology. Depending upon the physical properties, especially its specific gravity, electrical conductivity, and magnetic susceptibility, the individual minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral get separated from each other in our mineral separation plant. Our product range varies from minerals, rare earth compounds, to chemicals. Ilmenite is the primary ore of titanium. Ilmenite, extracted at IREL, is used in major applications like in critical components of spacecrafts, aviation industry, healthcare industry, pigment industry, and various high-performance alloys. Rutile extracted has applications in the electrodes industries and in the production of titanium pigment. Zircon, a light brown mineral, is mainly consumed as an opacifier in the decorative ceramics industry. It has a very wide variety of uses in refractories, foundry casting, advanced ceramics, and a growing array of specialty applications as zirconia and zirconium chemicals. Its sponge and alloys, including in nuclear fuel rods, catalytic fuel converters, and in water and air purification systems. Sillimanite is extensively used in furnaces of metallurgical and glass manufacturing industry due to its high refractoriness, very low coefficient of thermal expansion, great resistance to thermal shock, abrasion, and slag corrosion. Garnet, which is rose red to pink in color, is a good abrasive, and its uses include sandblasting, water jet cutting, and also as water filtration media. The yellowish light green rare earth mineral is used to produce 17 high pure individual rare earth elements with applications in almost all major industries. We also produce chemicals including rare earth chloride, trisodium phosphate, and thorium nitrate used for various industrial applications. We ensure that our products meet the highest global quality standards. We use state-of-the-art technology for mineral separation and extraction of rare earths, compounds, and chemicals. We have implemented integrated management system in our business processes. We have invested in fully equipped quality control laboratories and R&D centers for achieving the best and to stay ahead in the race around the world. Our rare earth extraction plant, REEP, at Odisha has an overall production capacity of about 11,000 tons of rare earth chloride and associated products. Our high-pure rare earths plant at RED, Aluva, is specialized to produce rare earths oxide and carbonates. Restoration of area after mineral collection is considered prime responsibility of the company, and we ensure that the area is refilled, afforestation is done, used for rehabilitation and community development. Whereas in some areas we work along with the local fishermen community by desilting of mineral-rich sand from the fishing harbors that helps ease the navigation of fishing boats. We are benevolent, and we believe it is our duty to give back to the society with a focus on community health care, rural infrastructure development, skill training, education, and community development.
Indian Rare Earths Limited is a Government of India undertaking under Department of Atomic Energy. It is having the mandate of extracting these sand minerals from the beaches as well as from the inland deposits. These minerals consist of titanium-bearing minerals, zirconium-bearing minerals, as well as rare earth-bearing minerals. Each of these minerals after extraction are finding niche application in varied area. IREL is a multi-product, multi-unit public sector. The plant is located across the coastal stretch of the country. The core philosophy of the company is not only to extract the minerals but as well provide improvement in the quality of life of the people in the vicinity of our mining area. Besides, public sector has a global vision and mission. As per that, not only we would like to be leading supplier of the minerals, as well we should be contributing a lot for supplying strategic material to Department of Atomic Energy. We have made a strategic management plan 2025. As per that, we would be expanding horizontally, as well we would be expanding vertically in the area whichever element is befitting to our mandate. Besides, R&D is a very important aspect in the rare earth business. We are being continuing with that, and debottlenecking of various issues in and around is another important objective.
The minerals, rare earth compounds, and the chemicals we produced have a presence in everyone's everyday life, right from the toothpaste you use to the satellites that connects you to the world. IREL, Unleashing Values.
1909, her chemist discovered something interesting. Yellow grain-like particles that were sticking to coconut fibers exported from Kerala. That is the beginning of our story. Envisioned by Dr. Homi J. Bhabha, the father of the Indian nuclear program, the first chairman of Atomic Energy Commission of India, Indian Rare Earths Limited was incorporated in 1950 to unleash the massive potential of India's rare earths resources and to cater the strategic requirements of the nation and become a full-fledged central government undertaking under Department of Atomic Energy. IREL, that started out as few plants in South India, has grown across different parts of the country while making ourselves indispensable in the global rare earth and beach sand mineral industry. Ilmenite, rutile, zircon, sillimanite, garnet, and rare earths mineral. From the shores of Kerala to that of Odisha, the nation identified deposits of these precious heavy minerals. Our product range varies from minerals, chemicals, to rare earths compounds. Technological advancements recognized a wide array of end-use applications of our products, ranging from the toothpaste you use to complex roles in the nuclear industry. Over the years, IREL has accomplished significant milestones. In recent years, we have witnessed a massive surge in production and sales turnover of over 10 billion, contributing to the country's growth. Community-oriented, socially responsible, and environmental-friendly mineral harvesting and value addition broaden our horizons and capability. In this momentous occasion of our platinum anniversary, IREL India Limited is proud to present our key projects that will shape and broaden the profile of our nation. The Rare Earth and Titanium Theme Park that will enhance the production and consumption of rare earths across the whole of India, which will boost entrepreneurial opportunities. The Rare Earth Permanent Magnet Plant that is set to come up at Visakhapatnam that will add strategic edge for India. More than an organization, we helm the complex role of driving the nationalistic spirit and be in the forefront of driving the country to a symbol of progress and power in this decade.
IREL, Unleashing Values. If you strive to go further than what you see, if you look past these beaches formed over millions of years, you would find alluring beach sand mineral deposits washed to shore each day, every day. And in India, we are blessed with one of the richest and largest coastline placers. With over 6,000 kilometers of coastline, our beach sand deposits and dunes spread across the states of Odisha, Andhra Pradesh, Tamil Nadu, and Kerala contain heavy minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral. India has abundant deposits of ilmenite, rutile, zircon, sillimanite, and garnet. Indian resources constitute about 10% of world reserves of ilmenite, 12% of rutile, and 5% of zircon. India meets about 18% of the world's requirement of garnet. Back in 1909, when German chemist Herr Schomburg realized that the shining yellowish-brown sand particles sticking to coir, a coconut fiber shipped from India, contained rare earth mineral which was used in the manufacturing of gas mantle, led to setting up a few plants in southern India and ultimately IREL with plants in different parts of India. IREL India Limited is one of the key players in the global beach sand mineral industry and has been the driving force behind the growth of hundreds of industries in country and has been proven reliable global partners for end user industry. With different deposits located across India, sea washing and surface collection are the two main processes used for the winning of mineral sand. IREL plants are strategically located that are close to the richest mineral deposits and are near to major ports and cities. The method of winning is determined by the terrain, like in intertidal areas where replenishment of heavy mineral sands happen mainly due to wave action. In such terrains, manual collection is done for harvesting the replenished material and transported to the mineral separation plant. While in terry and coastal areas, where there are inland heavy mineral sand deposits, the extraction of mineral concentrate is carried out by using the mechanized surface collection, like floating dredger and tipper and excavator combination, with simultaneous backfilling. With a series of mineral separation processes, extraction is done thoroughly for every mineral from the deposits using cutting-edge technology. Depending upon the physical properties, especially its specific gravity, electrical conductivity, and magnetic susceptibility, the individual minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral get separated from each other in our mineral separation plant. Our product range varies from minerals, rare earth compounds, to chemicals. Ilmenite is the primary ore of titanium. Ilmenite, extracted at IREL, is used in major applications like in critical components of spacecrafts, aviation industry, healthcare industry, pigment industry, and various high-performance alloys. Rutile extracted has applications in the electrodes industries and in the production of titanium pigment. Zircon, a light brown mineral, is mainly consumed as an opacifier in the decorative ceramics industry. It has a very wide variety of uses in refractories, foundry casting, advanced ceramics, and a growing array of specialty applications as zirconia and zirconium chemicals. Its sponge and alloys, including in nuclear fuel rods, catalytic fuel converters, and in water and air purification systems. Sillimanite is extensively used in furnaces of metallurgical and glass manufacturing industry due to its high refractoriness, very low coefficient of thermal expansion, great resistance to thermal shock, abrasion, and slag corrosion. Garnet, which is rose red to pink in color, is a good abrasive, and its uses include sandblasting, water jet cutting, and also as water filtration media. The yellowish light green rare earth mineral is used to produce 17 high pure individual rare earth elements with applications in almost all major industries. We also produce chemicals including rare earth chloride, trisodium phosphate, and thorium nitrate used for various industrial applications. We ensure that our products meet the highest global quality standards. We use state-of-the-art technology for mineral separation and extraction of rare earths, compounds, and chemicals. We have implemented integrated management system in our business processes. We have invested in fully equipped quality control laboratories and R&D centers for achieving the best and to stay ahead in the race around the world. Our rare earth extraction plant, REEP, at Odisha has an overall production capacity of about 11,000 tons of rare earth chloride and associated products. Our high-pure rare earths plant at RED, Aluva, is specialized to produce rare earths oxide and carbonates. Restoration of area after mineral collection is considered prime responsibility of the company, and we ensure that the area is refilled, afforestation is done, used for rehabilitation and community development. Whereas in some areas we work along with the local fishermen community by desilting of mineral-rich sand from the fishing harbors that helps ease the navigation of fishing boats. We are benevolent, and we believe it is our duty to give back to the society with a focus on community health care, rural infrastructure development, skill training, education, and community development.
Indian Rare Earths Limited is a Government of India undertaking under Department of Atomic Energy. It is having the mandate of extracting these sand minerals from the beaches as well as from the inland deposits. These minerals consist of titanium-bearing minerals, zirconium-bearing minerals, as well as rare earth-bearing minerals. Each of these minerals after extraction are finding niche application in varied area. IREL is a multi-product, multi-unit public sector. The plant is located across the coastal stretch of the country. The core philosophy of the company is not only to extract the minerals but as well provide improvement in the quality of life of the people in the vicinity of our mining area. Besides, public sector has a global vision and mission. As per that, not only we would like to be leading supplier of the minerals, as well we should be contributing a lot for supplying strategic material to Department of Atomic Energy. We have made a strategic management plan 2025. As per that, we would be expanding horizontally, as well we would be expanding vertically in the area whichever element is befitting to our mandate. Besides, R&D is a very important aspect in the rare earth business. We have been continuing with that, and debottlenecking of various issues in and around is another important objective.
The minerals, rare earth compounds, and the chemicals we produced have a presence in everyone's everyday life, right from the toothpaste you use to the satellites that connects you to the world. IREL, Unleashing Values.
1909, her chemist discovered something interesting. Yellow grain-like particles that were sticking to coconut fibers exported from Kerala. That is the beginning of our story. Envisioned by Dr. Homi J. Bhabha, the father of the Indian nuclear program, the first chairman of Atomic Energy Commission of India, Indian Rare Earths Limited was incorporated in 1950 to unleash the massive potential of India's rare earths resources and to cater the strategic requirements of the nation and become a full-fledged central government undertaking under Department of Atomic Energy. IREL, that started out as few plants in South India, has grown across different parts of the country while making ourselves indispensable in the global rare earth and beach sand mineral industry. Ilmenite, rutile, zircon, sillimanite, garnet, and rare earths mineral. From the shores of Kerala to that of Odisha, the nation identified deposits of these precious heavy minerals. Our product range varies from minerals, chemicals, to rare earths compounds. Technological advancements recognized a wide array of end-use applications of our products, ranging from the toothpaste you use to complex roles in the nuclear industry. Over the years, IREL has accomplished significant milestones. In recent years, we have witnessed a massive surge in production and sales turnover of over 10 billion, contributing to the country's growth. Community-oriented, socially responsible, and environmental-friendly mineral harvesting and value addition broaden our horizons.
Ratna PSU Nalco.
In this momentous occasion of our platinum anniversary, IREL India Limited is proud to present our key projects that will shape and broaden the profile of our nation. The rare earth and titanium theme park that will enhance the production and consumption of rare earths across the whole of India, which will boost entrepreneurial opportunities. The rare earth permanent magnet plant that is set to come up at Visakhapatnam that will add strategic edge for India. More than an organization, we helm the complex role of driving the nationalistic spirit and be in the forefront of driving the country to a symbol of progress and power in this decade.
IREL, Unleashing Values. If you strive to go further than what you see, if you look past these beaches formed over millions of years, you would find alluring beach sand mineral deposits washed to shore each day, every day. And in India, we are blessed with one of the richest and largest coastline placers. With over 6,000 kilometers of coastline, our beach sand deposits and dunes spread across the states of Odisha, Andhra Pradesh, Tamil Nadu, and Kerala contain heavy minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral. India has abundant deposits of ilmenite, rutile, zircon, sillimanite, and garnet. Indian resources constitute about 10% of world reserves of ilmenite, 12% of rutile, and 5% of zircon. India meets about 18% of the world's requirement of garnet. Back in 1909, when German chemist Herr Schomburg realized that the shining yellowish-brown sand particles sticking to coir, a coconut fiber shipped from India, contained rare earth mineral which was used in the manufacturing of gas mantle, led to setting up a few plants in southern India and ultimately IREL with plants in different parts of India. IREL India Limited is one of the key players in the global beach sand mineral industry and has been the driving force behind the growth of hundreds of industries in country and has been proven reliable global partners for end user industry. With different deposits located across India, sea washing and surface collection are the two main processes used for the winning of mineral sand. IREL plants are strategically located that are close to the richest mineral deposits and are near to major port and cities. The method of winning is determined by the terrain, like in intertidal areas where replenishment of heavy mineral sands happen mainly due to wave action. In such terrains, manual collection is done for harvesting the replenished material and transported to the mineral separation plant. While in terry and coastal areas, where there are inland heavy mineral sand deposits, the extraction of mineral concentrate is carried out by using the mechanized surface collection, like floating dredger and tipper and excavator combination, with simultaneous backfilling. With a series of mineral separation processes, extraction is done thoroughly for every mineral from the deposits using cutting-edge technology. Depending upon the physical properties, especially its specific gravity, electrical conductivity, and magnetic susceptibility, the individual minerals like ilmenite, rutile, zircon, sillimanite, garnet, and rare earth mineral get separated from each other in our mineral separation plant. Our product range varies from minerals, rare earth compounds, to chemicals. Ilmenite is the primary ore of titanium. Ilmenite, extracted at IREL, is used in major applications like in critical components of spacecrafts, aviation industry, healthcare industry, pigment industry, and various high-performance alloys. Rutile extracted has applications in the electrodes industries and in the production of titanium pigment. Zircon, a light brown mineral, is mainly consumed as an opacifier in the decorative ceramics industry. It has a very wide variety of uses in refractories, foundry casting, advanced ceramics, and a growing array of specialty applications as zirconia and zirconium chemicals. Its sponge and alloys, including in nuclear fuel rods, catalytic fuel converters, and in water and air purification systems. Sillimanite is extensively used in furnaces of metallurgical and glass manufacturing industry due to its high refractoriness, very low coefficient of thermal expansion, great resistance to thermal shock, abrasion, and slag corrosion. Garnet, which is rose red to pink in color, is a good abrasive, and its uses include sandblasting, water jet cutting, and also as water filtration media. The yellowish light green rare earth mineral is used to produce 17 high pure individual rare earth elements with applications in almost all major industries. We also produce chemicals including rare earth chloride, trisodium phosphate, and thorium nitrate used for various industrial applications. We ensure that our products meet the highest global quality standards. We use state-of-the-art technology for mineral separation and extraction of rare earths, compounds, and chemicals. We have implemented integrated management system in our business processes. We have invested in fully equipped quality control laboratories and R&D centers for achieving the best and to stay ahead in the race around the world. Our rare earth extraction plant, REEP, at Odisha has an overall production capacity of about 11,000 tons of rare earth chloride and associated products. Our high-pure rare earths plant at RED, Aluva, is specialized to produce rare earths oxide and carbonates. Restoration of area after mineral collection is considered prime responsibility of the company, and we ensure that the area is refilled, afforestation is done, used for rehabilitation and community development. Whereas in some areas we work along with the local fishermen community by desilting of mineral-rich sand from the fishing harbors that helps ease the navigation of fishing boats. We are benevolent, and we believe it is our duty to give back to the society with a focus on community health care, rural infrastructure development, skill training, education, and community development.
Indian Rare Earths Limited is a Government of India undertaking under Department of Atomic Energy. It is having the mandate of extracting these sand minerals from the beaches as well as from the inland deposits. These minerals consist of titanium-bearing minerals, zirconium-bearing minerals, as well as rare earth-bearing minerals. Each of these minerals after extraction are finding niche application in varied area. IREL is a multi-product, multi-unit public sector. The plant is located across the coastal stretch of the country. The core philosophy of the company is not only to extract the minerals but as well provide improvement in the quality of life of the people in the vicinity of our mining area. Besides, public sector has a global vision and mission. As per that, not only we would like to be leading supplier of the minerals, as well we should be contributing a lot for supplying strategic material to Department of Atomic Energy. We have made a strategic management plan 2025. As per that, we would be expanding horizontally, as well we would be expanding vertically in the area with whichever element is befitting to our mandate. Besides, R&D is a very important aspect in the rare earth business. We are being continuing with that, and debottlenecking of various issues in and around is another important objective.
The minerals, rare earth compounds, and the chemicals we produced have a presence in everyone's everyday life, right from the toothpaste you use to the satellites that connects you to the world. IREL, Unleashing Values.
Sir, please, on your camera, please.
Check. Once again, warm good afternoon and welcome back after the lunch session, and we'll be having session number 6 that would be based on rare earth applications. And the topic, let me just tell you that it is rare earth based electronic and magnetic materials for space applications. Shall we start? And let me invite this session's first speaker, Dr. H. Sri Mulanandan. He is the head GM in Steve area VSSC. As I have told you, he is a senior scientist in Vikram Sarabhai Space Center. And earlier at ISRO, he initially worked in REPM project for ISRO systems like AOCS thruster, inertial navigation guidance and control, etc. He pioneered electronic ceramics development and hybrid microwave processing of ceramics in ISRO. Currently, he is heading glass, electronic and magnetic materials development. Let me tell you that he has patents and international journals added to his credibility, and also invited talks are 7 numbers. And I would like to also add something really very interesting, which personally is very inspiring also. He is trained in Veena playing and South Indian classical music, and humble follower of Vedanta. This is really very interesting because somehow your passion keeps you burning inside, and definitely focus. Sir, all the best to you for your session, but I want to welcome you with a gesture. We are having a virtual slide welcome.
Thank you, madam.
And now I would like to request our Honorable CMD sir to virtually present a wonderful bouquet as a warm welcome gesture.
Thank you.
Over to you, Dr. H. Sri Mulanandan, sir. Thank you.
Good afternoon. Namaste. Thank you, madam. Thank you, dignitaries. Hope I am audible.
Yes, sir.
My voice is clear also, I hope.
Yes, sir.
Thank you. Thank you for the response. And you can see the background is my own house terrace, where you can see the lot of coconut trees. Now it is a celebration, Onam celebration time here in Trivandrum. Okay, let me start. I will stop my video and I will start the sharing of the presentation. I'm from the Glass and Electronic Materials division, as Madam has introduced. We are dealing with the development of glass and glass ceramics, electronic and magnetic materials for various space applications. We had a humble beginning on rare earth magnets with the great collaboration of GM model, which also I will be sharing here. And in electronic materials also we have going ahead with a few things. And in glass and glass something, of course, rare earth contribution is so far we have not identified to a great extent.
One request to you, sir. Please.
Yeah, I have put on the full screen.
Yeah. Thank you very much now. Thank you.
Is it okay now?
Yeah. Yes, sir. It's visible, sir.
Okay.
Thank you.
Fine. With this introduction, I first wish great success story of IREL to continue for many more centuries to come. And my greetings on the occasion of Platinum Jubilee of IRE. Is a great effort, and they have been contributing to the indigenization effort and self-reliance of our high quality raw materials. It is a word that is coming from my heart. Yes, I would like to acknowledge, like a squirrel, we have also done very small things humbly in a way, and I would like to acknowledge for the great achievements to our director, associate directors, and group director, and many people in the form of collaborations like GMRL, NIST, and our own people like Ahmedabad, SAC Center, LPSC for testing various things and all. And last but not the least, the scientists, engineers, and technical staff of my division, and they have been the integral part of these activities. And whatever I am presenting today is a great effort that has come out from their participation. Okay, as I was a little bit inclined to the Vedanta, I'm not going to bore you after the lunch thing. But if you look at the mind is the Chit Shakti, that is the basis for all the things in this world. If it is introverted, looking inside and trying to find out the connection between oneself, the world, and existence by introspection and contemplation, that is what Vivekananda used to put as microcosm, that leads to philosophy and spirituality. On the other side, if it is extroverted, if it is looking outside, observing and thinking about what is around us, why things happen, how that happening, and what is cause of it, what are the things around us, and when this will happen again, when this has happened before, all these things, when we are trying to find out the connectivity in the outside world, it is nothing but we are looking at the macrocosm, which is the worldly wisdom. And that has led to what is called science, which started from the natural philosophy. Of course, the observation of natural phenomena was the beginning of everything. You would like to agree also, I feel. And these questions on the natural phenomena and the inquisitiveness to know the underlying things led to the growth of science, wherein the understanding of the phenomenon, explaining them, and identifying connectivity between various phenomena, various happening, and various things. And then the formulating rules to understand them much more quantitatively and exactly. All this led to the growth of science, and science purview is also like that. From science sprung up the technology, which started predicting and restricting the forces or protecting mankind and other things, the pets, everything from the natural forces, and manipulation of minerals, manipulation of resources, manipulation of various things to create new and new things, to leading to the lifestyle what we are today, dictating the economy, generating as well as satisfying the needs. And the dotted and finally, I would like sometimes to put a mark between these two, the greed and the need. Now today the world, I would put, is all controlled by business. Whether it has come from the natural phenomena, natural philosophy, but the business is the one which is leading, dictating everything. So there, any program anywhere in the country has to be with a motive of doing good business. From that, if you look into the topic of my discussion, basically on the material science and technology, the essence is that nothing but it can be new materials development, maybe perfecting materials for specific applications, things like that. These are all based on the investigation of properties of materials at various levels, be it in the bulk level, microscopic, crystal, molecular, atomic level. All these are founded on the physics and chemistry of materials, wherein process innovations come, fabrication innovations come. There will be other protection for the materials and other things from the wear, oxidation, corrosion, aging. All those things all come under the purview of material science and technology. With a left side pillar, what is the extraction? From only it can start from minerals and refining to find good raw materials. And I have rounded that because here is where the contribution of IRA is much significant, and not much players are there in the country. But if you look at the developed countries, this part is also far developed like the other research parts. Coming to the space systems, basically, there are a few special aspects compared to the commercial or the what we call the terrestrial aspects of uses. They are all multidisciplinary and obviously complex. And if you start from the first principle designing of certain things and build the systems, it may take many years, and that will add to the cost. And ISRO has been always striking a compromise between modifying a few designs from abroad and using it at the same time in certain conditions designing from the first principles. And you all know manipulation of things in orbit is almost impossible. Only a few, one or two atoms we have been doing in space shuttles or in the space stations. There are uncertainties in design and development that in this space system that can really lead to great delay in realization. And sometimes in that process, we may land up with over design, which may not become competitive, which is, as I pointed out, a matter for business. And all this, when it goes to cost, obviously the business part comes in, which is now in front of ISRO in another way. The systems benefit only when the critical components that become greatly reliable. It is all know, you know, any space experiment can go to a failure, even nut and bolt, or even a weld joint failing, and all you have read widely in all stories around. The assigned parameters, they are usually based on the worst case expected things. That means the design parameters often people fix at 50% of the efficiency or sometimes even below that, so that you never encounter problems during the actual mission or the flight. And in other words, for this redundancy in critical systems is also being called for. And that all adds up to the weight of the system, wherein the payload share will be reduced. So these are all the special things, and above all space mission, any mission is an experiment. So you can only statistically argue before the mission. After the mission only you will find out new aspects coming up. When we compare, when I say space system, obviously you all will be familiar with the launch vehicle part and the spacecraft part. When we compare the system, the launch vehicle parts are, of course, very big, huge in size, and the satellite part, the spacecraft parts are obviously very small, sometimes even tiny. Just for example, if you look at the nose cone there shown of the thruster, which may be, of course, the size of a person, whereas the thruster in the satellite will be just to fit into your palm. And there will be differences between the lifetime, the shelf life, the functional deviations permitted, the temperature variations, the vibration and shock requirements for the subsystems, things like that. These all will vary. And there are specific requirements for structural and functional components. Today, I just with this overview, I will be trying to put in our recent developments and our previous rare earth-based permanent manganese developments for the space missions. And these rare earth oxides are indispensable in many electronic and magnetic devices that are used in space systems. And of course, for the permanent manganese, all of you know the rare earth metals of high purity. So 3 cases I have listed, and major point is that the components and the devices are very, very small, and the quantity in terms of the raw materials needed and all very small. And the components themselves, if you look at the quantity, they are not really attractive for conventional Indian industries to invest. That is the one reason which I have found that for our lagging behind, Indian industry is lagging behind in functional materials progress. Most of the inventions and innovations remain in the lab with a lot of effort to be put there into further taking up into the industry. But on the contrary, abroad, it is the reverse. And the imported subsystems or devices, and that tend to be expensive, not because of the technologies are bad at all, but often what you are forced to buy a minimum order quantity, things like that, and you cannot test and screen all the components. All these lead to a lot of revenue going on to the imported components, and many of the functional materials, either they are imported as such or in form of subsystems. Okay, this is just, I'm going into the rare earth permanent magnet side. You know, You might have definitely heard from Dr. Manivel Raja, Dr. Gopalan, and next to Dr. Chandrasekharan, and from Mark scientists. The right hand part. Hope my cursor is visible. Okay, the right hand part with the maximum coercivity for the rare earth based permanent magnets. That is the one really attractive for the space missions. If you look into the rare earth permanent magnets, I should really thank Dr. Chandrasekharan, Dr. Gopalan, and the DMRL team for taking me deep into these subjects and with hands shaking for many scientific facts revealing to me. These rare earth permanent magnets, you can see the second quadrant or the demagnetization curves for various magnets compared. The greatest charm that I would put in forth of this forum is the energy saving because of the high BH product that either samarium cobalt SMCO5 or the to second generation samarium 217 type or the neodymium and boron type. That is going to give you in terms of the energy saving, the weight saving, and the linear demagnetization curve. In Alnico based magnets, there will be a small curvature coming onto the down, and so the nonlinearity plays a vital part in creating a lot of hiccup for the designers. But when it becomes very straight, designers are very comfortable. And these two are the major reasons for selecting rare permanent magnets in lieu of many of the soft magnets wherein the power can be detached and the permanent magnets can be used. If you look at the space systems employing rare earth permanent magnets, basically they will be based on Coulomb's force or Lorentz force. A lot of applications are there, chiefly in the navigation, guidance, and control. If all the satellites of INSAT and IRS class, the launch vehicles of GSLV, PSLV, things like that, as Madam had put it in the introduction, the attitude, orbital control systems, thruster latch valves, xenon plasma thruster, servo accelerometers, brushless DC motor, TWT amplifiers, magnetic bearings, things like this continuing, and thousands and thousands of components are being either imported and some are being replaced with indigenous. A few examples I have listed here. The left side one is an AOCS thruster latch valve that is used for the attitude and orbital control in satellites. It will be a maximum 1 Newton to 2 Newton thruster only. It will be controlling the liquid flow as well as the oxidizer flow. And the thruster will fire often maybe for a few seconds or maybe 1 second or short periods of time, wherein the drift due to the gravity changes posed by the sun and moon acting on the satellite's orientation will be rectified by these tiny rockets fitted on 3 axes of satellites. You can see these like bush-like projections on the surface of satellites. The other one is a pneumatic latch valve, wherein also the magnets are used. With the permanent magnets, they act as a latching one, where the close or open position they hold, wherein the flow of liquid hydrogen or liquid oxygen in the cryo stage, they are controlled by the helium pressure. So the helium flow is controlled by the latching action of these magnets. These are all required per latch valve around 6 numbers or 5 numbers. But the latch valves are running in 16 to 20 or even 30 to 40 in a satellite. So all going to hundreds of numbers. But still the magnet size, if you look at, there are hardly 11 mm by 3 mm cross section. Very small. And another one is a magnetic bearing reaction wheel, which is used for the station keeping of satellites. And you know, the magnetic bearings work with frictionless. These are some examples. And I'm thankful to DMRL. Of course, a number of components, almost 8,000 to 10,000 components we have realized on samarium cobalt, SMCO5 alone. And some 2 CO17 based thing is now we have projected the requirement. Some DMRL is coming up with some alternative of I think there is some alpha BR values which we have to agree with. So those dialogues are on. So hope we will be able to integrate that also into the systems after the functional tests, once the functional tests are over. These are the properties that we could achieve with the DMRL magnets. And the magnets properties, basically, they will be tested on the test pieces by the BH test loop and will be given to us by the DMRL. Later on, the functional test or the device level test we will carry out. Starting from the raw material, there are a lot of qualifications involved as far as the samarium cobalt magnet was produced are concerned. The raw material processed by DMRL and the product was in the form of a block. wherein their magnetization direction is really marked. And ISRO, according to the requirement of the component sizes as and when they arise, we used to go for CNC wire cut machining, keeping the magnetic alignment intact, and the components are then taken for magnetization. Then device level testing and subsystem level testings are carried out at the system level agencies. This is a basic processor. The left hand chart is from the TM model, and the right hand side is from the ISRO side. And the components themselves are afterwards, there is no scope for the component level testing. So the peak axial field or the surface flux density was introduced as the verification point for each and every component. 100% components are inspected either using transfers or axial probes. And plus or minus 5% was the allowable tolerance to the surface flux density, which were communicated to the user agencies. And these were measured using Gauss speed. These are very small equipment. Afterwards, the system level test consists of thermal shock, rapid cycling in high temperature to low temperature in thermovacuum chambers with salt water spraying, things like that. And in certain cases, 5 cycles were accepted in the ranges of maybe minus 20 to 400. And in certain cases, it went up to even minus 200, where the cryogenic application or the satellite outside application during the eclipse period, the satellite outside will meet around 1000 minus 150 degrees Celsius. So functional tests like this are carried out, and the subsystems as such undergo vibration and mechanical shock tests, because after the assembly, if any change in the magnet assembly happens and a small air gap introduced to the assembly of magnet, that will reduce the flux input, and that can cause real problems. And accelerated tests are conducted for 5,000 cycles of operation in many cases, because looking into 10 to 15 years of lifetime in the orbit, these tests are essential. Another one which I would like to bring out is the recent developments in the magnetic side is the soft ferrite, which are widely used in circulators and microwave circuits. I don't want to give the introduction very bit. We are all familiar with the magnetic moment happening in the atomic magnetic moment, the magnetic materials, which leads to a ferromagnetic resonance under the application of a strong magnetic field, because there is a Lamer precision coming in, and there is an incoming EM wave will have an absorption at this natural resonance frequency dictated, and that leads to permeability differences below the resonance frequency and above the resonance frequency. And if such a material is made and a magnetic field is applied and the microwave or the RF signal is passed, there encounters two different propagation velocities along two perpendicular directions, leading to Faraday rotation. And this forms the basis for switching of microwaves from one arm to another arm. Like this device is called a circulator. So you have one arm where the incoming wave is there. You can direct the incoming wave to the left or the right by employing such ferrites, and this is widely used. A good fraction is still imported, but we have now indigenized. This is the basic of yttrium iron garnet one, which we have indigenized. A basic processing chart is given here. These are tiny components. You must remember that the numbers are only in the form of maximum of hundreds only required for a particular satellite, and together it will be hardly 500 to 600 numbers a year. Okay, these are the basic scientific facts behind the processing. This is around 20 mm in dia. It is cut into the form of a ring, and these are the basic characteristics. It is basically what we have done here is it's a well established material, but we understood that there is a requirement of a perovskite phase in a less than 5% fraction, and that is introduced here deliberately to get very good dielectric properties also. Otherwise, we will be dominating more on the magnetic part, and the dielectric part becomes a little bit less. Since the microwave propagation is involved here, a loss factor is to be reduced. That is only possible by introducing more dielectric component into it. These are the properties, the microstructure you can see. And this is the test, the device level. The bottom one on the left side is a coaxial test setup. You can see the Y junction at top, left, and middle. The switching action takes place between the left and the right arms, and this is working with only a maximum of 1 to 10 watt. But the top figure is showing the one is employing about 1 to 2 kilowatt, wherein waveguides are used. This is typically in the S band. I think the frequency was around 2 to 3 gigahertz, and the whole mechanism was working fine. If the ferrite is not working, you will not get any such dip, and the dip what we are getting, the insertion loss or the return loss, what the application engineers say is at par or slightly more than the imported that being used, and we are now trying to productionize it. If not able to productionize, we will be able to realize this in-house or through some pilot plant setup. I will be leading from here to the dielectric side, the electronic materials, which is another part of thing. I hope I have some 15 minutes or 10 minutes. Sir, am I audible? Hello?
Continue, sir.
Am I audible, sir?
Yes, sir. Yes, sir. You are audible, sir. You should continue, sir.
Yeah, sorry. Okay, just an introduction about the electronic materials, what we are working for the communication purpose. Basically, the electric fields impart polarizations in the insulators. When we look into the microwave applications in the satellites or in the launch vehicles or in the ground systems, the ionic polarization that is happening in the crystals, which is the separation of positive and negative ion centers, and the one which is between the electron cloud and the nucleus, which is the electronic polarization, which are the contributing factors. And this leads to a very, very, very low loss in the system when the material encountering electromagnetic wave propagation. Chiefly, the materials required for such applications are banded here with yellow, which require typically very good dielectric constant. It can range even from 2 to 1000. The basic problem is that the requirement of the temperature coefficient of the drift of the dielectric constant has to be very nearly equal to zero, very near to zero. Ideally, zero is not possible, but we practically within 10 to 15 ppm per degree Celsius is solicited, along with good loss factor, which is running into 10 to the power of -3 or -4. In that category, one material is DK65. We are coined this one coming under the orthogonal tungsten bronze category. This is basically a barium samarium titanate material, which we have tailor-made for our application in our NAVIC receivers. Here also we have made this by the solid state route, and the components are machined, and there is a screen printing for the patch. Metallization is given by silver palladium paste metallization. These are the basic properties. You can see here that temperature coefficient of the frequency is less than 5 ppm. It can either go to the positive side, increase, or left side, decrease. And this is basically a multi-phase crystal system with the dominating phase the orthogonal tungsten bronze, with minor phases of barium titanate and the rare earth titanate incorporated into it. This is the IRNS constellation. You can see 7 satellites already put into the orbit in the near to the 36,000 kilometers thing. 7 satellites will be scanning the Indian region, and to receive the signals and transmit back to, we have the NAVIC receivers coming into. The left side top is a typical NAVIC receiver. This is a ceramic patch antenna. The cursor is visible. Hope you can see it. And the entire circuitry is like this. And this particular one is an imported one, which was further we had a simulation to match the frequency of the, I think, our RF division simulated, and they gave us the dielectric constant, the loss factor back to us. We realized the substrate, and then the silver palladium paste was given on that, and the connector is fitted, and this now acts like a patch antenna at a frequency of about 1.57. This is the antenna test conductor. The red curve you can see is belonging to the imported receiver, which was taken out of the, imported patch antenna taken out of the receiver. And the blue curve, which you can see, is belonging to the indigenous one. And I would like to say that the Indian raw materials, thanks to IRA, has really kept us competitive with the imported one, which is now costing around 250 to 300 rupees a piece. And we are lining up now with around 450 rupees. Once we productionize the industry, we are very much sure that we will be able to reduce this further, and the performance is also better than what we have seen. And this particular material now, the technology, everything is now available for technology transfer. Indian industries can approach us. We have patent also put on this material. And next one is another neodymium aluminate, rare earth aluminate, samarium aluminate, and calcium titanate based mixed perovskite system, which is an indigenization of imported one. So far, we have not used it in our space systems, but based on the data sheet, we have developed this one. This is also oxidic material with orthorhombic crystal structure, but this is purely a single phase orthorhombic one without any secondary phase. Here you can see that this difference between the previous one and here one is, earlier one was the dielectric constant, of course, this is slightly lower, 20 dielectric constant less than the other one, but the quality factor is extremely high, almost 3 to 4 times than the previous one. Still the temperature coefficient is maintained far less. And this is the flexograph of the material. And using this material, we passed on the information to our SAC, Ahmedabad team. They have designed a 4-pole filter that working in 2.04 gigahertz. The simulation was like this, and there's a response. Don't worry, this scale is from 2 to 2.08, where this is from 1.95 to 2.15. The marker percent is at 2.0 exactly at the center. And the insertion loss, those working with microwave systems will appreciate this one is only 0.3 GB, and which is much less compared to systems. And this is the filter, which is much smaller than the waveguide filter, which would have been almost 6 to 7 times bigger. This is the piece, single piece used in it. For there are 4 pieces like this. This contains around 40% of neodymium, and we are trying to get IRE neodymium for this. We used imported neodymium. IRE was at that time out of stock for 99.9% because the raw materials are extremely pure in all the cases, be it in the rare earth permanent magnet or in our electronic materials. The raw material purity is very much important. So this one soon we will be getting from IRE, and we hope to get this one also. We are now trying for the Gaganyaan, as you know. We are heading for a one where the crew will fly in the space and come back. And there is a service module which is on the bottom and a crew module at the top. This is the crew module alone, which will be orbiting and which will be able to conduct experiments, and the communication with the crew module and the service module is in S-band. Basically, this filter, such 3-4 filters may be required minimum for one particular crew module. And this is now communicated to our Ahmedabad team. This is the thermal cycling result. You can see between minus 15 degrees Celsius and 75 degrees Celsius, the drift is only 250 kilohertz, which is approximately 3 ppm only, as what we have envisaged in the this technology also we are now putting up for the industries to buy, and initially we can build ourselves in the lab itself for the meeting the mission requirements, which is around 50 to 100. I will be summarizing. I think I am correct, well within the time, I hope. Okay. The one which, these are only a gist of the functional materials altogether used in satellites only. This may be maximum 1 to 2% of what is being used. These functional materials, there is still wide import, maybe around 50% is import, as I understand. This is either in the form of materials or devices, or even subsystems themselves are imported, and that is different from the story pertaining to the structural materials, wherein you are aware of the titanium-based things which we have indigenized, the maraging steel, whatever thing. Almost 70% of the structural side is indigenous. The indigenous on the other side is being slower. I mean, in the electronic, magnetic, optical side is maybe that it is smaller in size and number, and that is not really attractive for the Indian industries to invest. And it requires interdisciplinary skills and infrastructure in the Indian industries to really take up such technologies, and which is not that much attractive. Now only a few industries have started, and interacting with us. We hope it will come in the near future. The greatest challenge that I find myself as a material technologist is transforming the material knowledge to a material, to a device or a subsystem level and test. Without that, the application engineers may not gain any confidence on the material what is developed. This is one major difference between structural and functional. That is why I really put the interdisciplinary skills in the industry also is important for really leaping forward in this one if you want really self-reliance in the country. This self-reliance for the such satellite components is possible even with today's capability onto the component level. As I given you a few examples, this is only one or two. We have so many examples across the country, many labs, not only in ISRO, many labs have developed many components. ISRO being a multidisciplinary center, we are very much confident by joining hands with various organizations across the country and having collaborations to indigenous and achieve self-reliance existing. Finally, one or 2 points, this fine quality raw materials, these all require, as I put you, even in the samarium cobalt magnets, there were rare earth metals imported, even today maybe they are, but now there is a good endeavor coming up from the BARC, another thing I heard, it will be very much beneficial to the country in achieving the self-reliance. Definitely IRE can really contribute to this one because for electronic and functional materials, we may require from the lanthanum to the terbium entire periodic table, but all these things for the entire country's requirement will be only in kgs per annum. But the cost, I mind you, will be more than the normal quality what is produced in hundreds of kgs. And I thank really IRE for being a nodal agency in such things. May God bless all of you to further strut the heights. Best wishes again. Thank you for sharing. What I have shared is a small droplet. It is much more is to be there.
Check. Sir, thank you so much. Would like to present a virtual gesture note. Can we go for the same? Thank you, and of course would like to request our Honorable CMD to present virtually a memento for this wonderful session taken by Dr. H. Srimulanandan.
Srimulanathan.
Srimulanandan.
Thank you, madam. Thank you.
Honored to have you, sir. Thank you so much for your time and presence. I request you to please be there. We are having some more speakers and valuable sessions ahead. So, moving forward, we are having another very eminent speaker in his own forte. The topic would be rare earth for specialty applications, and it would be taken by Dr. V. Chandrasekharan, former head Magnets Group, DMRL. We welcome you, sir. Dr. V. Chandrasekharan. There is a small welcome note from our end in the form of a bouquet. Ladies and gentlemen, I would like to mention that Dr. V. Chandrasekharan obtained his PhD degree in physics from Annamalai University, Tamil Nadu, and joined DMRL Hyderabad in March 1976. He superannuated from DMRL in October 2010. Right from beginning, he was associated with R&D activities in the field of magnetic materials and led many R&D projects in magnetic materials as head Advanced Magnetic Group of DMRL. His major contributions were towards the development of specialty SMCO 5 magnetic components for defense, space, and atomic energy applications. For his significant contributions in samarium cobalt magnets, he was recognized with the RDO Technology Group Award 2008, IIM National Metallurgist Day Award 1998, Vasmik Industrial Research Award 1991, and MRSI Medal 1990. He is currently engaged as technical consultant at ARCI Hyderabad. Can I welcome Dr. V. Chandrasekaran with a huge round of applause from everyone, whoever have joined us virtually and physically to this session. This is a recorded version, so you have to listen to the points carefully. Thank you so much, sir.
Very good morning. At the outset, I express my sincere thanks to the organizers for giving me this opportunity. My presentation will be on the development of rare earth permanent magnets for specialty applications. It is based on the experiences what we have gained during our stay in DMRL, and the specialty magnetic components will also be discussed in this. I sincerely convey my acknowledgements to the director DMRL and the team members of the Advanced Magnetics Group of the laboratory. This slide is very familiar to everyone, where the variety of application areas of rare earths are presented. Now you could see that the magnets occupy the major share. This is because the addition of rare earths provide a quantum jump in the magnetic properties, leading to high performance magnets. Now, permanent magnet family can be categorized into two parts. One is the oxide magnets, which are known as ferrite magnets, where we have got barium and strontium ferrites. We have got metal magnets, that is alnico, rare earth magnets, and other magnets like platinum cobalt, iron chromium cobalt, manganese aluminum carbon, etc. Now, and in these cases, bonded magnets are also available. Now, the rare earth magnets can be classified into once again three parts: samarium and samarium based, neodymium based, and samarium based has got samarium cobalt 15 and 217 type, SMFEN, which is the latest addition, and NdFeB magnet, which is known to us. Now, when we think about the permanent magnet matrix, like any other magnetic material, the permanent magnets are also characterized by the hysteresis loop, where we plot the magnetic induction versus the applied magnetic field. The two hysteresis loops are normal hysteresis loop and induction. Induction is plotted against the magnetizing field, the normal hysteresis loop and the intrinsic hysteresis loop. Now, with respect to permanent magnet, we are more interested towards second quadrant characteristics. The second quadrant of the hysteresis loop of a rare earth magnet is given in this picture, where we have got the remanence, which is a measure of the field strength, and the two coercivities, normal coercivity and intrinsic coercivity, they are the measure of resistance to demagnetization. Now, we have got another property called energy product, which is a combination of the operative flux density and the demagnetizing field. Now, the BH max is a figure of merit of the given magnet. Rare earth permanent magnets are capable of exhibiting high BR, high coercivity, and high energy product. Now, the development of improving the energy product has resulted in the development of variety of magnets during the last 100 years. So, from steel magnets of 1 energy product, which is 1 MGOE, to NdFeB magnet of 50 energy product are given here. We could see that samarium cobalt magnets, which are introduced during 1970s, they are capable of now giving an energy product ranging from 20 to 30, whereas NdFeB magnets are capable of giving 30 to 50. Now, what is the advantage of this particular high energy product? That is directly explicitly revealed in this picture, where we have understood that 20 cc of ferrite magnet can be replaced by less than 0.5 cc of rare earth magnet. So that means this results in what is known as smaller and efficient devices with rare earth magnets. Now, this particular slide gives you the applications of rare earth magnets, right from consumer electronics to the high-end military applications. I don't want to go into the details of this particular thing, which is very well self-explanatory. Now, when we think about the combination of magnetic properties, rare earth magnets exhibit excellent combination of magnetic properties. The 4 magnets are given in this particular table, where the first one is saturation magnetization. That is the intrinsic property. They are called primary magnetic properties. That is nothing but atomic magnetic moment density. It should be remembered that the fundamental magnetic properties have atomic origin. Now, with respect to saturation magnetization, NDFE magnets are topping. Now, when you think about the Curie temperature, which is the temperature beyond which the ferromagnetism is lost, now that is based on the exchange interaction between the magnetic moments. That is very high for samarium cobalt magnets given here. Now, the other one is anisotropy energy, which is the spin orbit coupling. That is available as a large quantity for all the 4 types of magnets, and samarium cobalt 1,5 has got the highest anisotropy energy. Now, the intrinsic properties are due to compound chemistry and crystal structure. Now we could see why rare earth magnet is really increasing the primary magnetic properties. That is because of the strong electrostatic interaction between asymmetrical 4 shells leading to high magnetophysical anisotropy. That is nothing but responsible for high coercivity. In addition to the primary magnetic property, the engineering properties are controlled by, the second quantum characteristics are controlled by the coercivity. The coercivity can be understood by the coercivity mechanism of the rare earth magnets. There are 2 types of coercivity mechanism. One is the nucleation type and another one is domain 1 pinning type. This could be understood from the first quadrant characteristics of the hysteresis group. You could see that in some SMCO5 and NDFEB, the magnetization rises very high, very fast with the magnetic field. Whereas in 217 type, it rises slowly. This is because the domain walls are getting pinned during the magnetization itself. Now, the magnetizing field is, the magnitude of the magnetizing field is responsible for the second quadrant characteristics. Now, if we have very high magnetic field, then the second quadrant will be the second quadrant characteristics are also very high. If low fields are applied, then you will have what is called partial magnetization, resulting in partial second quadrant. So now we require very high fields for magnetization, for charging these magnets. For SMCO5, we require SMCO5 in NDFEB, that is the nucleation type, we have 25 to 30 kilowatt field is required. Whereas for SM2CO17, 45 kilowatt field is required. This particular equation gives you the relationship between the primary properties and the microstructural parameters. The microstructural parameters, why they are playing a role. We could understand from this picture, each grain behaves like an independent entity. When we apply a magnetic field to saturate them, the grain is saturated. When we apply a field in the negative direction, the grain has to get demagnetized. The reverse domains are nucleated at the defect points and they are getting pinned at the grain boundaries as well as at the defects. So the microstructure plays a role in controlling the coercivity. So 2K, MS, they are all microstructure primary properties, whereas alpha is a microstructure parameter, N effective is the demagnetization factor of each grain. Thus, the coercivity depends on the final microstructure of the magnet. Now, with respect to DM model development, we adopt powder metallurgical processing. That is, we take pure elements in this particular flowchart gives how the samarium cobalt magnets have been developed and similar to other types of things. They are applicable to other magnets also. So we take pure samarium and pure cobalt, pure samarium, pure cobalt, and it is melted in induction melting furnace in vacuum or inert atmosphere, and the ingot is uptime. The ingot is very brittle, and the brittle ingot is crushed and ball milled in an inert atmosphere like toluene, and then the toluene is drained and the wet powder is dried in a vacuum dryer, then compacted in a magnetic field press. That is, the dry powder is oriented first in an intense magnetic field and then compacted. Now there are 2 types of compactions. One is the axial compaction and transverse compaction. Now where the pressure axis and the field axis are parallel, field axis and pressure axis are transverse. Both the facilities are available in DMR. Once the compaction, orientation and pressing is over, the green compacts are textured. The textured compacts are heat treated or thermally processed in high vacuum, high temperature furnaces with the gas quenching facility. Now, the thermal cycle I will explain in my next slide. Now, the compacts are, after the sintering is over, they are ground to parallel surfaces and characterized with the hysteresis loop recorder or vibrating sample magnetometer. Now, the components are machined to the required dimensions and pulse magnetized to the required saturation level, thermally stabilized and given to the user. So we could understand that specialized facilities are required for the REPM technology. Now this gives you the thermal processing schedule of all the three types of materials. Okay? All the rare earth magnets, the thermal process consists of only simple steps. From room temperature, go to the sintering temperature, then sinter it for a sufficient amount of time at sufficient temperature, and then control cool it to the annealing temperature, and then quench it. The sintering temperature, the annealing temperature, the cooling rate, they are all very critical. Now in the case of 217, it is a two-stage sintering, where we sinter and solution treat it, then quench it, then go to the annealing temperature, then cool it, and then quench it. Now in the case of NDFEB, the similar technique is adopted. Similar process steps are adopted. Now I would like to give an explanation from the phase diagram how the thermal cycle is scheduled. Now for example, SMCO5, SMCO phase diagram in this one, in the interested region, exhibits the homogeneity range at a high temperature. This is how you are able to see the homogeneity range. So your melting is done at the liquidus temperature, then your sintering has to be done at the homogeneity range. Now we know very well that samarium has got high reactivity as well as high vaporization losses. So one has to take excess samarium at the raw material charge preparation stage itself. Now here the samarium cobalt phase is enflanked by two phases, SM2CO7 and SM2CO17. SM2CO7 is a high coercive phase which can be accepted, whereas SM2CO17 is a low coercive phase which should be avoided. So what we do is we take excess samarium so that we are operating in this range. Now this can be understood from these two microstructures, where in the ash cast alloy we have got only two phases, 2,7 and the matrix 1,5. Now even after sintering, the two phases only are retained. Now the annealing is very important, and during the annealing the coercivity improves in a manifold way and you are able to get very high coercivity. We could see from the phase diagram that below 800 degree, SMCO5 phase is not stable. It decomposes tectitally into 27 and 217. So that is seen from this curve, where a 760 degree annealing is decreasing the coercivity from 20 kiloAST to 3 kiloAST. That means 27, all your annealing treatment or heat treatment must be above 800 degrees centigrade. So this gives you the final magnetic property. Now I would like to say that the DMRL process has standardized for 17 to 18 MGOE, that is million conservation. When you think about the actual technology, we go into what is called our appropriate tools. Now here are the variety of non-magnetic high strength dies for the various shapes. This is for cylindrical magnets, ring magnets, block magnets, and from the block magnets, sector magnet circuits. So all these materials are limonic alloys or tungsten non-magnetic high strength. So why we have to select a high cavity non-magnetic dies are? It is because of the non-magnetic nature of the die body will give you high cavity field and give you better orientation of the powder. Now, when you think about the components are to be characterized in a different manner, because your hysteresis loop properties are applicable to material property. When you think about the component which is integrated in a device circuit, the operating energy product is utilized. So The Hall probe gauge meter and specially designed jigs are used to qualify the components. Here, we adopt three techniques. One is the surface flux density measurement on the surface at a particular point of the component with the help of Hall probes and digital Hall probe gauge meter. Now we create a magnetic circuit and then we measure the, this is the magnetic component. We create a magnetic circuit in the iron, pure iron, and then we create an air gap, fixed air gap, and the flux density is measured in the fixed air gap. For ring magnets, which are axially oriented, we measure the peak axial field at the center of at the central axis. For that, an aluminum jig which has been fabricated at a DR model is shown here. Now I would like to give the specialty components which have been developed at DR model. These are the axial ring magnets for microwave tube development R&D center of a DRDO lab. This is for traveling wave tube, which is a microwave amplifier. So the axial ring magnets with the diameter ranging from 8 millimeter to around 90 millimeter have been developed. Hundreds of such magnets have been developed and given to MTRDC for the development of TWT, which is a traveling wave tube. Each magnet has to be stabilized at 200 to 250 degrees centigrade for 4 hours, and the peak axial field has to be measured, and it has to be within a band of flux density. Now these magnets have been given to MTRDC for that. Now this is yet another important development which has been done at DMRL. Now this is a radial ring magnet for inertial sensors. Now here, this is the ring magnet. The ring magnet consists of 12 sectors. The size is around 20 mm OD, 15 mm ID, and 4 mm thick. It's a very thin magnet. So 12 sectors means it's a very, very tiny sector. But if you want a radial ring magnet directly from the compaction level, then you require a radial field, which is not available. So what we adopted is a block technology where we make the block, and from the block, the sectors are fabricated by wire cut, and then the sectors with the proper polarity, and the sectors are glued inside a titanium ferrule, and the radial ring magnet is machined to the required dimension. They are magnetized in a radial pulse magnetizer, which is available at HAL Corva, and the air gap flux density is to be measured for 360-degree distribution of the field. So 12 sectors will give a sinusoidal 12 crest and trough radial field, and that has to be within a very stringent band, and it has been developed, and the field pattern is acceptable. So the first time achievement of this radial ring magnet has been realized. Now the challenges are development of a sector, tiny sector, according to the polarity, gluing them inside the ferrule, and then radially magnetize them, and 360-degree field measurement. Now this has been realized. Now when you go to the yet another application, they are for ESSC, that is space programs. Now variety of shapes have been developed for prototypes have been developed, and this particular thing is a very important one, where the sector magnet is used for AOCS thruster latch valve, and hundreds of such magnets have been developed and given to ESSC. Now this is a BRC DMRL collaboration with the help of NFTDC, and they are the axial ring magnets for high-speed rotor applications. Now these magnets have been developed. Here the beauty is the field distribution all along the axis. So it has been accepted. Now it is not that we have developed the technology for SMCO5 alone. 217 and NDFEB technologies have also been developed, and such components have been developed and given to various DRDO as well as space labs for the applications. Now I would like to conclude my presentation giving a picture of maximum energy product with the price of the magnet. Now you could see that no doubt rare earth magnets are high cost magnets because they are capable of giving you high energy product, which is having a greatest advantage. For critical applications, we make use of samarium cobalt type of magnets, and for ambient temperature or commercial applications, NDFEB magnets are used. Now, this area is available to us for doing new material R&D, which is really a challenging one. So, I would like to conclude with the remark that fully dense SMCO and NdFeB magnets will always rule the market till we identify alternate permanent magnets. Thank you very much.
Thank you, sir. Can we present the memento from our Honorable C Editor, sir? Dr. V. Chandrasekharan. Can we present the memento after the slide? Thank you. Moving ahead, our next speaker, Mr. K.R.A. Nair, XAD Lucas TVS. The topic he would be covering would be is motors for electric vehicles and magnet with rare earth metals. Before taking to his profile, I would like to welcome him, sir. Mr. K.R.A. Nair. Glad to have you, sir, for your time and presence. Thank you. Can we present a warm bouquet as a welcome gesture from our end? Now taking you through his profile, Mr. K.R.A. Nair, after obtaining postgraduate degree from IIT Bombay, has been in R&D and engineering management in large corporates for many years and retired as Executive Director Development from Lucas TVS. He introduced lean product development practices and PLM in Lucas TVS for the last 15 years. With over 50 years in managing new product development, Mr. Nair has guided a number of electronics, mechanical and lighting products for various automotive applications. He was associated with many educational institutions in India and has delivered many lectures and tutorials. He is a member of SAE and IEEE. His special interest areas are innovation management, creativity, new product development systems, and design thinking. His current interest is in the field of electric mobility. He was actively involved in new product innovation and holds 25 patents to his name. This definitely calls for a huge round of applause. We welcome you, sir, Mr. K.R.A. Nair, for his amazing session. Thank you. Over to you, sir.
Sir, you're audible, sir. Please share your presentation.
Yeah, please present the first slide. Or shall I share it?
You please share, sir.
Let me try.
Yeah.
Can you see my slide, please?
Yes, sir. It's visible, sir.
Okay.
Sir, make it full screen, sir.
Thank you very much for inviting me to share some ideas about
Sir,
the use of rare earth magnets.
Sir, request to you, please make it full screen.
Pardon?
Make it full screen, sir. Slideshow, sir.
Yeah.
Yeah, thank you, sir. Thank you.
Okay. Thank you very much for inviting me to share some of the ideas of the use of rare earth magnets in electric motors, specifically for electric vehicle. As all of us realize, a very huge change is taking place in the mobility sector. Mobility constitutes one of the major economic activities of any country, and in India it is probably around 16% of the GDP is contributed by mobility, and many other countries it is 25% and above. Government of India has plans and have policies to increase the contribution of mobility from 16% to 25% in the coming decade. Now, a major disruption is taking place in the mobility sector. As all of you know that mobility sector is dominated by fossil fuel based engines or internal combustion engines or turbines or the like of that. And that took about 150 years to reach the present level. And we are seeing now, mostly due to the importance of climate control and environmental protection, a change to electric mobility. Now, I believe from the data and the analysis done by many companies, in the next 50 years' time, electric mobility will completely replace the fossil fuel-based transportation, whether it is on the road or the air or in the water. If you look at this major change that is going to happen in a much shorter period, you can classify them as based on-road vehicles, aircraft or vehicles in the air, drones, again vehicles both in the air, ships and boats, and I have not specifically mentioned here railways, because railways are already using in a major way electric vehicles, except that the source of power may vary in the future. But if you look at the on-road vehicle, there are vehicles like scooters, motorcycles, passenger car, transport buses, and then going into large trucks, which could be 10-ton to 40-ton trucks transporting goods across the country. Now, aircraft, already there are aircraft which is flown using electric motors. The photographs which I am showing him are actual vehicles which have flown with electric mobility, and the Airbus is now developing large passenger aircraft using electric motors. We will see a large amount of drones in the future. I predict that due to the e-retailing and the delivery that is going to happen in the future to all our household items and products, there will be a large amount of use of drones, and millions of drones will be utilizing if you look forward to 10 or 15 years' time. Already ships are using the electric propulsion using batteries, and the pictures which I have shown there are actual vehicles using batteries and electric motors. And of course, small boats, there are thousands of boats already electrified, and millions of will happen in the future. So this dramatic change in the mobility sector, moving from fossil fuel-based mobility product to electric mobility, is a major change. And one of the enabling factor for this is the availability of high-power neodymium magnets. Now, if you look at the motor for each of these applications, just to give you an idea about the range, we are talking about it. A small electric scooter could possibly be from 250 watts to 10 kilowatt in 10 kilowatt. And a motorcycle could be from 5 kilowatt to about 30 kilowatt power. They will be low voltage because it's generally between 12 volt to 32 volts. Passenger cars have been built up using 72 volts to 800 volts, with power rating going from 35 kilowatt to 300 kilowatt. Passenger buses, again high voltage applications from 150 kilowatt to 250 kilowatt. And large trucks will require much larger power from 200 kilowatt to 400 kilowatt. So when you are talking about electric motor for the electric mobility on the road, you are talking about power ratings between 250 watts, that is small, very, very small motors, to 400 watts, 400 kilowatt motors, which are very large in size and energy requirement. Now, all of these motors today are using permanent magnet because of their efficiency over the normal conventional voltage excited field coil motors. So a 250 watts motor may probably be using ferrites, but 1 kilowatt and above that is used in the motorcycles in this country and everywhere are using neodymium magnets. All others are also using neodymium magnets. So that is the reason for it. Now, if you really look at it, in 2020, about 3.2 million units of passenger vehicles were produced and sold. The growth curve is shown here. It is just accelerating, and in the future it is expected to grow at a CAGR anything between 2.5% to 8.6%, depending upon the country we are talking about it. All of them are either battery electric vehicle or they are plug-in or hybrid electric vehicles. Now, if you really look at the global projection for passenger cars going up to the 2040, now today it is just about 3%. It is expected to reach about 54% to 55% by 2040. So the number of electric vehicles at that point in time would be approximately 45 million electric passenger vehicles will be manufactured in the world by 2040, another 20 years time. This does not include the two-wheelers. In our country, we know we produce about close to 20 million two-wheelers now, and the government of India have plans that 80% of those two and three-wheelers should be converted to electric vehicle by the year 2030. Based on the current demand projection of two-wheelers, I have made an approximate estimation of the production will be approximately 18 million two-wheelers by the year 2030 or maybe 2040. Similarly, about 2.4 million passenger cars will also be made by the year 2030. So a huge quantity of motors are required for this, and hence a large volume of neodymium magnet or such powerful magnet material are needed in the near future. 2030 is not far. It is only about 10 years from now. If this happen by 2030, then our climatic efforts to do climatic control will not be achieved. So it is absolutely essential such changes take place in the next 10 to 15 years time. Now, what are the motors used in the passenger car today? More than 80 to 85% of the passenger cars today use permanent magnet motors, and the balance is non-permanent magnet motors like induction motor, etc. So, though there is a need for moving away from expensive, high price volatile neodymium magnet into non-neodymium magnet or magnet-free motors, the present situation is such that mostly people are using neodymium or permanent magnet based motors. That is not going to change immediately. Maybe another 10 years time, this may change, but not in the immediate future. Now, how quickly will the market for EV rare earth elements grow? Now, according to one of the predictions, dysprosium for EV would reach a volume requirement of 6,000 to 13,000 tons by 2030. Now, this wide variation is because people are not able to clearly predict what would be the demand for electric vehicle in the future, because today it is not cost competitive with IC engine vehicle. But with battery price dropping dramatically, the figures like 13,000 ton requirement of dysprosium is likely to happen. Similarly, when you look at neodymium, the prediction is between 20,000 tons to 40,000 tons by 2030. The sodium will grow from about 5,000 to 10,000 tons by 2030. So there is a huge demand. This is the global demand, it's not Indian demand. So there could possibly be changes in these numbers because there is work going on in making electric motors less dependent upon the quantity of neodymium used in per motor. They are trying to come out with a design where neodymium iron boron magnet usage is lesser and lesser as time moves forward. Now, a particular electric vehicle will need a passenger vehicle will need approximately 3 kg of neodymium permanent magnet motors, and from the numbers I quoted for the vehicle, you can estimate the volume of magnet that will be required. What are the characteristics of a motor required for the electric vehicle? It has to be high specific power and high specific torque. That means the power per kg or power per liter of the volume of the motor should be smaller, because that gives you higher range for the same battery. High specific torque is needed because large mass of weight is to be accelerated in a short time for the electric mobility. And that means higher torque, and that indirectly calls for high magnetic flux density in the motor, and hence high power magnets are required to produce high torque. It needs a wide speed range. The magnetic flux and the current in the motor have to be varied considerably to vary the speed from very low speed of, say, almost zero speed to 16,000 speed RPM in the case of a passenger vehicle, and in the case of a two-wheeler from 0 to about 5,000 RPM. High efficiency over wide torque and speed ranges. High efficiency is very vital for two reasons. One is the battery can give you a particular range depending upon the efficiency of the motor. It has a direct impact on the size of the battery that will be required to drive a vehicle. And this is also required, high efficiency should be obtained at a wide range of torque and speed. As I told earlier, the speed could vary between 0 to 15,000 RPM. There are two kinds of areas. When initially the vehicle is started, you need high torque for a certain speed, and thereafter the vehicle won't require the same kind of torque, but that will require higher speed and lower torque, hence constant power operating capability. Now, passenger vehicles have today reached a very high reliability stage. Quality of IC engine have remarkably improved. 5 or 10 years life is available to it. So the new motors which we develop should have high reliability and high robustness for the vehicle environment. That means the magnet must be highly reliable. It should not lose its magnetic capabilities and should be robust against vibration, against mechanical forces, and against temperature. And obviously, automobile is highly price sensitive product, and hence motor has to be reasonable cost for that. So these are the requirements for an electric motor, and let us see how the magnets give these kind of capabilities to the electric motor. This is the power I mentioned about it. I don't know where you can see my cursor. The black curve here shows the torque curve. There is a constant torque region at the low speed. The x-axis is the speed curve, and the y-axis is the torque and power. The black one shows the torque characteristic required. So low speed region, high torque, and then the torque can come down to a lower value. If you look at the power requirement, the power starts from 0 to a certain rated power, and thereafter the power can be maintained constant. So this is the characteristic of an electric motor required for electric vehicle, and fortunately, permanent magnet motors are ideal for this application. This is a typical arrangement of a motor in a two-wheeler, because I'm mostly concentrating to two-wheeler, that is biggest market in India. This is from the motorcycle which is in the market, either a motor connected through a speed reduction mechanism. The initial stage will be a gearbox or a belt drive, and then another belt drive to the wheel. So the motor speed will be reduced, torque will be multiplied by the reduction mechanism that is shown here. Another type of motor is called the hub motor, which is used in low-speed scooters and motorcycles. The wheel is built around the motor. The center portion is the motor, and then you have the ring which is connected to that, and the wheel and the rubber tire is put on top of that. This becomes a wheel. This has got certain disadvantages in terms of reliability, but in terms of convenience and cost, it has the advantages. Hence, low-speed scooters and motorcycles use hub motors, and the arrangement shown on the left side is the arrangement which is generally made for larger scooters, motorcycles on it. Now, there are different types of motors for electric vehicle. One is the permanent magnet synchronous motors, and the subclassification of that will be the PLDC motor, brushless DC motor, then interior permanent magnet motor, and there is another class of motors called axial flux motors. Another kind of motors used are induction motors, which is produced in large volume for industrial applications, but they are also finding application in the electric vehicle now. Then there are synchronous motors, new motors type like switch reluctance motor or SRM motor or synchronous reluctance motor. These are the typical type of motors used in the electric vehicle, and I will briefly point out the characteristic and constructional features of these motors. Now, a permanent magnet BLDC motor, there are two types, where the stator and rotor is placed in two different arrangements. As you know that any electric motor have got a stationary part which we call as the stator, and a rotary part which we call as the rotor. In the internal motor, the rotor is in the center of the motor connected to the shaft, and the permanent magnets are mounted on that. On the outside is the stator, which is a lamination stack punched out of low loss silicon ion laminations, and windings are put on that. Power is connected to this through the electronic control. In the outer runner motor, which is a hub motor kind of arrangement, where the rotor is on the outside and the shaft is not rotating in this case, and that carries the stator with the winding to which power is connected. So hub motor is an outer rotor arrangement. Now inner rotor BLDC motor is more efficient than an outrunner motor. But because of the structural arrangement, the magnet could fly out at high speed, and hence this is not used for application where the speed range is more than 5000 RPM. That is where interior permanent magnet motors are used, where the permanent magnet is now embedded in the lamination structure of the motor and hence can withstand high speed application. In addition to that, the interior permanent magnet motors produce magnetic torque, that is torque due to the magnetic field in the machine, as well as due to the change in the reluctance of the machine when it is rotating. Now all these motors carry the flux in the radial direction with respect to the air gap. That means the electromagnetic flux crosses the air gap in a radial direction from the shaft of it. In order to improve the power density and efficiency of the motor, it is possible to produce what is called axial flux motor. A scheme and sketch is shown here, where windings are placed in such a way that the flux moves along the axial direction compared to the shaft. This enables about 10 to 15% more output from the same volume or weight of the motor. So these are the most common type of permanent magnet motors used. Now you will notice that the neodymium magnet could be in the shape of an arc or rectangular or cuboid or trapezoidal. So various shapes of neodymium magnet will be required for making these kind of motors, and various sizes will be required depending upon the power requirement. The other type of motors, induction motor is well known. Millions of motors are produced for industrial application. Tesla, when it produced the model S car, they used 2 induction motors as shown here in the picture side by side. They have developed motors using copper cage. Induction motor consists of a stator and a rotating part which is called a squirrel cage, where aluminum conductors are cast. Instead of that, Tesla used copper as cage material to increase the efficiency and specific power of the motor. In the later models, Model 3, Tesla has moved away from induction motor and they use one of the motor as, later I will be explaining what it is, synchronous reluctance motor, where the reluctant torque is used along with magnetic torque, and another motor is a BLDC motor of the interior type. Another motor which is of promise for small power applications, scooters, motorcycles, small boats, etc., will be the SRM motors. These are under development now. A lot of companies are developing these. This will not require any permanent magnet at all, but it can also improve its performance by adding neodymium permanent magnet to the structure. The structure consists of a winding in the stator part and a iron path, iron member in the center, and the torque is produced by change in reluctance happens when the rotor rotates. Synchronous reluctance motor is a new development. I will skip this slide and go to the next one later to explain that. Now, when you look at, as I told you, most of the vehicles today use permanent magnet motors. You will see that I listed out the vehicles on the left side, the type of motors, and you will see that most of them are permanent magnet motors. And Tesla and Audi uses induction motors. Now they also are using one of the permanent magnet motors. There is Renault alone is the company who is using synchronous reluctance motor, but they are using a wound rotor arrangement, which is many people don't use it because the reliability is in question for this vehicular application. Now, the high neodymium magnet, I don't have to tell you the august audience here, have certain long-term issues. The long-term availability of, stable availability of neodymium is in question, because as it is today, neodymium magnet is produced, almost 90% that it is produced by one country in a particular location, and they have their political agenda and commercial practices to control the production of neodymium and the supply of neodymium magnet. So vehicle producers are finding it difficult to depend upon neodymium magnet-based motors, and hence work is going on towards avoiding neodymium permanent magnet in motors for the EV. The other disadvantage is technical limit on the performance, particularly in demagnetized. When a stator is carrying the electric power from the battery is short-circuited or draws large current, that can produce a magnetic field which is opposite to the magnetic field produced by the permanent magnet, and the permanent magnet can permanently get demagnetized. That means the motor power suddenly will go down. Similarly, neodymium magnets are not very good for high temperature application above 120, at best probably 150 degrees. Motors can be designed to operate much larger temperatures by water cooling, and water cooling or oil cooling of permanent magnet arrangement is expensive and difficult and cumbersome. So generally motors are designed to operate less than 120 degrees where they are using neodymium magnet. Now that is a disadvantage. If you can go up to 150 or 180 degrees, the motors can be made smaller and smaller. So a lot of work is currently on this. One other type of thing is the synchronous reluctance motor. As I told you, there is a stator, which is the outer, where the winding will be placed and the power will be fed to that from the inverter. And the center portion, where you see a spider-like arrangement, is lamination blanked out with the holes in the white portion. This arrangement will produce reluctance torque. The advantage of this motor is that when you supply a particular frequency power to the stator, that corresponds to a particular synchronous RPM, and the rotor will get synchronized with that. When the rotor and the stator magnetic field get synchronized, there will not be any magnetic losses that will happen in the rotor, and there are no conductors in the rotor, no current carrying conductors in the rotor, and hence there will not be any iron losses. So when the motor is synchronized with the stator rotating magnetic field, there will be zero loss in the rotor, so the motor will be more efficient, the temperature rise will be lower, and it will be a constant speed operation. So considerable research is going on in this. There are companies who are producing this, but it has not been yet used en masse in the electric vehicle. And my prediction is that in the future, this will be one of the major type of motor that will be produced. Now, in order to further improve the performance of this motor, it is possible to place some neodymium or samarium cobalt or even ferrite magnet within these slots shown here in the rotor. So you will have both reluctant torque and the electromagnetic torque, and hence the motor could be made smaller. So this is definitely one possibility for new motors in the future. Now the new two trends that is taking place is design of motors without rare earth magnets or with less rare earth magnet. The other one is producing magnets without rare earth at all and or with lesser rare earth elements. A lot of work is going on with Toyota and Japanese companies. They claim that they can produce same kind of neodymium magnetic power with about 20% less of rare earth elements. Further work is going on in reducing the use of dysprosium in neodymium magnets by dispersing it only on the boundaries of the crystals. So that is one major work is going on. Not much work as far as I know about is happening about that in India. And one of my recommendations to the abbess body here is please take up development of magnet with less rare earth or without rare earth. That will free us from a lot of import and strategic dependence on a country, particularly China. And again, work needs to be taken up in academic institutions, industries, and research organizations to develop motors without rare earth magnets. So these are the two trends, and efforts should be directed in this country to follow the trend and achieve so that the goal of the government of India in introducing electric vehicle in large volume in India by 2030 can be achieved. And that's all just to give you an overview of the use of motors with the neodymium or rare earth magnets in electric vehicle. Thank you very much.
Thank you so much, sir. I want you to please be happy that we all are here and we all have properly got the insight what you wanted us to go through, and definitely I'm sure that it would be beneficial to many who have connected physically or virtually. Right now, it's our honor and privilege to present you a token of appreciation and memento from our Honorable CMD. Sir.
Thank you.
So, till now, so far, how was the session? I would definitely like to break the monotony. How was the session? Did you enjoy? And many heads are still down, busy with their mobile. I would like to tell you the one thing, that many people are connected to us in virtual medium. They are also listening, they are gaining insights, and definitely these 2 days would be that beneficial that you would be going with very wonderful memories and of course valuable takeaways. So whether you directly belong to IREL or you are connected as a direct or indirect stakeholder, I really want all of you to feel proud that we are celebrating 7 decades of journey so far in the form of Platinum Jubilee celebration of IREL conducted by REAI and IREL conjointly. And right now, I want all of you to please have your eyes on the screen than your cell phones, because cell phones are going nowhere, but this particular few moments will never come. So let's have a look on our IREL in a more better way, in a more crisp way. Let's know it in a more, I can say effective way, and let's feel the pride once again. Let our adrenaline rush in our body, and let's all of us say together, Jai Hind. Please have your eyes on the screen because we are gonna play the corporate video of IREL. Can I hear a round of applause from everyone, at least whoever are seated over here, physically present? Thank you, thank you.
In 1909, a German chemist discovered something interesting. Yellow grain-like particles that were sticking to coconut fibers exported from Kerala. That is the beginning of our story. Envisioned by Dr. Homi J. Bhabha, the father of the Indian nuclear program, the first chairman of Atomic Energy Commission of India, Indian Rare Earths Limited was incorporated in 1950 to unleash the massive potential of India's rare earths resources and to cater the strategic requirements of the nation and become a full-fledged central government undertaking under Department of Atomic Energy. IREL, that started out as few plants in South India, has grown across different parts of the country while making ourselves indispensable in the global rare earth and beach sand mineral industry. Ilmenite, rutile, zircon, sillimanite, garnet, and rare earths mineral. From the shores of Kerala to that of Odisha, the nation identified deposits of these precious heavy minerals. Our product range varies from minerals, chemicals, to rare earths compounds. Technological advancements recognized a wide array of end-use applications of our products, ranging from the toothpaste you use to complex roles in the nuclear industry. Over the years, IREL has accomplished significant milestones. In recent years, we have witnessed a massive surge in production and sales turnover of over 10 billion, contributing to the country's growth. Community-oriented, socially responsible, and environmental-friendly mineral harvesting and value addition broaden our horizons and capability. In this momentous occasion of our platinum anniversary, IREL India Limited is proud to present our key projects that will shape and broaden the profile of our nation. The Rare Earth and Titanium Theme Park that will enhance the production and consumption of rare earths across the whole of India, which will boost entrepreneurial opportunities. The Rare Earth Permanent Magnet Plant that is set to come up at Visakhapatnam that will add strategic edge for India. More than an organization, we helm the complex role of driving the nationalistic spirit and be in the forefront of driving the country to a symbol of progress and power in this decade.
IREL, Unleashing Values.
Check. So after 2 days of discussion, right now when we are arriving towards the concluding session, I would like to request all of you to please be attentive because we would be having some of the eminent panelists in virtual mode and some would be joining us physically. And we would be conducting a panel discussion which would be, you can say overall it will be generalizing the topic, that is RE Roadmap for Energy Security of Self-Reliant India, REES 2021, for which you all are here. So if you all are ready, it gives me sheer pleasure to welcome our Honorable CMD IREL, who would be chairing the panel discussion, none other than Sri Dipender Singh, Mr. Dipender Singh is the Chairman and Managing Director of IREL India Limited, a central public sector undertaking under the aegis of Department of Atomic Energy, Government of India. Having rich and varied experience spanning over more than 3 decades in the field of strategic corporate planning, sales and marketing, project management, production planning and control and quality management system, human resource management, vigilance, skill development and industrial training. Recipient of several awards including Best CEO conferred by National Feather Award and Public Sector Enterprises Excellence Award 2016 for Corporate Governance and Public Sector Enterprise Excellence Award for Outstanding Contribution to India Public Sector Industry. Conferred with National Best Employer Award 2018 by Global Employer Branding Institute International Leadership Innovation Excellence Award 2019 by Institute of Economic Studies and the prestigious Scope Award for Excellence and Outstanding Contribution to the Public Sector Management Special Institutional Turnaround Category 2016 and 17. Credited with over 65 presentations in international mineral and other conferences, at present, President of the Rare Earth Association of India, Chairman of Processed Mineral Panel of Capexil, ex-member of Executive Board, Standing Committee on Public Sector Scope for 2017-19 and 2019-21 and member of Managing Committee of Federation of Indian Mineral Industries and other prestigious industry associations. Please put your hands together upon welcoming our Honorable CMD Sir, Shri D. Singh. Moving forward, we are having another panelist. He is present physically, so would like to welcome him, Dr. M.B. Verma, Consultant T&I NSCS. Shri M.B. Verma is former director of AMD, an outstanding scientist, has an experience of nearly 4 decades in uranium, rare earth and strategic minerals exploration in India. He is gold medalist from AMU and has contributed immensely in improving uranium resource of the country. Mr. Verma is field scientist and worked different terrains of Eastern India, Western India and Southern India and guided strategic mineral exploration. His major contribution in uranium exploration led to opening up 3 major uranium mines of Bagjata, Molide and Bandharung uranium deposits which are being exploited by UCIL. He played a significant role as Director AMD in safeguarding BSM resources of the country in policy matter. He has guided rare earth exploration in parts of Rajasthan and Gujarat, and Ambadungar may come up as first rare earth mine in the country. He has been honored by Government of India and number of institutes for his outstanding works. He was awarded National Geoscience Award in 2010 by Government of India, Lifetime Achievement Award by GEO Geochemical Society of India, Hyderabad and DAE's Outstanding Achievement Award. He has visited number of countries such as Canada, Australia, Vienna, China and Israel and presented research papers and attended meetings as official capacity. He has nearly 200 publications in national and international journals. After retirement, he is associated with National Security Council, Secretariat and advising matters related with rare earth and strategic mineral resources. Please put your hands together upon welcoming Shri M.B. Verma as one of the panelists. So we welcome you and thank you for joining us physically, giving your valuable time and presence. Already our CMD sir have joined us. Moving ahead, we are having another panelist. His name is Dr. Mohan K. Dongre. He is a senior scientist from Catalyst Division, National Chemical Laboratory, Pune, India. He is a visiting professor at the following institutions: Institute of Material Science, University of Connecticut, USA, Leibniz Institute of Catalyst, University of Rostock, Germany, Department of Chemical Engineering, Tufts University, Boston, USA, United Catalyze, University of Lille, France, Department of Electrical Electronics Engineering, University of Surrey, Guildford, UK. Currently, a director at R&D MOZZ Engineering Systems Limited, Bhusari, Pune, India. Malathi Fine Chemicals Private Limited, NB Pure. And let me tell you that he has about 100 publications in reputed national and international journals, also bagged many awards and accolades, and about 10 US and world patents and 15 Indian patents. He has the following accolades you can see: process for the manufacture of the titanium silicate 1, Silicalite 1 using the ethyl silicate 40 as the silica source. Process has been transferred to Shat Chemi India, and the product is manufactured by the SUD Chemi and is being sold in the market. Preparation of quaternary ammonium hydroxide from bromides using electrochemical processes. Process has been transferred to alkyl amines India. Process for low cost production of silicon tetrachloride polymeric TiO2 nano stands as photocatalyst for environmental applications. Recovery of potassium from spent wash incinerator fly ash. He is supervising 5 PhD theses, and also he is supervising 10 students who are currently pursuing MSc and MTech. Sir, we welcome you to this wonderful set of panel discussion. Please put your hands together upon welcoming Mr. Dr. M.K. Dongre. Now moving forward, we are having another virtual presence of an eminent person we can see. He is none other than Professor Chandrasekhar Srinivasan. He is the J.R.D. Tata Visiting Professor at the National Institute of Advanced Studies, NIAS, Bangalore. Before joining NIAS, he was a professor in the Corporate Strategy and Policy area at the Indian Institute of Management, Bangalore, IIMB. Before moving to IIMB, he spent more than 20 years working at the Indian Space Research Organization. His work at ISRO covered all parts of the program: satellite, rockets, as well as the application of space technology, including remote sensing and telecommunications. At ISRO, apart from his role in major projects such as the Indian remote sensing satellite, he dealt with activities related to international cooperation that included the US, France, European Space Agency, Germany, and the Soviet Union. He has represented and led Indian delegations to the United Nations Committee on the Peaceful Uses of Outer Space. He was also involved with the space-related activities of the Conference of Disarmament in Geneva. At NIAS, his work largely covers the missile, nuclear, and space domains. This includes war and deterrence strategies, space weapons, space war. Along with colleagues at NIAS, he has also studied the use of satellite imagery for identifying uranium mills. Recent work outlines a space strategy for India that links space assets with both development and military needs. He has also completed a study of anti-access area denial strategy and its implication for war and deterrence in the Indo-Pacific region. Please put your hands together upon inviting Professor Chandrasekharan Srinivasan. Last but not the least, to moderate the panel discussion, I would like to welcome Director of Deloitte, who is none other than Sri Rajiv Maitra. Sir, we welcome you. Let me take you through his profile. Mr. Rajiv is a director working with Deloitte India with around 18 years of experience. Rajiv has more than 15 years experience in metals and mining sector and has led 60 plus consulting engagements for governments, public and private sector clients. His experience includes engagement across solutions, including corporate strategy, business planning, policy advisory, operational excellence, bid advisory, including mineral block auctioning, project management, and digitization. Rajiv has a deep understanding of the critical minerals and rare earth sector globally and in India. He was also engaged by various government entities in drafting policies related to mining and investor promotion for minerals. He also has deep understanding of digital transformation and future of work across clients in mining and metal sectors. He has co-authored thought leadership publications within firms as well as national and international conferences. He has been invited as a speaker at leading conferences and industry forums. Currently, Rajiv is a special invitee member of the Mining and Minerals Committee and a member in International Trade Committee at Chamber of Commerce in India with respective focus on shaping and trade policies. Please put your hands together and let's have a wonderful, meaningful panel discussion right away, right here. Thank you.
Good afternoon to all of you. Good afternoon to Honorable President REI and CMDC IRL India, eminent speakers, dignitaries, industry veterans, and conference participants. It's a great pleasure to be here amongst all of you for the Platinum Jubilee celebration of IRL. And it is indeed a momentous occasion, and many congratulations to the IRL family for the glorious 70 years. As India, marches towards a 5 trillion economy, I wish IRL a very best, and over the next decade in its performance. And very significant is, both the global and domestic megatrends are forecast to drive significantly higher global demand for critical rare earths and its processing technologies. And India has an ambitious industrial reform agenda to expand the manufacturing capability and to transition to a low carbon and digitized economy. And this includes plans for rapid expansion of electric mobility and renewable energy generation, as well as enhanced capability across high technology sectors. And for all of these, rare earths is going to be a very, very important source of materials. And thus it is a great privilege to moderate this panel discussion and also the concluding session on RE roadmap for energy security of self-reliant India. First, would like to welcome the session chairman, Sri Dipendra Singh, Dr. M.K. Dongre, Professor Chandrasekharan, and of course Dr. M.B. Verma. We are indeed grateful to have all of you today. And over the last 2 days, we have heard very eminent speakers covering multiple topics pertaining to rare earths. They spoke about perspectives on demand and rare earth applications. They spoke about exploration and supply, including from non-conventional sources, processing and refining technologies, and recovery from secondary sources, and magnet manufacturing. We all know that India's rare earth supply chain has limited commercial scale production in the midstream and the downstream sectors, and the end-use players are largely dependent on imports, which kind of necessitates that there's a technology available for conversion of rare earth oxides to metals and alloys. Of course, BRC has developed kg scale technology for many metals, but development of a commercial scale indigenous technology is very important. And some of the key themes and considerations that emerged over the last 2 days deliberations included end-use market trends, end market products, application technologies. We spoke about EV, we spoke about clean tech, strategic applications like nuclear, defense, and space. We also spoke about role of substitutes in shaping future demand. So, for example, some of the elements like lanthanum, cerium, today they don't have much demand, but they are going to also significant demand going forward, especially lanthanum and cerium used as a mish metal in the magnets, as well as for hydrogen. I mean, in lanthanum, nickel compound can be used in hydrogen generation storage. We also heard about the supply side dynamics and supply chain for rare earths in terms of access to minerals, exploration and mining, commercial scale processing, extractive metallurgy technologies to produce high purity materials, supply chain, resilient supply chains, and business model for supply chain collaborations, and also the ecosystem for the RE supply chain. Also, we are aware about sustainable processing and handling of radioactive waste as a major theme around the world. And lastly, of course, recovery of secondary sources for urban mining of rare earth metals. And lastly, the enabling measures. Some of the speakers spoke about policy support in terms of recognition of this sector as a strategic sector, research and development, which already is happening very significantly in the sector, partnerships, not only domestical, but globally as well, and incentives and support. For example, one of the speakers mentioned about tax credits that US has come about in the last 1 month or so. So how those kind of supports and financial incentives can address the viability concern in projects. And last, of course, India is deficient in heavy rare earths, so can also some government support in the acquisition of assets, especially in HRE and through IRL Videsh. So these are some of the key themes, and probably I would open the forum to the panelists, and starting with Dr. Singh, Shri Dipender Singh, on his key, key themes that he has kind of observed over the last 2 days, and what are the implications for the sector as a whole.
Thank you very much, Mr. Rajiv, and good afternoon to all my fellow panelists as well as the audience. So, in order to do justice with the topic of this seminar, that is the roadmap for energy security, roadmap of rare earths for the energy security, I would like to go back a little bit and let's try to analyze some of the things which we have been hearing so long. So first and foremost, ever since I have been associated with this rare earth sector, I have been hearing two statements, two narratives rather, I will say. And one of that which has been well reverberated statement in RE sector by Chinese premier, that is Deng Xiaoping in 1992. He said that Middle East has oil and China has rare earths. So this is a single sentence, but if we slightly look into it, it is a statement which has been derived after, I think, a lot of research and a lot of work behind that. So let's analyze what is the meaning of this statement, which may, I feel that, in my opinion, it may encompass RE or rare earths in totality. So why have these two commodities been compared? Are they really comparable? Oil has been necessity all along. Need not to explain it. All of us knows it very well. It has made distance shorter, mobility increased, and today life cannot be imagined without oil. But can we think the same thing with the rare earths? Of course, no. Life can be very well imagined without rare earths. So what is common in these two? What I feel that, in my opinion, the common is only one, that in case of oil, it is part of almost all the segment, and without oil, no industry could have progressed to the extent which it has done today. It is part of almost all the industry, all the part of life of human being, and that's how the oil is very, very important for the human being. And when it was discovered, after that, I think the global scenario also took care of this sector very well. And in order to overcome the market risks in terms of demand and supply gap, a particular component has been introduced in the system so that such situation do not arise. And if this situation is not arising, probably the risk factor has been mitigated to some extent. So what is there in rare earths? So in my opinion, there is only one similarity, as footprint of oil is available in all the facet of life. Similarly, the footprint of rare earth could be experienced or could be found wherever one feel that he has to become technologically superior. And this is what probably the statement meant for. If we have the rare earths, if one has the rare earths, let us try to utilize in various facets of life, and how we can try to improve, or how we can try to prove ourselves superior than the others. So this is what, of course, my own analysis. There might be something different besides this. So there are other commonalities, that is, both have usability in the wide window of application, and the thing is that oil is driving and rare earths provides the edge to the specific country. But with the oil, there is a advantage of very high volume. Therefore, they have the economy of scale of production. They have very high commercial value. But whereas the rare earth is of low volume consumption and therefore low volume production, and therefore it tends to be monopolized, and therefore it is devoid of economy of scale. But it is very critical in certain areas, and therefore it has become of a commodity of strategic value. And that is the reason, in my opinion, that mostly developed economy only has the interest in rare earths. Say the economies who are struggling may not have much interest in the rare earths, and this we can very well see in the surrounding. So in the geopolitical scenario, we are often hearing that the rare earth-based trade war is going on. No sooner some difference of opinion arises in the system, then suddenly these news starts coming. With the COVID pandemic, also we heard that China and US there is a trade war. So what difference does it make basically? So the difference is can be better understood by just one application, that is F-35 fighter plane of US that is using around 417 kgs of rare earths, and mostly these elements are led by dysprosium, terbium, and ytterbium. So these are the elements which is making the rare earths critical, and it is giving a very high value to the rare earths. Of course, there are other elements too, but this example is specific to F-35 fighter plane. So in essence, the rare earths, what is the utility? That utility is a small volume, a small quantity of rare earths will make sea change in the performance of the material. So if we look at the value chain of rare earths, in my opinion, the value chain of rare earths ends either at oxide level or at the metal level, where out of then the oxide level is better marketable because of its stability of the compound. And in case of magnet, it has to go up to the metal level. So in all the applications of the rare earths, we cannot make any commodity product by using rare earth alone. So this is a addition to play the critical catalytic role into the product. We can take any of the example. For example, addition of just 0.1 to 0.2% of lanthanum or cerium into molten steel, the properties can improve, and these properties are toughness, fatigue resistance, corrosion resistance, hot ductility, so as to produce next generation steel. Similarly, addition of 0.98 to 1.92% of erbium and gadolinium to magnesium alloy improves the corrosion resistance of the alloy to a greater extent. And all of us know that a small amount of terbium and dysprosium improves the coercivity of permanent magnet, while addition of cerium to NdFeB magnet improves its corrosion. But these even addition of cerium into NdFeB magnet is in a very small volume. So basically, this is the importance of rare earths in a nutshell. Addition of a small volume, a small percentage, and improvement of the performance multifold. And that's the reason the global consumption of rare earths is only of the order of around 180,000 ton reported in 2019. And out of that, around 7,000 ton are the heavies rare earth, and rest is over 1 lakh ton cerium, lanthanum, and then rest is coming the neodymium, etc. The another thing which we have been hearing very often about the rare earths, especially in India, that India has very vast resources. So though we are ranked 6th in the world about the resources, and in global market, I have not heard this statement for those 5 countries, but in our countries, we are very often hearing these vast resources. So vast resources of what? And what are the challenges? So first and foremost challenge is the rare earth resources, whatever we have in terms of monazite or in terms of carbonatite, etc. The grades are very lean. we are working with monazite resource, the grade is just 0.06%. So when we are working with such a lean grade, then in order to extract it, the number of plants, the number of stages required are more. So we ourselves are using around 4 to 5 stages to bring it into a shape by which it can be made usable to the industry. The other resource which we have recently come across is carbonatite source. So there also the average works out to near about 1.5%. Still the exploration is on. It is likely to change either side, maybe plus minus 10% on either side. But when we look at to the global resources, we are being operated today. The Chinese resource is 6% average rate, and that is found with gold, iron, and silver. So then the cost of production is distributed, and it is much lower. That resource was so strong that even higher average grade of US and Australia stopped production because of that, and now only they are trying to start their production. So looking at that, and if we see the other mines which are operating of that particular resource, no mine is operative less than 5.5% of the average grade. So we have gone ahead with the available resources, and therefore the economic viability is a real difficulty with such resources. Apart from that, the lean grade will have another issues. The one is long gestation period, because when one has to set up more number of plants, the gestation period will be higher. Then the number of statutory clearances required would be higher. Achieving economy of scale would be a challenge. So that's our challenge number one. The second challenge is that we are operating, if in India, we are operating in an environment where there is a virtual monopoly of a particular country. How that monopoly is created? When they saw that they have 37% of resource available with them, and the resources available elsewhere are not being utilized, the attention is not there, they have very proactively pursued the policy of overseas acquisition, and then today they are sitting about 75% or more than 75% of the global resources. So if anyone operator has more than 75% resources, then the monopoly is very obvious. They are working with a mature technology. They are having a very matured ecosystem. So at this time, when anything has to be started, I think this has to face challenges, and recognizing that probably the ecosystem is required to be developed. The another good point is that this is only India could not be affected because of this monopoly, that we continue to have our processing, and then therefore the capability retains, and we have not lost on this front. The basically, in my opinion, for this, the 3M factor works. That is mineral technology, metallurgy, and material engineering. So these are the things, because these are the 3M factor. We have to work with our customers or buyers, and unless as a processor we are addressing this issue, probably it is difficult to get a buyer in the global scenario. The another important point I feel that normally it is said that a value chain of rare earth need to be developed. See, when we are going for a value chain development, see, beyond rare earth, what is required, it is less known, and sometimes in those what is additionally required may be depending on imports or some such material which are not available in our country. It may be the equipments which are available or not available in our country. So then it is not a very definite approach. I feel that if these development are taken as a supply chain development in the sense those who are using it, if they are working and on the direction of development of vendor or development of supply chain, probably the ecosystem could be better developed. And to have that, as I think Mr. Rajiv was mentioning, and there was a discussion, certain support requirement would be there, and strategic need not to be in the sense that it is to be used only for a particular sector. Strategic can be for even the commercial sector also. But the approach to address the sector, whether it has to be strategic or commercial, that need to be crystallized in order to develop the ecosystem in the country. And to have the advantage of availability of this material, we definitely need to develop a ecosystem. Only the question is how it has to be developed and what kind of support system is required, what are the challenges available, and are we really addressing those challenges? So the whole system has to work together for achieving this ecosystem. So I would be ending at this point of time. Because there are other panelists too. And I would like to hear all of them. And if required at the end, maybe I'll request 2-3 minutes if any point is developed to reply for that. So thank you very much, Mr. Rajiv. You can proceed.
Thank you. Thank you, sir. Really wonderful hearing you. I think some of the points you touched upon was around relating oil to rare earths, and also in terms of the focus of the developed economies on rare earths, and the 3 M's in terms of mineral technology, metallurgy, and material technology, and the very important aspects about ecosystem and the supply chain development. So one of the questions that probably we can take up later is what can be the business models for supply chain. And I'll go to my next panelist, Dr. M.B. Verma, especially around looking at the end-use market trends, end market products, application, and technologies. There is a theory that either the supply chain can be developed from the upstream to the downstream, or some of the downstream players can also go, I would say, backward integrate to develop that midstream and downstream processing. So just want to hear from you about, especially from a market application and from a technology perspective, what are your views? And the very important point of ecosystem. I think very important that the ecosystem needs to be there so that India is a powerhouse in rare earths. What can be the possible business models?
Thank you, Mr. Rajiv. Before I answer whatever the queries you have raised, first of all, I am thankful and extending my greetings. So I extend my warm greetings and heartiest congratulations to IRL family for completing 70 glorious years of journey. You are one of the pillar of rare earths in the country, no doubt about it. Under dynamic leadership of Dr. D. Singh, a very active CMD, and I am very sure whatever the constraints and challenges he has raised, if we have a will, we have a desire, we will be honge kamyab definitely. Sir, no doubt about it, the rare earths are modern key drivers, and many challenges are there in our country, particularly transforming many of the sectors. Out of that, energy challenge is one of the biggest challenge. Even recently, PM in his address, he said that green energy is the need of the hour, and we need independence in the energy. Henceforth, the role of rare earths are going to be multiply number of times. Coming to the query raised by Mr. Rajiv, see, in the rare earths, we have got 3 kind of the setup, if we will see, basically for any mineral industry. That is upstream, midstream, and downstream. Upstream side, if you will see, mainly the exploration, mining, And to some extent, it is the concentration of all those things. Midstream will deal with extraction processes, separation processes, converting oxide to the metal stage, and downstream basically we go for the alloy, industrial applications, and all those kind of things. IREL is completing almost 70 years. All these process technologies are not new to the IREL. Challenges may be different. As Dr. Singh has raised that we have got, as far as resources are concerned, basically using the monazite, which also contains, besides rare earths, a good quantity of uranium and thorium. Fine, but and only selected rare earth elements are present in that. Henceforth, and we also have, we are somewhat deficient in terms of heavy rare earth resources. Most of our rare earth resources are confined into the beaches and placers, but at the same time, some of the important deposits which are coming in the Rajasthan and Gujarat, basically one of the deposits is having a much better concentration of HRE. In India, we do not get weathering profile as we are available in China's, particularly those iron clay deposits. Henceforth, there is no concentration of that quantity because it all varies with the geomorphic conditions, terrain conditions, climatic variations, and age of the deposits also. Henceforth, whatever available with us, with that we are trying to develop. Even we say slowly, slowly, if we will keep the pace, and there are number of other alternates do exist. What Mr. Rajiv was telling, if suppose we go for the backward integration, probably he wanted to say that sometimes the recycling can be useful, or there may be number of other resources. Those resources are unconventional resources. Many people talk about red mud, fly ash, phosphogypsum, even metal slag and all those things, maybe few alternates. But definitely, we need a very coordinated efforts of all the research institute, atomic energy laboratories, and the people, those who are working in these fields. Unless until a seamless coordination is there, then only we can able to achieve such type of the success. Our success rate will be very high. We will meet number of failures because it's a very complex, technologically complex process which involves multi-stage separations and also purity matters when you take any product to the marketing. Henceforth, it will take some time because although IREL is started very early, almost 70 years, see something around 1950 IREL is started, or maybe 51, something like that. But somehow other, as and when demand comes, because then only the development takes place. After 2010, when the people find there is a real kind of the strategy, world strategy involved, that everything segregated to one country, then the people get very much alert what to do. Henceforth, everybody started developing their kind of the resources. People started looking for all kind of the possible aspects. So in these type of the scenarios, we have to develop those resources in such a way that we can able to not only meet our requirement, but we can able to maintain a sustainable supply chain for our strategic sectors, defense, atomic energy, space, for our commercial sectors, electronic, this EV vehicles, and lot many sectors. So these are all the challenges which we need to address. But when we are going to this type of the phenomena, what we see, if we are extracting these things from the monazite, because there are only 4 minerals used worldwide for rare earth extraction. monazite, loperite, bastanesite, and that yttrium mineral, that is genotyme. Out of these 4 minerals, they are the basically, and then some clay minerals which are slightly heavier. What is important is we generate large quantity of the light rare earth element also. Therefore, we have to make some kind of the balancing arrangement in such a way. We have to develop those downstream industries also which can able to utilize the resources which remain unutilized with us. Sir, Singh sir has raised one very important question is that low grade. Fine, the grade is very challenging thing. It is the mother earth which has created the mineral resources. Some country, Bayanobo, etc., 6%. People say 5%, 4%, something like that is workable. But I tell you, very clear example. When the people were working in Kolar gold field, 7 ppm gold was cut off grade. Now more than 50,000 tons of gold is lying in Kolar gold field. Because today workability is 2 ppm. 2 ppm gold content is there, it is economically workable. Henceforth, we have to develop technology. We have to develop what are the co-products and byproducts available. Therefore, we can make those deposits workable. There are very good quantity of magnesium oxide, vanadium, then this niobium, other co-products are possible. So we have to look entire entity as one to make our domestic resources as one of the major source. Besides this, if we can able to get some good rare earth deposits, because China, beside developing their own deposits, they have developed large number of the world scale deposits. They have a control, many stakes are there. Henceforth, we have to go for some kind of the requirement to meet our strategic resources, even to go for heavy rare earth kind of the deposits. Even if it is not possible, try to develop some alternate for that which can able to meet our demand and supply gap. Therefore, more emphasis for the heavy rare earth exploration, to bridging the gap, this kind of things. We have to take right steps, develop the technology, try to extract the things, even if it is slightly low grade, because even the Ahmednagar grade comes around different cut-off grade, the grade will vary, but it goes up to almost 1.5% cut-off grade is more than 2%, 2.5%, what Dr. Sinha has said yesterday in his presentation. Other deposits also, Sivana, Ring Complex, etc. There is a good concentration, good ratio of HRE and LRE. Therefore, we have to work out. We have immense potential of metallurgists, technology, and very good network of CSIR laboratories. A coordinated efforts can able to overcome these kind of challenges. Because unless until we meet these challenges, we may not able to be successful. Resources, whatever available in our country, we have to develop our indigenous resources very well to be self-reliant. Whether you use today, you use after 20 years, 50 years, 100 years is a different matter. You conserve is a different matter. But definitely you should have availability. So tomorrow, if any kind of the disruption in our supply chain, people will not able to stop any of our commercial identity or any important strategic sector to be deprived of the resources.
Thank you, Dr. Verma. Really wonderfully you put across. I think the two focus areas that you mentioned, what I would capture is indigenous resources and indigenous technology for a self-reliance Bharat or Atmanirbhar Bharat. So talking about technology, and especially if I look at commercial scale processing, extractive metallurgy technologies to produce high purity materials, and especially we have technologies, extraction technologies like solvent extraction, which is primarily used globally, ion exchange also done. But some of the other technologies which are in lab scale or under construction, especially around rapid SX or MRT or maybe bioabsorption. So maybe I would like to go to Dr. M.K. Dongre to talk about what he perceives in terms of the technologies of the future, and how can India become self-reliant in terms of indigenous technology.
Good afternoon, everybody. I'm very happy to see that IREED is celebrating their Platinum Jubilee celebrations, and 70 years of, period is a big period in any organizations, and I'm sure people have learned the area in which they are working on. So, first of all, I congratulate to them. Second thing, am thankful to IREL authorities, particularly Dr. D. Singh, for inviting me to be a part of this panel discussion. I'm associated with IREL for last 8-9 years. Before my retirement from National Chemical Laboratory, we were trying to develop automotive required catalysts, particularly three-way catalysts and denox catalysts and other things. And we were successful up to a certain extent as far as the laboratory type products are concerned. So my colleague Dr. Shubhangi Umbarkar from National Chemical Laboratory is still working on that. I retired in 2011 and still associated with this group as an honorary. Friends, one more thing I want to tell you, because I had to leave Pune because of certain problems at my hometown. So I am in my hometown, so my range is not so good. So I request you to bear with me if there are some communication problems. We were working on catalyst development for catalytic converter in National Chemical Laboratory, and as you know, yesterday Dr. Shubhangi has already covered about the requirement of Syria, and we were using this Syria and we could get very good results. So one day I told her that, you see, why don't you see that we have such a good source of Syria, IREL people, should we talk to them? So it took for me, everybody will appreciate that we pursued IREL for nearly 1 year with Mr. Asnani, clear and Singh's period got a good shape project. And attend all the for last 2 days because the requirements at my hometown, so I'm sitting in my farm and trying to use mobile data. So there are some problems. When we talk about what I should say that what IREL is supposed to do, I am not that kind of what I should say expert to advise IREL. I heard Singh Saab just now, and he told the real problem. These are practical problems, and the person who has to execute, who has to plan, who has to implement, he knows the real problems. Friends, I am now in the market for last 10 years, developing certain products and trying to give to the industry. And knowing yourself what is the product, theory, all science behind, and you make be on a few gram scale, and then say that I have the material, I have the technology. It doesn't work. This is what we faced in NCL. So when IREL supported NCL project, we were very happy, and we could start with IREL Syria, and we could meet the specifications required by automobile industry. We could import some part of Syria from outside just for comparison. But Singh Saab, what I want to tell you that, you see, for any technology or any product development, involves lot of expertise, because what I have seen yesterday also, there were presentations from CSIR. I could see 2-3, even Dr. Shubhangi, others. You see, knowing just science behind this is not enough if you want to develop a product and give to the industry. In our scientific system, I don't want to say anything more about it, but then my advice to Dr. Singh Saab is that you know your strengths now. You have the material, you have mastered the production of various rare earths, and as you rightly said that we have problems when we are interacting with the industry, when you want to give a sample to them for testing, because that is not the only one material. They may need some other materials, other things. So my request to IREL is that, for example, if you take a case of Syria, which NCL has done, and there was a target for us that the product should be given to the industry. We tried our level best. It's not that we went all the way to Chennai, we went all to the Sutkimi, we went all to the people. You see, it is something like, if I give an analogy, you have made, you have basic, very good cotton with you. But from that cotton, you have to make thread. From that thread, you have to make a cloth, and from that cloth, you have to stitch your shirt. So there are 2-3 stages. So being a farmer, I know how to grow the cotton. It's something like analogy which I am going to give, may not suit directly here. But now it is high time for IREL that you have collected the required knowledge of your product by supporting R&D laboratories all over India. I'm very happy that Singh Saab takes very keen interest in supporting R&D. Now, when you want to go into the market, now you need a different kind of a team, different kind of support. Basic R&D has been done. Now, from this basic R&D, I have to give this product to user industry. So now you should know, or your people should know, that what is the requirement of user industry. What do they want? For example, it is like, you have to do 2 things. One thing is already basic material is, preparation is done. Second thing, now you have to scale up, maybe kg, few kg, maybe 100 kg, or a pilot plant of 1 ton. You need to have that product in your kitty. And apart from that, you have to establish a very good connection with user industry. For example, now in automotive catalysis, which we are working on, there are 5-6 players, big players, like BASF, Johnston Matthey, EcoCat, Sud Chemi, all these people. We know them personally. But somehow, being such an important area, you see, one catalyst in a car costs something like more than $200, $300. So, and this is a guarded technology. You see, we have the basic raw material with us, but now this needs to be coated on ceramic monolith, then it has to be tested. You have to have, for example, we wanted to test one catalyst at ARAI, Automotive Research Institute of India. You know how much they asked for? 1 lakh rupees, one sample. Now for R&D people, can they afford that? So best way now, one phase has been nicely completed by IREL. Now the second phase, which is very difficult, because working yourself in your own laboratory and developing material, testing things, and you are happy, everybody is happy. But now I have to make the user happy. So my request to Dr. Singh Saab is that now you need a different team. This team should go to the pole and post of the industry, establish a very good contact with them, and see that they are involved in the development. You have to find out a mechanism that how they will take, why they will take the interest of using your material. Sometime back, I mean, when I was developing material, I went to one company in Pune and they said that you are importing this zinc oxide from China and we have made this technology, why don't you use it? So he said, look, Mohan, this is something which has been established. I have a good source of supply, which has got reproducible, which is reliable. Now tomorrow you will give me 1 kilo, 2 kilo, and then afterwards if I disconnect that one and if you are not able to meet the requirement of my production, then I started saying like today we talk about Atmanirbhar, this, that, I said, you see it is indigenous, why don't you use it? So some kind of emotional drama I started making. He said, look here, I am not interested. I am a businessman. I am paying tax. So whatever you are saying is the government problem, not my problem. So now it's a different ball game for if you want to really enter the market. Fortunately, you have a big market of atomic energy and very nicely. I am happy to the area authorities. Whatever requirement was of our strategic requirement was there, they have met. But now, apart from that, if you want to do in the normal, I mean, another commercial market, you have to be different. So in that case, even myself and Dr. Chubangi, several times we were discussing how to break this barrier. For example, so my suggestion is initially you have, if you know that these are 3-4 materials which I am able to manufacture maybe on small scale or larger scale, can I make it still larger with reproducible properties, keep it with them, and then start the marketing. So unless until you do that, get the feedback from the market, you have to see that what is internationally available, what is the cost of that material, what is the, so you can sell your product based on two yardsticks. One is the specifications which you should be equivalent to international. Second thing, at what cost? Okay. So if you meet both these requirements, I'm sure you can enter the Indian market or international market also. It's not that, for example, if you see Syria, people use even for glass polishing. So what is that glass polishing cost they give? Whether can you give very high purity or normal purity? For catalysis, you need a very high purity. For example, in catalysis, you can give the mixture of 2-3 oxides. It's a very difficult part, and there you need dedicated people who have got, for example, if you want to go to the industry, we should be able to talk their language. For example, in catalysis, for example, some time back, I wanted to buy some material from IREL, and when I got the specifications, I think in the last meeting also I discussed with you, that specifications for normal chemicals are different, and specifications for catalysis are different. So you should be able to know that different. So we should be able to talk their language. So now Syria for normal applications, Syria for electronic applications, Syria for catalysis applications, specifications are required, different. In one case, you need only purity, 99.9% pure. In second case, you need some kind of the particle size distribution. Third side, it will say very high surface area. Sometimes it is less surface area. So my request is that now we have achieved certain good level of confidence. Yourself. You have the strengths. And now the next stage is that how to cater the market, how to, and then you need for that a good team, a good pilot plant facility, and maybe a separate division for material manufacturers apart from what you are doing. So I'm happy that you are supporting R&D activities in various laboratories, but I will tell you, I am also from CSIR for last 40 years. You see, you can get certain required data from our laboratories. You can get certain confidence. But if you ask them to deliver the product to the satisfaction of the end users, they will try. I don't say that they are genuine people, but then you see they have limitations. So this is what I wanted to convey. I'm sorry I couldn't participate very actively in the conference. I am at my hometown. I am in my farm. So Dr. Singh Saab, I am thankful to you for inviting me again the conference. And I will be associated even, for example, I am interacting with your R&D laboratory in Kerala. For example, I talked to Dr. Shubangi that saying that, you see, cerium nitrate, if I am making from cerium carbonate to cerium nitrate, so I say that we have to have such a technology where we can go directly from cerium carbonate through something to the oxides. So all these things are to be discussed along with your people. So normally what happens, so we develop certain things and then we try to pass on to your people up to what extent they can pick up that, or when they are doing, what are the problems at your end, we do not know. So we need to work together. I am ready. I will be very happy to support your people for developing the material.
Thank you, Dr.
So I wish all the best for your future endeavor. And NCL is the best place for doing basic work as well as certain applied work. They have the best facilities for catalysis. And yesterday, as he said, nearly in Europe or in US, nearly 40%, 50% rare earths are used in catalysis. And now new areas are coming up. So Syria, everywhere, if you talk in catalysis, Syria is always there. Syria, zirconia. Keep in mind. When you say catalysis, Syria as a support along with alumina is always there.
Thank you, Dr. Dongre. I think
thanks a lot.
Thank you so much. I think you touched upon very important points around the quantum jump from lab scale to commercial scale, especially when you have a kg scale technology or a gram scale. How does it work in the industry, and requirement of the industry in terms of the engineered rare earth materials, in terms of their specifications, and whether we can live up to that. And of course, the more effective partnerships between industry, academia, and R&D labs. I think with that, I go to the next panelist, Professor Chandrasekharan Srinivasaran. I think probably I would request him to talk about the sector, but focusing on certain other themes that we mentioned in the earlier. One is around sustainability. So we are seeing a lot of focus on sustainability, especially in the rare earth sectors. There has been challenges for liners in Malaysia in terms of handling the radioactive wastes. We have been interacting with Australian companies recently, and they are also facing some challenges. That is one in terms of how do we have sustainable processing. Secondly, in terms of the secondary market recovery of from secondary sources, and of course the enabling measures in terms of policies that the government needs to bring about for this sector to thrive. So these are I think the specific focus areas, but of course you can talk about the sector as a whole, Professor.
First of all, can you hear me clearly? Yeah.
Yes, very much.
Can you hear me?
Yes, we can hear you.
Okay, thank you very much. I have a small presentation which I will upload now, and then I will start what I have to say. Thank you. Just keep this now. So first of all, it is a privilege to be a part of this Platinum Jubilee celebration of IREL. I have very fond memories of IREL because when I was a student at IIM Calcutta, I did my summer internship at IREL. And I'm very happy to hear that they have now completed 70 years. I would also like to take this opportunity to thank Dr. Singh for asking me to share some of my views on what India should do in the rare earth part with this very distinguished set of people who are gathered there to look at drawing up some kind of a roadmap for the rare earth industry. Now, one way to look at the rare earth industry is to look at it in terms of an evolutionary framework. A lot of industries follow a kind of S-curve of evolution. And the rare earth industry is not very different from many other industries. And if you look across many industries over a period of time, you would find such a typical kind of evolutionary process in place. And each one of those industries, or the evolution of an industry, have certain distinct phases in the evolution of the industry. For example, here, sorry. One minute, please. Escape. When you look at each one of these industries, they go through certain clear phases. There is what is called an incubation phase, where the industry is just beginning to evolve. It either emerges from an existing industry, or it comes up ab initio because of some breakthrough in technology, or a change in circumstances, or some market-related or demographic-related factor. It could be any one of those factors. And then once it emerges and it's able to cater to a few niche applications, it actually moves into what is called a diversity phase, where the particular technology or the product that enables that industry to start is then moving into a number of other areas, and it kind of proliferates into the ecosystem, or the economic ecosystem, to say that. And then as it evolves further, it becomes more focused. A lot of things get more directed, and you get into what is called the growth phase of the industry, which normally consists of two parts. One is a very fast growth part, and the other is a relatively smaller growth part, or a slower growth part. And then it finally reaches maturity, and then at the stage of maturity, it kind of declines. Now, one of the hallmarks is that the strategic imperatives facing both the industry and the government in each one of those phases, and what the government should do or should not do, or what industry should do or should not do, is dependent very much upon the particular phase in which the industry is. So we need to if you want to do something in terms of a policy intervention or a strategy intervention in the rare earth sector, we need to be able to position a lot of these value chains that Dr. Singh talked about into where these value chains are in the context of where the Indian industry is in this global kind of industry cycle. Now, coming back to the rare earth part, and you can see that the incubation phase of the rare earth industry, after the discovery of the rare earths in 1880, took a fairly long time before actually many products became available in terms of major markets. Of course, the most important and the early application was gaslighting, and then it followed up with flint. And then in the early 1930s or 40s, glass and optical glass became kind of important. A lot of people know about the Manhattan Project and the ion processing, as well as solvent extraction, were two major processes that were involved in the Manhattan Project. And they enable the separation of very closely linked elements in the periodic table from each other. And therefore, the rare earth industry actually got a fill-up after the Manhattan Project. And the first major application in the electronic area was the phosphors, the European phosphors that were used in the early color TVs that were made in the United States. So as that happened and the Manhattan Project happened, leadership moved away from Europe into the United States. And for the period in which what I call the diversity and the growth period, the US led the way for the world. And it became, in a sense, the capital of the rare earth industry. And it moved into a lot of high-tech products. People talked about catalytic converters. Catalysis, of course, was an important application. Magnets became important. Fiber optics, as it emerged, and the amplifiers used to connect networks. Ceramics, chip capacitors, a whole lot of high-tech industries came out of this growth phase. Now, the Chinese, as somebody had already mentioned, have a major resource of rare earths, and they were smart enough to figure out that it was very important and strategic in nature. And going back to the 70s, they actually enabled a lot of things to happen inside China. And by the time the US had assumed the leadership position, the Chinese had already identified it as a major strategic area where they would put a lot of effort. And one of the advantages that the Chinese had is that the economic models that the US was pursuing, what is normally termed as a neoclassical economic model, facilitated outsourcing of a lot of these things because financial efficiency and cost cutting became the mantras of business. And therefore, a lot of the technology and the products went out of the US, which was clearly the world leader, into China. And China leveraged that position in order to become this global monopoly for rare earths today. So this is the kind of story that we are talking about. And one expected, if you were looking at it in the 1990s, you thought the industry is going to mature and maybe it's going to decline. But a lot of new things have happened in the world, including climate change and the impact of climate change and the fact that you are going to go green, and therefore there's a huge demand for rare earth requirements based upon the plans of many, many countries globally to go into this green energy markets. Now, before I kind of go away from the slide, I'd like you to think about this a little bit because underlying the industry, the rare earth industry is not one industry. It consists of products that come from many, many industries. A magnet which powers a turbine. It can be a rare earth magnet, or it can be a ferrite magnet, or it can be, an electromagnet or any other kind of magnet. A motor that powers an automobile can either be a permanent magnet motor based on rare earth, or it could be something else, or it could be an electromagnet too. So there are a whole lot of what I call product cycles within other industries, right? Which kind of influence the rare earth industry itself. So the industries, for example, the automobile industry is connected in a fairly substantial form to the rare earth industry if the demand for electric vehicles is going to increase. Clearly, so there are connections between these industries, specific products in each one of these other industries. And therefore, underlying products and how they connect up to the rare earth, either backward or forward connections, as somebody mentioned, is a kind of important factor. And behind that, you also have a lot of technology cycles. And what are those technologies? Improving the efficiency, samarium cobalt, because cobalt became very expensive, neodymium, boron ion magnets kind of got discovered. So there's a whole lot of other factors that also enable technological choices to come up and kind of influence. So you have a technological cycle, you have a product related to an industry cycle, and a product related to an industry related to the RE cycle. So you can see that we are looking at a fairly complex chain of connections, and these connections are the ones that we have to look at if you want to understand what kind of a thing can India do. So this is really the point I want to make. I'm sorry I took a little bit longer to do this, but I thought it's important for us to understand what is it that we are really talking about. And just to give you a simple example, just told you about magnets. A typical, today's magnet, you have four possible things. If you look at the evolution of magnets over a period of time, aluminum, nickel, cobalt magnets, followed by ferrite magnets, followed by samarium cobalt magnets, followed by neodymium iron boron magnets. There are 4 cycles. A typical product in an industry may use one of them, or may use combinations of them, or you may use an electromagnet. So you have a whole range of architectural possibilities for product configurations. And we need to find that part of the product which may use a rare earth component. So the question of how the demand side is going to work out and how the estimates of rare earth in the supply and demand are going to work out is going to depend a lot upon how well do we understand these specific aspects of product value chains. And more important, how do they integrate with the final product and the kind of supply chains that people talk about, how complex they are. So all of these are therefore connected, and we need a way in which these connections can actually be mapped and figured out. I think Dr. Singh already made this point. Materials constitute a small fraction of countries' GDP. Materials like iron and maybe steel and aluminum, a whole lot of other things are fairly bulk materials, and therefore they are a little bit larger in terms of their contribution to the GDP. Now, rare earth materials are much smaller in terms of output, and therefore maybe a smaller fraction of GDP. But unfortunately, or if you want to build a modern economy, or an economy that is going to be relatively in the front rank of developed countries,
you need to worry about how these elements are going to integrate with a whole lot of value chains. So you're looking at a lot of downstream value addition products in industries, and you're looking at intermediate products incorporated into final products. So you need to worry a lot about a fairly complicated network of connections between the supply end and the demand. We need not to worry too much about the supply. We need to worry not so much about the demand. We need to worry about how the total aspect of both the supply and demand integrate in terms of providing a functional value to, in my opinion, the Indian customer or Indian consumer. Now, I'm not going to talk about the strategic sector at all in what I do, even though I've done a lot of work on that. I would rather try and look at the commercial sector, because I tend to believe that the real challenges that we're going to face is going to really come from those from that commercial sector. So I will try and build up an argument for how do we look at prioritizing our approach to the RE development of a modern RE ecosystem. That's really what I will try to do. In order to do this, I would like to give you a simple example of how materials actually connect up with different industries. So I'm going to take a very simple example. We have a very simple economy where output of coal is 100 units, and about 60 of them go into power, and about 40 of them go into steel. And therefore, we need to look at the connections between the coal sector and the power sector, the coal industry and the power industry. So you can see that out of the output of coal, which is 60, it goes as an input into the power industry. And the output of the power industry is 200. So we can build an input-output kind of matrix of coal and power can go down into something else, steel can go down into a whole lot. We can build a kind of matrix where we can use these input coefficients of how much input is required to produce a unit of output in order to kind of connect up the material requirements in terms of the underlying supply and demand in terms of quantities, right? So this is a very simple idea, but in a real economy, you can draw a very complicated kind of chain. So this is what I would call, in the same way, you can look at a backward value chain. If you want to look at the implications of the power industry on the coal industry, you know that 60 units of the output of coal is actually the power industry. So 60 by 100 will be the backward linkage coefficient. So the matrix can consist of a link between coal and power and a link between power and coal. They can connect up in all kinds of ways, and you can have this complex array of an input-output matrix, which will capture the essence of what Dr. Singh said is an ecosystem. I mean, the word industry is no longer very relevant. It's more like a network. And as I said, so this is the kind of thing that we will look at. Now, you can complicate this a little bit by adding what I would call the money part of it, right? And the moment you bring in the money part, you look at the question of supply and demand. It raises a whole lot of issues. I would argue that for the kinds of work that we do from a technological perspective, it may be useful and more relevant to actually look at the coefficients in terms of numbers, and that's what I think we should do. More quantities are important rather than the money, because markets fluctuate and values fluctuate. And output in terms of value doesn't really tell us very much about the hard day production and supply and demand of the physical quantities that are required in many of the RE value chains. So that's really what I will try to focus on. And how do we kind of apply this framework to the RE context in India? That is really about a few years ago in NIAS, we had looked at this RE value chain, and we looked at RE as a kind of strategic sector that we wanted to understand. And we therefore put down what I call an input-output matrix. It's not actually an input-output matrix in traditional sense. It's basically a linkage matrix, I could argue, where we looked at all the RE elements, and we kind of mapped it into all the intermediate products and all the final products that we could think of. And we came up with a 92 by 92 matrix, which basically tells you, what is the total RE ecosystem and how does it look like. A 0 represents no connection, and a 1 represents a connection between the two components. It's a very simple representation of all the complexities associated, basically to kind of tell us what are the various products and industries and sectors that we need to look at in order to understand this total ecosystem and how do we go about it. So this is real.
So
I don't know. Everybody knows that a matrix and a network are mathematically equivalent. So if you can put a matrix, you can also put a network. So this is the network that we got out of that 92 matrix. And as you can see, it's kind of very difficult for us to understand it. I mean, I'm sorry for the mess that you see, but it's really messy. Right? And therefore, to figure out so obviously there are some parts which I can see a lot of what I call a lot of lines concentrated on some of the nodes in the network. Obviously, they're more important than other times. But the point I'm trying to say is that it's complex, and we have to unravel this complexity in some form so that we can come to the job of trying to apply some priority. Right? How do we go?
So, sir.
So that's really what I would try to.
Sir, sorry to.
But one of the advantages of the network is we can eliminate a lot of the stuff. Supposing we want to look at only one part of it. Let's assume that we want to look at lanthanum. We can actually do that very easily with this kind of approach. And you can actually look at all the connections that lanthanum has. You can do that. Or you can take an end product like an automobile, and you can look at all the elements that are there as a part of it. And therefore, you will have a complete understanding of all the things that you need to know. What kinds of industries do I have to worry about? What kinds of products in those industries? And how do I actually go about trying to understand what should I do in terms of any kind?
Sir, thank you, sir. Thank you. Just a time check, sir. I think we are already running short of time. So maybe if you can.
I will go through very quickly. Okay. Yeah. So this is the cerium which people talked about. I'm not going to dwell too much on it. Right. It's a part of it. And you can also prioritize the rare earth nodes that we are talking about very critically. As I said, you can look at a particular node, you can look at the inputs into the node, outputs of the node, add them up, and you can then rank them. And you can see here I've put some of the major rankings: permanent magnets, catalysts, fuel cells, automobile, etc. You can do that. The more inputs and the more outputs they have, the more important is the node in the network. So I'm not going to elaborate. This is just a summary of whatever we said earlier. And let me come back and quickly come to the Indian position, right? If you look at this global chain, I would argue that even though India has had a history of 70 years of rare earth, we have largely been an exporter of the raw material and maybe some limited intermediate products. China is the monopoly provider in the world. And, my point would be the US is actually declining in a sense, and it's now figured out that rare earths are important, trying to compete back with China. And therefore, it's trying to do that kind of thing. So the point I'm making is that India needs to go up this value chain. It needs to go up the S-curve. It therefore needs to find a way in which it can do that. So it needs to get into the product space. It also needs to get into the material space. Both materials and products are kind of important. And that's what India needs to do. So let me just get this out. Yeah. So how do we choose? That's the real question that I want to pose. So my point is, the one approach that we can definitely take is the fact that we are in the process of a major green energy challenge for the transformation of the country through, and RE is a very important component of this green energy transformation. So what are the sectors that we can think of? Obviously, one of the most important is wind energy. Right? And there are two value chains in the wind energy sector. One is an offshore segment, and the other is an onshore segment. The challenges that we have in both of them are kind of different. Right? And therefore, the kind of application that we might want to do, for example, permanent magnets is one solution. A ferrite magnet or a rare earth magnet is another possibility, or a non-rare earth magnet is a third possibility. So you're looking at a technological architecture of all this. And each of the companies in that business may have a different type of model. So we need to be able to work back from the microstructure of the industry back into the industry overall structure, and then look at the trends and see what's going to happen. Now, electric vehicles, again, you consist of many, many types of vehicles. Two-wheelers are obviously more important than four-wheelers. Three-wheelers are also quite important. And permanent magnet motors is one solution. Rare earth magnets in permanent magnets is another kind of approach. So we need to worry about which of those industries, so the two-wheeler is different from the four-wheeler is different, the three-wheeler may be different, buses and trucks may be very different. So we need to worry a little bit about where Indian industry is with respect to each of these and how do we actually look at the structure of the industry and take that structure into account before we decide on what kind of a strategy that we want to do. Of course, automobiles otherwise also is a huge industry, catalytic converters, many of the specialized applications are there. How do we address that problem? That's an issue. So what I'm trying to argue, again, coming back, is each one of these sectors is different. For example, the offshore energy segment in wind energy, for example, is in the incubation phase of the life cycle. It requires a lot of government support, technological support, help with markets. Whereas I would argue that the onshore segment is either in the slow growth phase or in the maturity phase, and the kind of support that it may be very different. It may need some expansion of markets with more wind energy, maybe more efficient wind machines, etc. So the structure of the industry itself, whether it's a concentrated industry, whether it's a fragmented industry, a competitive industry, all of those factors will decide on the kind of approach that we want. So the value chain that we're looking at for the onshore segment is kind of different from the value chain that we're looking for the offshore segment. And we need, therefore, to take that context into account before we decide on what kind of policy intervention would be. So this is really the point that I'm making. We can look at two-wheeler, three-wheeler. Two-wheelers may be much ahead of the four-wheeler electrical segment. The automobile market may be behind the two-wheeler market. The four-wheeler market may be behind it. So all these kinds of things we have to worry about. How can we capture the RE part of those value chains, and what kinds of interventions the government should make in order to do it. So the other thing we need to do is, I gave you a kind of connection matrix, but each one of these connection matrix has to be, we now need quantitative input-output numbers to that matrix. In addition to the connection matrix, we need to populate that connection matrix with these numbers. So we need the forward linkage coefficients and the backward linkage coefficients so that we can do a proper understanding of the demand and supply. And we can do it at any point in the value chain of a particular.
Thank you, sir. I think it's really, I think it's
okay.
Wonderful hearing you.
Give me 2 more minutes and
Sure,
I'm done.
sir, sure.
Okay. So I'm saying, so what is the logic of this? So I am only trying to say that we should not adopt, as far as rare earths is concerned, it should not be a top-down policy intervention. We need to worry about the context of the value chain, the industry structure of the value chain. Each of them requires a very, very specific and clear approach. And so it should be a bottom-up approach rather than a top-down approach. That is one of the most important requirements that I want to say. Once we do that, we will also identify the various stakeholders. IREL and the Department of Atomic Energy may not be the stakeholder or the major government entity involved in the automobile industry, or I don't know, in the wind energy industry. We also need to look at the company structure and the number of companies and the role of R&D in those companies. And how do we look at the government R&D sector and how it can be incorporated in this and that. Those specific aspects of it will only come when we do this detailed assessment of each of these critical value chains. And my argument would be that the green value chains, especially related to wind energy and the two-wheeler industry, and maybe we should look at some of the more traditional industries like glass, because they already have established capabilities. And, so that, the other so-called non-important RE materials like cerium, etc. So this is really what we want to do. So, and this will also shed some light on how easy or how difficult is it to bring in an RE component into the supply chain of the existing companies in each. So it will enable us to rank even these 7 or 8 value chains that I'm talking about in some form, so that we can have a more nuanced and a clearer idea of the kind of strategy that we should adopt. We should not have a one-size-fits-all kind of approach. We should build a plan which is based upon the micro detail or the industry detail, rather than a plan that is dictated from. That is really the point. So we need really a national plan that comes out of these industry kind of value chain analysis that I'm talking. And we need to, as somebody pointed out, we need to worry about many kinds of risk. How do we elevate risk? There may be R&D requirements. How do we promote it? We need to worry about market buyback arrangements, especially government entities can help nurture an industry, push it from the incubation into the diversity phase, etc. So there are a lot of things which can be done. So each one of those measures that we need to take will only come when we do these detailed value chain analysis. And obviously, we can't do all 92 of them. We have to pick and choose. And my view would be that we should take the green energy value chains as the first priority. That should be the way in which we go forward to build up what I think is a national RE mission. It's a national RE mission. And it's beyond IREL and DAE in a sense. It should be a national mission. That I think is the key point that I would like. And if we do that, I argue that the international environment, India is not exactly a small technological part. It's also a fairly big economy. And the international climate is such that the China and the US is having major problems. Europe is also having major problems. And I tend to believe that the overall alignment between India and US is favorable. The rare earth market in the world is going to grow enormously. I mean, the green energy plans of the Western, of the more developed countries is going to grow enormously. So even if you have a problem in being able to meet import, indigenously do everything, we can still export a lot of it. I think those possibilities exist. And we need to work. So my point is, the global environment is favorable. Can we get our internal act together? And that is really the question. And I think we should be able to do that. We have the capability, we have the resources, we have the people. But we need, in my opinion, a major national kind of coordination effort, which is a kind of intergovernmental department, inter-industry. So each one of them has to be kind of separately conceptualized. And maybe we need an umbrella framework to look at it as a problem. So that's really the point I want to.
Thank you, sir. I think pretty much.
I have finished. My apologies.
No problem. I think you have touched upon a very important point around the national RE mission, especially when if you look at the key factors for a self-reliance. One is demand. Demand is already there in India and it's going to grow significantly. We are more worried about how the supply across the supply chain is fulfilled, technology as well as the government support. I think this is a good way in terms of what you said about partnerships, especially with the Quad. I mean, already that Quad is very active in terms of rare earths. So my next question I would to Dr. Singh is around that there are two elements. One is, if I look at particularly similar kind of industry in India, which is around the entire solar PV cells and modules, and even the battery chemistry in terms of advanced cell chemistry for cells and batteries for electric vehicles. Particularly if I look at the PV cells and modules, government has come up with a PLI scheme where they are going to give certain incentives based on production. Also, there is a plan to have a BCD in place, custom duty, so that the industry, domestic industry, kind of thrives over the next 3 to 4 years. Similarly, we are seeing PLI for advanced cell chemistry in batteries. So do you think it is time, as a part of the RE mission that Professor Chandrasekhar also mentioned, that we should have a mission where there should be some support so that the domestic industry, it can be self-sufficient, and some promotion support and all those things from the government?
In my opinion, you are very correct, because if you look at all these years, from 1950 or maybe 1947, it was a misconception that the rare earths are only with DAE. Actually, our activity or our mandate was to extract radioactive substance, because the source was radioactive for rare earths in India. So our activity was to separate the radioactive element and then provide it to the market. So means it was open for the industry all along. But since industry did not come in these many years, so therefore this raises the question that why it has not come. So probably now we are emerging on a conclusion that there is requirement of certain support. And on this, I would also like to mention that last year we have made an initiative that we have released an expression of interest. We wanted the industry to come forward to manufacture magnet, etc. And we had been successful in our endeavor. certain industries came forward, but ultimately they have requested the same kind of means support from the government. So they have asked for this PLI, they have asked for this a kind of safeguard duty, and so many certain other aspects which we have also forwarded to the government. So those supports are required because, as I have also said earlier, and Dr. Chandrasekhar has mentioned in the terms of national mission, I have said in terms of means we are competing against a mature technology and monopolized resources. So without support, I think this industry or ecosystem would be a difficult proposition. So with your permission, some more points I would like to address, which are raised by other panelists, and as well I also left it for the means concluding part. The first and foremost, what Mr. Verma has spoken, and I fully agree with that. Whatever resources are explored and the availability of resources is indicated, actually we have to ready with the technology, and we need to be ready in with our whole system, so that when it is required, then we can actually exploit it for the benefit of the country, for the benefit of the industry. So that specific thing we are already in that system, and we have been doing it. Only thing that when it becomes a interdisciplinary, like if a polymetallic deposit is there, then the mandates are given by the government, and we are not supposed to invest our resources for the mandate which is not given. So maybe I think certain collaboration would be required with the laboratories, with the other industries, so that the other metallic deposits also can be established. So, however, I agree with his version that we should be ready with. And there is other things also. Suppose whatever contents are there and the demand supply equation is getting disturbed over the period of time. For example, one of the TFR we have conducted for the same Ambadongar for a very small area. So at that time, the NDPR price was around $50 a kg, but today it is around $95 a kg. So that almost prices have become double. So this will keep changing, but we need to look at the from the industry viewpoint, from a sustainability basis, whether sustainably how much quantity can be produced and how much quantity can be supplied to the industry. So with these aspects definitely require more analysis, more work to be done. Second thing, certain points Dr. Dongre has raised, and I fully agree with his analogy of cotton, then cloth and thread, etc. So what I would like to highlight that we are into cotton and thread, and this making cloth has not been mandated to us, then coloring it into a nice fabric and making it into a very highly aesthetic way to the market, that has not been mandated to us. So anyway, but that analogy was very correct. So as like any other industry, there are segments like if you look at the rare earths, there is a segment that exploration and then establishing the resources. So one of our sister unit in DAE, Atomic Mineral Directorate, from where Mr. Verma was the director earlier, they do it. And then they provide us the resource. So then we do mining, concentration, then we do mineral separation, then we do rare earth extraction. So the rare earth extracts, after the rare earth extraction, it was not means our activity, but when the industry was not coming forward, so we went into refining also. Then thereafter, the area through which we have connected with each other, that was a Technology Development Council. And then this Department of Atomic Energy had given us that particular mission, that with the help of institution, we need to develop certain technologies. and marketing part was not there included. Same way now we are doing another mission that is in terms of RE theme park, in which again department is giving all financial means support, and we with the help of BARC are going a stage ahead for the means manufacturing the metal of these rare earths, and maybe then we will try to encourage the industry if they take it up. And as far as branding is concerned, to the area which we deal, we have an international brand, and in those material, anybody if ask for IREL brand, it is well means recognized brand in the international market. But you have rightly mentioned that if this area has to be developed, and if those mandates are given in future to us, definitely we will be needing a separate team. We would be needing separate resources. We would be needing a separate entity rather. Then only this could be taken up. And the specification part of Syria that you have rightly noticed. But what happened that what is our product and what product a catalyst manufacturer is needing, there is a gap. So our product goes to an intermediary industry, then they will make maybe for glass polishing or maybe for catalyst, and in glass polishing itself, they will receive the inquiry from the user industry, and that much tonnage only they will make tailor made. So there is an industry in outskirts of I think some at some distance from Vienna in Austria, Tribeca. So they take care of, they buy cerium oxide, what we produce, that type of material, and then they make a tailor-made polishing product for and supply to whole of Europe and America. Same way, this material is supplied to, for the sake of catalyst, to BASF, and there is a Solvay outfit in Japan, as well as yeah, I think mostly these two products. So there is a gap between our product and then the industry, user industry is needing. So user industry will go for catalyst. Ours is a cerium oxide. In between, there is a intermediate industry required, which is not existing. And the plight of this intermediate industry is also not very good in India. I will mention an example. When this COVID-19 was means pandemic emerged last year, the first affected was these intermediary industry, because the user industry will stop the order. So then the product manufacturer will go for a go slow policy, and this intermediate industry will lose the link of supply of material in that period, and as well he will lose the market. And whatever changes are coming in market, he has to supply at the same rate with very, very low margin. So this segment is not developing in India very well, because the margins are very, very limited and the risks are very, very high. So same is the problem with our rare earths. If the intermediate industry is not there, probably a system has to develop which can support the intermediate industry. Then the third one, which I intentionally left in my discussion, which also I think Dr. Chandrasekhar and you have touched upon, that is a dilemma of the industry. See, when now I am speaking on behalf of the industry, because we are part of that also. So industry dilemma is this, that they have to continuously produce with consistent quality and with low rejection. So they can't experiment because they have to ensure certain returns. Now, if I give them a technology and ask them to develop, they will first look for what is the IRR, what is the ROI, and he has to depend on bank loan. So if he doesn't see that, the bank will not give him loan. So this financial issues will be there. So again, the way where the industry dilemma comes, this is one dilemma. The another dilemma is that, suppose, let us say, washing machine, he has to buy a motor. Now he has two options. He will put one person for sourcing, and that person will sit on a desk, research, and find out who can supply him a very low rate. But when same industry has to develop a vendor, then I think they will need more manpower. Then sometimes the cost, if the cost of this motor is high, then their end product will go out of the market. So instead of taking that market risk, he will try to buy it from wherever it is available. So this industry who can actually develop the vendor, their obvious preference will go for outright purchase of that product in order to maintain his price in the market. So this industry dilemma, who will overcome? Again, the question dwell upon what Mr. Rajiv stated at the end: requirement of PLI and requirement of certain support. So basically, uh, what we are talking is about an industry which is almost non-existent. And here I would also like to clarify one thing. Uh, Establishing industry which uses rare earths is not part of REL mandate. So it has to go into a interdisciplinary segment. There would be requirement of support. There would be requirement of a different team. There would be requirement of a separate skills. Those skills need to be developed. Those entrepreneurship capabilities have to be developed. There should be a separate chunk of funding arrangement has to be made. What elsewhere it has been done in other countries, and then only we can feel that some growth is coming in this industry. So I hope, Mr. Rajiv, I have covered probably your question, or
Yes, sir. Yes, sir. Yes, sir.
something.
Absolutely. Absolutely. So, one last question from my side is, as a takeaway from this conference, which is the roadmap for self-reliant India and RE and energy security. So, what would be in your opinion, the top 5 or 3 takeaways or the imperatives to work upon as an industry in the next 2 to 3 years?
Yeah, I think this is a really excellent question. So the first thing which Dr. Chandrasekhar has highlighted, say today's requirement is a clean energy. And for achieving clean energy, I feel that a clean development mechanism need to be developed. And this clean development mechanism will not confine to something specific. It will take the development of materials, development of machines, development of equipments, the funding arrangement, and so on and so forth. So for clean energy, there is a requirement of specific equipment, and those specific equipment, definitely I feel the incorporation of rare earths can improve their performance, and this is how the technological development is taking place elsewhere as one of the part of that, besides the other things. So this is one thing. Second thing, this of course magnet initiative have already been taken, but this in case of magnet, there would be requirement of the support system, which I have already forwarded what I have received from the industry, and hopefully something positive will happen in that direction. And third is, in my opinion, uh, rare earth has to go hand in hand with R&D. And as we have worked with NCL, I would call upon other labs also, please keep on doing research in extramolar level. Whatever you are doing, try to see by adding some rare earths, and please see if performance improves. Maybe in that process, we will reach to some better conclusion and something original for our country. So these are, I think, these are the 3 things which we can take away from this conference.
Thank you, sir. Thank you so much. So I would like to ask the same question to other panelists as well. What would be their, in their opinion, the top 2 or 3 or 5 takeaways or imperatives for the industry to work upon as an urgent basis?
Yeah, taking the lead from what Dr. Singh has just said. Sir, you have told one very important part, that is a kind of major impediment in terms of growth, because you are producing the metal, oxide, chloride, whatever it is required. But in between, there has to be some industry. Which industry can take those things finally in terms of the product, which you said, key besides out of your mandate, that is technology for production and marketing you have taken. See, my humble submission is, in this kind of the forum, you have brought industry, R&D in a single platform, where a very good interaction is there. Since you are, right now you are the only agency, only body which is producing rare earths, and also having maximum available knowledge in the country. Henceforth, you should be one of the frontline engine to invite the industry to take the chance, and obviously with the all those PLI, PCP or whatever the incentivization is there, support has to be there. Without support it is not possible. In India, if we really wanted prolific growth of RE, just like any other things, we do need somewhere those bridging the gap of industry, which has to stand with the support of, right now with the IRL, because they are the frontline runner, have a maximum knowledge of material, and they are ready to produce any kind of the specification, what are required for the industry. So to take away this forward, more interaction, more industrial kind of the interaction, inviting them, and even some kind of the proposal where government should really help out to develop this sector, because in coming time, whatever the projections have been made for EV and other things, 2030 or 50, I'm very sure this, the initial stage, those challenges can able to overcome. Secondly, we need more R&D input, particularly in our proving high-grade resources, and also better developing better beneficiation technological parameters by R&D, so we can able to treat even slightly low standard ore in comparison to the world average. These are the two major things I wanted.
Thank you, Dr. Verma. I think you have touched on a very important point around industry interactions, in end use and supply interactions. From my experience, I've been engaged with Ministry of Steel as well. So one of the dilemmas they had is, they were looking at import substitution, and a lot of the end use industry like shipbuilding and defense and railways, they were actually importing, where the steel industry had the capability. So one of the things that really worked for them, and now of course we are seeing more and more companies manufacturing in India, for example, rails and specialty rails and defense regulated steel. So it's more about the industry interactions, the workshops they had over the last 2 years. So maybe this is a good takeaway from this, as you said rightly. I would next move to Dr. Dongre. Dr. Dongre, if you're there, what are the top three takeaways for the industry or the RE industry from this conference, which they can work on over the next 1 to 2 years on an urgent basis? You are on mute. Sir, you are on mute. Yes, now.
Hello.
Now you're audible.
Yeah. Dr. Singh, I'm thankful to you for considering my suggestions. I spoke extempo, I was not prepared. But what I have seen, you see, now after working in NCL for such a long, and then now in the market for delivering the product, I know both the sides of R&D and manufacturing and marketing. You see, we have a lot of experts around us, but unfortunately what happens was we play a role of advisors. and finally you have to act, because you are the person who will be delivering the products. We can deliver lectures, absolutely no problem. We are very good in that. So my first request would be, as you rightly said, that if you want to really go into the market with rare earths, because I know you are very nicely doing your mandate, whatever has been given by government to the IRL, supporting the strategic, requirements of our country, supporting atomic energy commissions and things like that. But now, for going into the market, sorry, please.
Slightly, I would like to correct here. Actually, we are 85% into commercial market. Only 15% strategic. Yeah. So
nice.
means, yeah. That's actually, yeah. IRL has 30 products. So this, what happens when we look at with the perspective of one product, normally that kind of perception is made. But if we look at all together, 85% we are commercial, 15% only we are strategic. Yeah.
Very good, very good. So now the area in which we are working, for example, Dr. Shubhangi Umbarkar, myself in catalysis particularly, is a very good area. And in catalysis, normally it is not something like in electronics, whether it fails and it works. So in catalysis, sometimes you get 90% efficiency, sometimes 95% efficiency. People will expect 100% efficiency, but you will have market for your 90% efficiency also. So catalysis is such an area where you have a flexibility for playing depending upon the product. So my request to you, that first takeaway is that, you can identify one or two products which you feel that this can be pushed in the market. So it's something like low hanging fruits. So identify one or two products and see that they are scaled up and they are meeting the requirement of the industry. And then you get confidence that you can supply this consistent quality material to the people. Then I'm sure, you see, once you have a good material and the industry has got a good confidence, definitely it's not difficult to enter in. So my another takeaway is that you have very good interaction with the industry, but now, there is a company called Sukemi, BASF, Johnson Matthey. These are the people, EcoCat. For example, EcoCat, indigenous company which uses materials from the nearby. So we have very good interactions. So best way, we will have a very good tri-party kind of thing, IREL, NCL and these industries. So if you make a small consortium for another project, because base has been created, now this has to be pushed to the market. So this is what my appeal would be, that IREL, NCL support and the user industry, because user industry also had to take interest, because now in Pune we are interacting with one company called Verak and they are happy with that, but there's a small company taking care of only Bajaj. So there is an opportunity and we will be very happy to support your R&D people in scaling up, pilot plant, other things, characterizations. We have all the facilities. So takeaway would be at this moment would be that we will identify one product or two products and push it as far as, with our maximum capability. So this is what I wanted to just support and request IREL to go ahead. Thank you.
Thank you, Dr. Dongre. Professor Chandrasekhar, top 3 takeaways for you from this, from the conference as the industry. You are on mute, sir.
Hear me? Hear me now?
Yes, we are audible.
Can you hear me?
Yes, you are audible.
Yeah.
Can you hear me now?
Yes, sir, you are audible.
Okay. I think Dr. Singh put it very well. I think the green energy challenge is the one that is most important for the country. It is an opportunity space because we are still in the early stages of the evolution of many new market segments and product segments, and the underlying technology possibilities are also substantial. I'm not so sure we should always look at an indigenous approach to doing the technology. I think industry should have the freedom to be able to make those choices. But I think we can definitely look for a market for for either the intermediate stage or the raw material or whatever we can do in terms of a value addition to the value chain. I come back, we need to do the micro level work associated with a few important value chains. And I think we need that impetus in order to be able to define a kind of national effort. The national effort is going to be complicated because it involves not one government ministry, but many government ministries. And we need something like a national plan and a way in which a national plan can be implemented. I think this is a major challenge before the government. And unless we do those kinds of challenges, I think the next meeting we will have, we will continue to discuss the same issue. So my point is prioritization, identification of the key value chains, green energy requirements, and understanding what specifically needs to be done at each stage in the value chain. That will automatically enable us to tell you what kinds of incentives, what kinds of easing of regulatory measures are needed in order to promote a proper ecosystem. And I wouldn't rule out imports also. I think industry has its own share of problems, and we should not unnecessarily overdo this part associated with indigenous. We should give them the choice. But we should make sure that we give them enough incentives to make the correct choice. I think that's the other thing. So we need to be much more proactive and much more industry supportive if we really want to do this. Just changing the rules is not enough. We need to provide R&D money, product development money. Maybe, for example, in the wind energy market, we need to be clear that there is a market. We need to have data on wind and speeds and offshore data so that somebody wants to do an engineering construction for an offshore site. All the data is easily available if they can do the engineering design. Because these are pretty complicated pieces of technology. The windmills today are huge, very big. There's also a lot of requirement for RE magnets. So my point is all these things, we need to worry a little bit about it. And I believe that this kind of effort and a national mission is kind of good.
Thank you, Professor Chandrasekhar. I think well said, and especially you mentioned about technology choices should be left to industry. We have been interacting with the solar PV as well as battery storage, industry participants. They also feel the same, and they are partnering with whoever has the best technology at the cheapest price. I think that is, of course, that they're looking at. So I think probably we have come to this end of this panel discussion. Before I request Dr. Singh to say the concluding remarks, I would probably ask the audience if there are any questions for the panel. So that before that. Okay. So fine, I think, sir, we don't have any questions for the panel. So maybe, sir, a concluding word from you, and then we can close this discussion.
Concluding words from whom? Actually, somehow I could not hear.
Sir, from you, sir. From you, sir. From you, Dr. Singh, from you.
Acha, from me only. Okay. So I think the last round, which all the panelists have spoken, that is more or less the final concluding word. And I will just reinforce what Mr. Verma has said, that maybe we will organize such interactive sessions with little more frequently, and so that we have an opportunity to meet and discuss together, and then whatever has happened means from this conference to that we could add on to our knowledge and system and skills of the people who are participating. So at the end, I would like to convey my sincere thanks to all the panelists and all the speakers, participants who are physically available as well as who are connected online. Then the master of ceremony, I think last 2 days she has been there. So with all the efforts of, and Mr. Rajiv also. So with everyone's effort, this the seminar conference could be conducted successfully. And I could find yesterday also, I think the time was, what was the designated time? We have crossed that. Today also we have crossed that. and still everyone is looking energetic, as if we can have more discussions on the topic. So this is the real success of the conference, and thank you once again to all who have actively participated in this conference. And we will see you next time very shortly again. Thank you. So
Check. Thank you so much. What an amazing interaction, and I'm sure this output is gonna help the entire family of IREL and of course our country. Ladies and gentlemen, I would like to quote one of the very beautiful quotes cited by APJ Abdul Kalam. मंजिलें उन्हीं को मिलती हैं जिनके सपनों में जान होती है. मंजिलें उन्हीं को मिलती हैं जिनके सपनों में जान होती है. पंख से कुछ नहीं होता मेरे दोस्त, हौसलों से ही उड़ान बनती है. So today, when we have arrived at the verge of closing of this wonderful 2 days discussion, very important, valuable, interactive, and everyone showed their patience, and thank you for the cooperation. And sir has already thanked, but it's my duty, because we firmly believe that great is the art of beginning, but greater is the art of ending. Every beginning has an end, but every ending promises for a new beginning. So this is not the end, in fact the beginning. So thank you so much from the bottom of our heart, everyone, all the speakers, panelists. First and foremost, I would definitely would like to take the name of our Honorable CMD, Dipender Singh sir, being so cooperative, so visionary, and I'm sure under his guidance and supervision, the family of IREL gonna achieve really very good growth. And congratulations to once again all of you. Thank you so much. Please be connected. And as I said that this is a beginning, so let your spirit be high from today onwards. And our event partner, Eyeball, and of course everyone who have helped us technically online streaming. And let me tell you that our venue partner, Mayfair Hotels and Resorts, one of the reputed venue when it comes to the state of Odisha and beyond. Thank you so much each and everyone for helping us to achieve this wonderful Platinum Jubilee celebration. And thank you for giving me this platform. And once again, I would like to say, take good care of yourself. Keep smiling, and see you all at dinner time, 7:30 p.m. Down the pub, down the hotel, there is a cellar pub, you all would be knowing. So please meet us, and thank you. And you can clap if you're free and if you're feeling relaxed enough. Thank you so much. Take good care. Thank you.
Just a moment, gentlemen, just a moment. Mahapatra ji, please come on stage, sir. For this one lady who has conducted this program throughout these 2 days, I mean, we need to give her a memento to cheer up her and memories for our future. Thank you.
Thank you once again for making me a part of this extended family and wonderful celebration. Congratulations to one and all once again. Thank you.